case everybody just has to. Got it. I have to acknowledge. Got it. Okay. Okay. So let's see. First thing I will ask is, if your name is listed as something that I wouldn't recognize, change it to something that I will recognize, because I'm really bad with names. So the more names I see that are actual names, the better I will be at all of this. And good morning. So let's see, who's the furthest east? I'm curious. Raise your hand if you're east in the Eastern time zone or further east. Okay, so for you, you've already had breakfast. It's almost lunchtime. So, all right. So welcome to class. My name is Scott. My call sign, which I will put up here, is N7JI, which will make some sense in a little while. And I have had my license since 1984 when I was a 15-year-old living in Maryland. My original call was KA3NJI, which was a 3-land call. So if you're in Maryland, DC, or Delaware, or Pennsylvania, you'll get a 3 call. At which time I then, after a bunch of years, moved out to Oregon, which is where I live now, which is 7-land. And so you don't have to change your call sign, but I wanted to after a while because I got tired of saying that I was a 3 call, but I was completely on the other side of the country. For those who are not necessarily interested in long distance communications, that's not a big deal. But if you are on the air and you do a lot of DXing, as it's called, and people, let's say in Europe, are looking for the West Coast and they hear a 3 call, they'll be a little bit confused by that. Not so much anymore, but at that time it was not all that common to be a 3 call living on the West Coast. So let's see. What we're going to do is, for the first thing, we are going to just cover what it is that we're going to do in this class. So I guess I can delete the thing that says, don't forget to record. Thank you for reminding me. So does everybody have a copy of the book that we're working off of?
Yes.
Okay, good. Is anyone missing a copy of the book? Okay, good. So that being said, what I notice about the book is if you have the PDF version, it doesn't have actual page numbers. It has PDF page numbers if you're looking at the PDF file. So we're going to go with the PDF page numbers. So it'll say, we're on page 7 of the PDF, on page 22 of the PDF. So that's what we're going to go with, because this is a new version of the book, and the old version of the book stopped being valid in July. I guess it was July 1st of 2022. So you guys are actually guinea pigs in that you're the first class that I've done since they changed the question pool. So the question pool, let's just talk a little bit about that. Has anyone taken practice exams yet? Been studying? If you're going to take an exam, I strongly recommend taking practice exams. Now, this is the same thing as with SATs. It's the same thing as with, MCATs. It's the same thing with pretty much any exam. If you can get a practice exam and take it, I strongly recommend doing so. Fortunately, unlike the MCATs and unlike the SATs and unlike all those other standardized exams, the exams that we have available to us are not only standardized, but they're actually already prescribed. What I mean by that is what we're going to do is just very quickly show everybody a website, if I can somehow manage to bring it up. Here we go. And we're going to look at exam tools. Now let's look at hamstudy.org. Okay, has anyone been to this site yet? Okay, this is a really good site. Notice you have the technician exam, and you can read questions, right? So you can read questions by sub-element, T1 through T0, and for each sub-element, you have individual sections that you can read all the questions. And notice what you have here. You have this little green answer, and you have this little flip thing that allows you to explain, that allows you to see why the answer is what it is. Unlike a lot of exams, every single question that's in the question pool has been agreed upon along with answers. So if you really wanted to, you could go and study all 415 or so questions, memorize the answers like my wife did, and pass your exam with flying colors. So that is absolutely a valid way to study. That's actually back in 1984. I'll say 1986. That's the way that I studied for and practiced my my advanced and extra class exams, except that you had to read a book back then instead of having a website. But my goal in doing this is to give you a lot of background knowledge that will not only allow you to not only allow you to answer the questions right, but allow you to understand exactly what it is that we're doing and why we're here. So my hope is that in doing so, you'll say, oh, I wonder what the answer to that one is. Oh, I don't remember this one, but I can go figure it out. It also will hopefully get you to the point where even if your interest is just getting a license and being able to use a handheld radio, being the fact that, you know, with more knowledge, you may actually decide, oh, you know what? We do have all these other things to do. Look at that. Well, we have, let me open up that web page again. We do have access to every single one of these things that's in teal. Notice it says amateur. And you look at this chart. This is actually the United States frequency allocation chart for basically all of radio, not just all of ham radio. And everywhere you see something teal, we have access to it. Like there's a slice, and there's a slice, and there are some more slices, and you go down here, and there's another one, and there's another one, and another one. So we have access to all different kinds of frequencies, all different kinds of modulation techniques, all different kinds of experimentation. So the fact that, okay, I just want to operate on the 2-meter band, well, if you've done some reading and you know what the 2-meter band is, you know that the 2-meter band is 144 to 148 megahertz, which on this giant chart is this tiny little teal slice right here that says 144 to 148. That's actually, looking at this giant chart, a very, 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 very small part of the world of radio. So my goal is that you will actually take an interest, I can't guarantee it, but that you will actually take an interest in all those other things. And it might be a couple of years before you decide, oh, you know, I think I want to take an interest in all of those other things, or at least one of those other things. The other thing that I find interesting is that as you get a license and go through the process of learning and go through the process of experimenting, you tend to have these other ideas that say, oh, you know, I never thought about doing that before. And you look at your license and say, oh, well, my license allows me to do this. So one of the big questions that I get asked is, why do we have to learn all this stuff when all I want to do is go out and buy a handheld radio and use it for search and rescue? And the answer is there are plenty of other services, such as a radio that looks like this, for learning how to just use a radio and go do search and rescue. A ham radio license, also known as an amateur radio license, is a lot more than that, because if you look at the FCC rules that govern amateur radio, which we will do, It's not what I would call an appliance user's service. It's actually an experimenter service. And it has a lot of different disciplines contained within one discipline. So even though you may not ever decide that you're going to build your own equipment, your license permits you to do so. It's basically the saying, okay, well, why do I have to, on my driver's test, why do I have to show that I understand all this stuff? All I really need to do is go backwards and forward and make turns. And the answer is, well, by having a driver's license, it allows you to take your car out on the highway, right? Well, I never planned to do that. And the answer is, I don't care that you don't plan to do that. Your license permits you to do so, so you have to be tested on it. So we're allowed to build our own equipment. We need to, as a result, be able to prove that if we decide to do that, that we actually understand what that entails. That means that we actually understand, for instance, when someone says your harmonics and your spurious emissions have to be 60 decibels down from the fundamental frequency output, that we have some understanding of what that means, because we have the permission by virtue of getting this license to do things like that. So now the other thing that I like to add when I do a class like this is, if you have a question, don't bother like raising your hand because I'm not necessarily looking. Just unmute yourself and blurt it out. Say, hey, I have a question. Because the questions that you guys come up with, there's no such thing as a dumb question. So just get that out of your vocabulary now, right? If it's a question, you're asking it because you either want to know more or because you don't understand something. The other thing is that in the process of doing this class, I've actually downloaded this book in audiobook format, and it's a 2-hour read by the guy who wrote it. So in 2 hours, he basically went through the entire book. And we're doing 8 hours today and 4 hours tomorrow, which is, by my math, it's 12 hours. So that means that we've got, minus an hour for snacks and for going to the bathroom and lunch and things like that. That's 11 hours, which means we've got 2 hours of class, which he would be doing, reading the book, plus 9 hours of extraneous or extemporaneous discussions about pretty much anything. So we have time. At times it might seem like I'm rushing through stuff. Really, that's just so we stay on schedule. But we've got time for questions. We've got time for discussions. If there's something you don't understand, something you want to understand better, you're probably not the only one. So don't feel like it's a dumb question. All right. Do we have any questions before we get going? No? Okay. All right. So the first thing I'm going to do is not talk about radio at all. The first thing I'm going to do is hopefully draw this somewhat, I don't know why it keeps doing that, somewhat imperfect circle. And can everybody see the circle? Which is not a perfect circle. I'm going to redraw the circle. That's a bad way to start. Let's redraw the circle. That's a better circle. Okay. So how many quadrants do we have in that diagram? We have 4. These are known as the first, the second, and the third, and the fourth. And when we're on a circle, the assumption is, if we're looking at this circle, we are moving in this direction. We're moving counterclockwise. Notice we go from 1 to 2 to 3 to 4. Okay, how many degrees are there in a circle? I bet you didn't think you'd be doing math, right? How many degrees are there in a circle? I ask you guys a lot of questions.
360.
360. Okay. By definition, our 0 degree point is right here. This is the x-axis, and this is the y-axis. Okay, so as we go around on this circle, let's imagine that we're sitting in a car that's driving on a circular track, and we start at 0 degrees. When we get to the y-axis, all the way up here, at that point, how much angle have we gone through on the circle? How many degrees?
90.
90 degrees. Okay. Now let's keep going around the circle and we get to this point. We're back on the x-axis, but now this is the positive side. This is the minus side. And by definition, this is positive and this is minus. So how many degrees have we now gotten to when we're on the opposite, when we're on the green dot?
180.
180. Okay. How about when we get down to the very bottom at the blue dot?
270.
270. Okay. All right. So we're at 270. And how about when we get back up to the red dot?
360.
Or what's another name for it?
2 pi.
Or what's another name for it?
0.
0. Okay. So we have no idea whether we have gone around the circle or not. We're just back where we started. Okay. So as we go around this circle, what we find is that we go around and around and around and around and around. And we can't tell the difference between the starting point and the ending point. It just keeps wrapping over and over and over. But what's important to note is that we have really four very interesting points. We have at 0 and 90 and 180 and 270 degrees. So now if we were to plot this out and say, okay, as we are looking at how far we've gone, angle, how far above or below that horizontal axis are we? What is our distance above or below the horizontal line? So if we're at 0 degrees, how far above or below that horizontal line are we?
0.
0. So we start right at the 0. Okay. When we get up to the 90-degree mark, how far above or below the horizontal axis are we? And we're going to say this is known as a unit circle. So our radius is 1 unit.
1.
We're at 1. That's right. We're at exactly 1 unit above the horizontal axis. Okay. How about when we get to the green dot?
0.
0. Okay. And how about when we get to the blue dot?
-1.
-1. We're now underground. And how about when we get back to the red dot?
0.
0 again. Okay. So notice we now have 5 very interesting points on that line or on that curve. Well, the distance from the x-axis is a trigonometric function called a sine, also known as SIN. And the function that is drawn out by looking at how far above or below the horizontal axis is at all points is known as a sine wave. If we were to connect all the dots, we would basically do that. Now, if we continue on at, here's 360 degrees. If we were to keep going, what would happen to the sine wave?
It would repeat.
It would repeat. Well, what happens before the sine, all the way to the left of this? It would have repeated. So basically what that means is as this car goes around the track, if we were to plot it, we basically are looking at a wave known as a sine wave that goes around, that goes up and down and up and down and up and down as long as this car keeps moving. Now, we could also do something called a cosine wave, but that's basically looking at the horizontal displacement from the vertical axis, but there's really very little point in doing that at this point. But you can certainly do it. So this is known as a sine wave. And there are some very important fundamental parts of that define a sine wave. One is how big it is. Anyone know what that's called?
Is it amplitude?
Amplitude. That's how big it is. Okay. And how about another one? How about another really important part?
Frequency?
Frequency. Okay. And also, if we were to go beyond that,
Phase?
we can do phase. Yeah. And there's also a wavelength. There's also something called a period. Okay, so there's a lot of really interesting things that we can do with this sine wave. So if we increase the amplitude, we make it bigger. If we decrease the amplitude, we make it smaller. If we increase the frequency, that basically means that we are going around the circle more frequently at a higher rate. And what that will do is compress. It will compress the sine wave. So a new sine wave might look something like this, because we're making that loop a lot faster. Now, it also turns out, okay, at the same time, what I did was I lowered the amplitude, but I increased the frequency, and it would look something like that. So now we can also change the phase of this thing. So what that would mean basically is we are saying we're going to delay the start. So here's the first car, and let's say there's another car that is starting 60 degrees behind the first one. If this is a racetrack, our second car is 60 degrees behind the first one. So here's our first one right here, and here's the second one. And it's basically shifted. Oops, let me draw that right. Here we go, 60 degrees roughly. Same amplitude. Except that's advanced. I don't want to do that. Here we go, it's delayed. So it basically starts later. So it's actually over here. There we go. I finally drew it right on the third try. So that would be known as a phase. Basically, the thing is delayed a certain amount. If another one was ahead, let's draw this car way over here. Well, that would actually get to this part ahead of the other ones. And that's known as our phase. So basically, there's a couple of things we can do. We can change our phase, which changes the crossing points and the starting points with respect to each other. We can change our amplitude, which is the size. So let's say that one of them is going around a bigger track. The track is actually this big. That means that when it made it to the top, it was like 2 units. So it would actually see a much bigger sine wave. And we can change the frequency, which is how fast we're going around, and thus up and down, and what our phase is, which basically shifts it left and right as we're delayed. Okay, so now that we've sort of established this, what we're going to do is we're going to erase this entire drawing. And we're just going to draw a very simple circle. I hope I can draw a nice simple circle. Okay, so here's our nice simple circle again. And we're going to be going around the circle in this direction. And here's our wave that it makes. Okay, so now what we're going to do with this circle is say we're going to increase the frequency by a factor of 2. So let's say that this took 1 second to go all the way around. If I were to instead draw a time, what would the amount of time be that it took to go all the way around? I hope it's 1 second. So if this is at 0 seconds, this is at 1 second. So now I look at, okay, how long is this period? How long did it take to make that picture?
1 second.
Okay, that is known as a period. And what you will find is that period and frequency are inversely proportional. So if we were to take this time and we were to say that now this took 10 seconds instead of 1 second, we would say how many, okay, so it takes 10 seconds instead of 1. So that's our period, 10 seconds. How long, okay, how many times does it go around every second? 1/10. It makes it about this far every second. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. It takes 10 seconds to go all the way around. So every second it goes around about 1/10. It goes around 1/10 of a time. So that frequency would be 1/10 of a thing per second. Well, a thing per second has a name. It's a fundamental unit. Anyone know what it's called?
Hertz.
That's a hertz. A thing per second is a hertz. Okay, so now let's say that our period is 0.1 seconds. Okay, so if our period is 0.1 seconds, what's our frequency? How many times does it go around in 1 second?
1.
If our period is 1/10 of a second, if it takes 1/10 of a second to make one full trip,
10.
10 times. So our frequency is now 10 hertz. And so now you can see that period, which is t, a time, and frequency are inversely proportional to each other. So as frequency goes up, our period goes down and vice versa. So this takes 0.1 seconds. Okay, so now we're going to start to deal with numbers that make a lot more sense as far as radio goes. So let us say that we instead have this thing that's going around this track, and it is going around with a period of 0.000001 seconds, which is 10 to the minus 6 seconds. What would the frequency be? Well, it's 1 over 10 to the minus 6th, which is equal to 10 to the 6th, which is 1,000,000, and the unit again is hertz. All right, well, that has a name. Anyone know what 10 to the 6th or a million is also known as?
Mega?
Mega.
Is it a megahertz?
That's a megahertz. So something that goes around with this, with that frequency, with that time, with that period, has a frequency of 1 megahertz. So now what we've started to do is combine things that happen very fast with very high frequencies. Okay. So now what we can do with that is say, okay, we're going to add something to this. We're going to add some movement. So let's say that I am actually on this particle right there. I'm in a car. And if I now look at the circle as it's going around, right? I'm now in the car that's moving around the circle. As it's moving around at some frequency and time, frequency and period, right? It doesn't really completely matter what it is. And now what I'm going to do is add a third dimension to this. All right. So what I'm going to do is I'm going to take this circle and I'm going to turn it so that we're looking at its edge. So basically now I'm going to rotate the circle so that there's a third dimension, and here's the circle. And I'm going to flatten that out even more so we can't see anything of that circle in the horizontal direction at all. So now we're just looking at this circle on the from the edge, and we see this thing going up and down and down and up, and it's just going up and down and down and up. Does everybody agree with that? We've now taken the circle and we've rotated it so we're looking at the edge of the circle. Okay, so if I were to do this with my phone, for instance, what I can do is say, okay, so here's, can everybody see my phone flashlight? Okay, so we're going like this, around in a circle. Well, now I'm going to take my phone and do this with it. And what direction is my light moving? It's exclusively moving up and down, right? Okay, so now we've taken something that's moving with a sinusoidal pattern, except that it's not moving in this direction or this direction. So what we're going to add now, so we have, this thing is called a frequency, right? If I go faster, the frequency is higher. If I go slower, the frequency is lower. Well, what we're going to add again now is that third dimension. And the third dimension is the fact that this thing is now moving through space. So if this thing is moving through space, if this thing is now moving through space, if it has no speed, if it stays right where it started, what are we going to see? What shape does that make? That would just be a vertical line, right? Okay, but now we're going to start moving that thing in this direction. And what's going to happen to it?
It'd be like one of those sine curves, or
It would turn into a sine curve. But now, what have we? All right, so it internally has a frequency and a period of it moving up and down. But what have we now done in the horizontal direction? We've now added something called distance. And how fast is something physically moving? What do we call that? What do we call it when we say how fast something's moving? Everybody's being so shy.
Speed or velocity.
That's your speed or velocity. Velocity is speed with a direction. So we'll call it a speed. Okay. Now, what relates speed and distance?
time.
Time. Okay. So now we've related speed and distance and time. But notice the time shows up right there, doesn't it? That's our period of our sine wave. Well, now we've added this other thing, which is speed and distance. Well, we know that this thing right here is our period. And that's measured in seconds. Well, what can we also measure in seconds? We have our distance that's covered is also equal to speed or velocity times time. That's a distance. So now if we know that this thing is moving horizontally as well, what we now have is a distance. And this distance is known as a wavelength, because it is the distance that is required for one entire wave to exist. I mean, everyone agrees that's one wave. This is a wave. And what we use for wavelength is the Greek letter lambda. And we usually measure it in meters. Okay. So that is our variable for wavelength, lambda in meters. we also have another one, which is f, little f for frequency, and we measure that in hertz. And we have a formula that relates these two. Has anyone ever seen that before? V is equal to F times lambda. That's our velocity or speed is equal to frequency times wavelength. And the reason this works is because frequency is in things per second and lambda is in meters. So we're now in meters per second, and meters per second is a unit of velocity. So what we can now do is we can figure out, given our wavelength and given our frequency, they're related by velocity. This is actually really profound because this means, for instance, that we can say, okay, well, we're going to take a very simple wave right here. And this is a sound wave. I'm just going to say it's a sound wave because I can say it's a sound wave. And this has a frequency of 1000 hertz. And this is moving through the air. And the air has a velocity of sound through the air of about 1000 feet per second. Okay, so now I can write that equation. V is equal to F times lambda. Okay, and I can plug things in here. That goes there, that goes there. 1000 is equal to 1000 times lambda. Lambda is equal to 1. In this case, I went feet per second, so lambda is 1 foot. So basically, if you have a musical tone of 1000 hertz traveling through the airwaves, it would physically make a wavelength, if you were to look at it as it existed, of 1 foot. So if anyone's ever done acoustics, built a speaker cabinet or anything like that, and you wonder why speaker cabinets are certain sizes, for instance, or why the resonator body of a guitar is the shape and size that it is, the reason is that you're now dealing with mechanical waves that have to exist inside a hollow shell, right? That's why we make certain things the way we make them. That's why rooms are certain sizes. That's why you go to when you go to a concert hall, they're built in a certain way for acoustics because of the ability of that room to reflect frequencies and absorb other frequencies and bounce things around. Well, now what we're going to do is look at this other thing called a radio wave, or actually, we're just going to say in general, an electromagnetic wave.
Hey, Scott.
Yes.
So real quick, being in Oregon like you,
Mhm.
I have not had enough coffee. I cannot keep up with the notes. Did you say this was going to be recorded?
It is.
Okay, this stuff fascinates me, but I'm trying to keep up.
Yep. Yeah, I started the coffee an hour ago.
Thank you.
Okay, so we're now moving into something called an electromagnetic wave. So we're going to take that particle, and we're going to have it go like this, and now we're going to add that third dimension that looks like this. Okay, so that particle, as it's sitting there, actually makes two waves that are perpendicular to each other. Okay, if everyone holds up your right hand and takes your first three fingers, so you got your thumb, your index finger, and your middle finger. If you can set them up, and don't do it with your left hand because that'll be wrong. It has to be the right hand. If you can take those three fingers and make them so each is perpendicular to the other two. This is known as the basis of the right hand rule in calculus. In three-dimensional calculus, this is known as a vector cross product. You have this cross this equals this. It generates a vector that's perpendicular to both of them. So the way that this works is that this is known as the E vector, which is the electric field. This is known as the H vector, which is the magnetic field. And this right here in this part of math is the S vector, which is the direction of flow of the energy, also known as the Poynting vector. So if I were to draw this, I would see this. Here's the electric field. Simultaneously, I would have a magnetic field. And my direction of flow of energy would be in that direction. This is what electromagnetic waves do. So there are two parts to an electromagnetic wave. There's an electric field, and then there's a magnetic field. That's why they're called electromagnetic waves. Okay, so now let's take a look at things that make this wave interesting. What can we actually say that, again, there are certain features of waves. What are some features of waves that we just talked about? Well, amplitude, which is what? What's amplitude?
It's the height of the wave.
That's right, the bigness of the wave, how high it is. We can also change the wavelength. And wavelength is very tightly tied to
Frequency.
frequency and period, which is the time that it takes to make one wave. Frequency is the number of times per second. The other thing we can do, in addition to amplitude and wavelength, we can also vary the phase. We can delay it from going around. We can advance it going around. We can move it 300. Okay, here's a question. What happens if we shift it 360 degrees?
There will be
300
no visible change.
Yeah, you don't know the difference. In other words, a 360-degree phase shift is indistinguishable from where you start. You can't tell the difference. Okay, so we have our amplitude, our wavelength, frequency, and period, and phase. So for this section, we're not going to bother with amplitude, and we're not going to bother with phase. So we're really looking at wavelength and frequency and period. These are all very tightly tied together because, as we said, our frequency is equal to 1 divided by the period. They're inversely proportional because they're related to time. So something that has a frequency of 1,000 hertz has a period of 0.001 seconds. These are it's very tightly tied together. So we're just going to erase amplitude and we're going to erase phase. All right, here we go. And we're going to erase those two. Okay, so now we have something that relates frequency and wavelength. We have our velocity of our wave is equal to frequency times wavelength. And because in the meters, kilograms, seconds system, we're going to use the metric system, we're going to use meters because the rest of the world runs on meters. So a meter is about 3.3 feet because we have to be bisystemic in this country. If you're in the United States, you have to know meters and inches and feet. So we're actually, we actually have an advantage over the rest of the world in that because we follow the old standard, we also have to know the new standard. So we have to be able to convert. Trust me, if you go over to Europe and you say, oh, this cable's about 26 feet long, they look at you funny. I've worked in Europe. Like, I know that's about 8 meters, but they have no frame of reference. So it's actually good to know both systems. Okay, so now we have this thing called V, which relates our frequency and our wavelength. Well, an electromagnetic wave is a very special kind of wave because it travels, unlike a sound wave, it'll travel through empty space. It travels through empty space at what speed, everyone?
Speed of light.
Speed of light, which is how fast? How fast is the speed of light?
I just looked it up. It's 3 times 10 to the 8th, or almost. It's like 2.99.
Yep,
8
3 times
10 to the 8th.
10 to the 8th meters per second, or 300,000,000 meters per second. So really, really fast. Now, interestingly, the speed of light in free space, as it's called, is the speed of light. However, if it travels through something else like water, or let's say like hydrogen gas or any other material, it changes its speed. The light actually changes the speed that it travels. That actually is really important as well. We're going to get to that. But that's the reason why if you take your, let's say you take a spoon and you stick it in a glass of water and it looks like the spoon is bent, that's why the spoon looks bent to you. Because the light is actually traveling at a different speed through the water than it is through the air. It gives us something that's called an index of refraction of a material. And it's actually very, very important in electromagnetics. Now, I just gave you a little bit of a hint, which was we now have this electromagnetic wave and the speed of light. Well, what does that mean that light is?
A wave.
It's an electromagnetic wave. Okay. So, but I thought this was a radio class, right? I want somebody to say, I thought this was a radio class. You're probably all thinking that. I thought this was a radio class, not a class about light. Well, it's very important to note that what do we know about light waves? Do they travel through empty space?
Yes.
And why is that important? Why is that really, really important to us on Earth?
So the characteristics of where a wave is.
No, why is it really important to us on Earth?
The sun.
The sun, that's right. If it didn't travel through empty space, we would not get any sunlight. So, okay, so what I've put on the screen here is the electromagnetic spectrum. And what do you see on this electromagnetic spectrum all the way at the right-hand side?
Microwaves?
All the way at the right-hand side.
Oh,
X-rays.
X-rays. And then you have UV, which is
Ultraviolet.
ultraviolet. And then what do you see?
Visual spectrum.
The visual spectrum, all of our colors. And then infrared, moving left. And then microwaves. And what's all that stuff to the left of microwaves?
Radio waves.
That's all radio waves. So what does that mean that radio waves and visible light and X-rays all have in common? What do they all have in common?
Well, they're all electromagnetic waves. But
They're all the same thing. They're
Yeah,
all exactly the same
different frequencies.
with
That's-
different
yeah.
frequencies and wavelengths. So
Yeah.
why is it that yellow light is yellow light and a light that's red is red?
Because what's absorbed and what's reflected, right?
Right. And why do we call red red?
Because certain frequencies are absorbed instead of reflected.
Right. But why do we call red red? I mean, why to us, if I were to draw something like this right here, why is that red?
Because our eyes are capable of picking up and differentiating the frequency between red versus yellow.
Right. So this right here has a wavelength of about 660 nanometers. Very, 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 very short. Now, I'm going to draw a different color. What color is that? Unless you're colorblind.
Yellow.
That's yellow. That's about 600 nanometers. I'm going to draw another color. What color is that?
Green.
Green. That's about 550 nanometers. And now I'm going to draw another color.
Blue.
And that's about 500 nanometers. So why can we tell them apart? The reason being that our eyes are very good at looking at this range and telling them apart by giving us a different representation of color. Now, I could also make it so that if I had an ultraviolet pen, you're just going to have to imagine that I just drew something with an ultraviolet pen. Why can't you see it?
Because our eyes don't pick up those frequencies.
That's right. Our eyes are no good at picking up those frequencies. So now what we're going to look at is this map again. Okay. So why is it that we have to build a thing called a radio? Why does anybody need an infrared camera in order to do anything with infrared?
To be able to see what our eyes can't.
To be able to see what our eyes can't. Okay. So really what this class is about is the equipment that's necessary, the things that are necessary to communicate using wavelengths and frequencies that our eyes are not capable of doing. However, we can build a device like this, which can operate on 144 megahertz, which is a wavelength and a frequency that our eyes can't see, we can't hear, but we can basically build a detector for, and we can also generate frequencies of that particular frequency and wavelength that we want to, and use it to communicate with each other. And that is the fundamental reason why we're talking about what we're talking, and all the cool things that we can then do with all of those different frequencies and wavelengths that we've now created. Okay, so now we have discussed what is the electromagnetic spectrum, and it goes all the way from radio all the way up to frequencies that are so high that we have no recollection. We basically, they're hard X-rays, they're cosmic rays, they're wavelengths that are so short that there is actually a practical limit. It's nothing that we will probably ever see in our lifetimes. What happens if your frequency goes all the way down to 0? That has a name, actually. A wave that always stays the same, always stays at the same thing. In voltage, it's called. It always stays at like 12 volts and never changes. What's that known as? That'd be called DC. Direct current. That's a voltage that never changes. That's something like a car battery. And it's a good thing because it doesn't change. It doesn't go up and down and up and down. It just stays at a nice constant voltage. We use those all the time. That's a battery. That's what's inside your phone. That's what's inside your computer. Electronics don't like AC. They don't like voltages that change frequently. So anything that uses alternating current or an alternating voltage will have a sine, well, I should say everything, but most things that we deal with in the world have something called this sinusoidal pattern. And they go up and they go down. And the reason that it's so easy to deal with that is because things that travel in circular patterns are very good at making sinusoidal patterns. They're very good at making things that look like what we think of as a wave. Now, can you have a wave that looks like this? Does it have a wavelength? Sure does. This is the wavelength. Does it have a frequency? Yep. Okay. Well, this wave, that has a special name. Any idea what this is called? This is called a triangle wave.
Sawtooth? Okay.
Yeah, or a triangle wave or a sawtooth. All right. I can also draw it with this wave. Any idea what that's called?
Square.
That's called a square wave. So where do we use square waves?
Electronics.
Electronics, because we have, let's say, +5 volts and -5 volts. Well, we don't honestly really want to see this in electronics, because if we're doing digital electronics in particular, and we say that if we have +5 and -5, and +5 is yes, and -5 is no, or we say that this is equal to 1 logic, and this is equal to 0 logic, well, if we have this sine wave thing, what's all this gray area in here? What is all that gray area? That would be a big question.
Noise?
That would be noise. That would be a question mark. We would basically be yes from here to here. We'd have a value of 1, and we'd have 0 or no from here to here. And in the middle, we'd have all this question mark area. And if you're dealing with a computer, you really don't want that question mark, right? You want your computer to say either a 1 or a 0. You don't like those things that are in between. So that's why we use things that are called square waves for computer logic. Now, what happens if we were to transmit something like this? That would be a big X. Because, as it turns out, a square wave is actually made of, if we were to look at the frequencies, so now we're looking at a graph of frequencies. So let's say that we have a square wave at this frequency of, let's say, 100 hertz. It looks like this in time. Well, what we would find is we would actually have a component at 300 hertz and another one at 500, and they would be getting smaller, but they would all still be there. That's actually something called a Fourier analysis, named after a mathematician named Fourier. And what you'll find is that a square wave is really, really dirty for creating a pure wave. It has lots of these things called harmonics. A harmonic is an integer multiple of another frequency. So this would be 1 times, this would be 3 times, this would be 5 times the frequency, 7 times the frequency. And you would find that in order to make a square wave, this actually goes all the way out to infinity. Fourier showed that you actually have to use an infinite number of sine waves of different frequencies to make a square wave. So if we're using it to transmit information like radio, this is a very, very bad idea because it's a mess. We like sine waves in radio. Electronics, we like ones and zeros. We like square waves. For radio's purposes, we really don't like square waves. Okay, let's see. So, do we have any, whoops, I lost my camera there for a second. All right, do we have any questions so far? And remember, this is fundamental stuff and it's really important to understand. So if you don't understand something, again, there's probably somebody else who doesn't understand.
So if the handhelds that we're using
Yep.
probably require a lot of square waves, but yet we're trying to capture and change, frequency waves.
That is true. Yep.
So I'm assuming that that's what the radio is for.
Well, really what we have is it depends. I mean, if you were to look at a sine wave, right, we're looking at, let's say we have the radio tuned to 146.52 megahertz. This is the national simplex calling frequency on the 2 meter band, which actually, let's just briefly cover that. If we have a frequency, or sorry, a wavelength of 300 million, velocity meters per second, that's also known as the speed of light, and c is equal to f times lambda. What we can do is we can draw this little circle and say 300 million is equal to f in hertz, f in hertz times lambda in meters. We say that the 300 million is equal to the frequency times the wavelength. So whichever one we don't know, we can cross out. So let's say we want to know what frequency band that's in. So we have our frequency of 146,520,000 hertz, right? Which we represent as megahertz because we don't really want to carry all those zeros. We don't know our wavelength. So now we have this division bar, and we have wavelength is equal to 300 million divided by 146,520, sorry, 146,520,000. Well, we want to represent everything simply. So what we typically do is we get rid of all the zeros like that. And we replace this hertz with megahertz. And we get rid of all the zeros up here. We make it just 300. So that's what our formula looks like. 300 is equal to the frequency in megahertz times the wavelength in meters. So we can look at this and say, okay, what's 300 divided by 146.52? That's approximately equal to 2. This is known as in the middle of the 2-meter band. That's why we call it that, because the wavelength that it carves out is physically how big? Approximately 2 meters long, which is about 6.5 feet. So now what we've shown is that this frequency, as it's traveling through space, has a wavelength of about 2 meters in length. That's its physical wavelength. This is actually really profound because this is actually going to determine how far you need to move. It's going to determine how long an antenna has to be in order to function properly. It's basically a fundamental building block that we're going to be getting into. Okay, so now let's go back to the original question, which is, okay, we have this frequency of 146.52 megahertz. And in order to make this, we need something that will generate a frequency of 146,520,000 hertz. So that's our frequency, 146,520,000 hertz. We need some electronics that will actually make that frequency. Well, we can do this a couple of different ways. Number one, we can have a transistor, for instance, and this drives something, and part of the feedback of the transistor gets sent back into the input, and we go into this, we basically build something called an oscillator, which is a essentially a self-running amplifier circuit. And by selecting certain components, like a capacitor and an inductor, for instance, we can actually have it be tuned so that it runs at a certain frequency. We can also, and that'll actually generate a sine wave. The other thing we can do is we can have our electronics, which are a microprocessor running inside this box, and we can program it to generate something that looks like a sine wave by approximating values and spitting out a new thing every very, very rapidly, so that its total frequency is that. So we'd have to figure out what to do there. The other thing we can do is we can actually have our electronics generate a square wave at a certain frequency. But now we have to take the square wave and turn it into something that looks like that. And we use something called filtering for that, because we know that this has the original frequency plus 3 times the frequency plus 5 times the frequency, and so on and so forth. And we only want this one, so we can generate a square wave and then filter out all the others. Can make them basically disappear. And then we end up with a prettier copy at the right frequency. So there are a lot of different ways to do this. And to be totally honest, they are all used. Now, as far as the actual, you know, like if I turn this thing on, it has a display, right? This has a rather powerful microprocessor in it. It handles all the push buttons. It handles the display. It handles when I, for instance, hit a button, this doesn't automatically do anything. What happens is that that button is then interpreted by the microprocessor, which says, okay, that means turn on the transmitter. In which case it sends a signal to the transmitter to start amplifying a signal that it generated internally. So there's a lot going on in there. Heaven forbid you ever take a look at what's actually happening inside your cell phone or inside the computer that you're using to connect right now. More technology than any one person can possibly understand in their lifetime. Okay, any other questions?
Was there any specific reason that you brought up the triangle or shark tooth wave?
Just to show that they're just, I mean, they have wavelengths, they have frequencies, but that a wave does not have to be a sine wave. There are lots of different waves out there. And in fact, when you go to test, let's say you go to test a circuit, if you get let's say something called a function generator will actually be able to generate sine waves, square waves, sawtooth waves, or triangle waves, for instance. The reason that you would do that is, let's say that you want to take a look at a filter that you've built. You know that every one of those different waves, somewhere in there is the right frequency that you're aiming for. The question is, you know, how good is my filter that I built at filtering out the extra frequencies, the harmonics that I didn't want? You could use it for testing that. You could use it for being able to say, okay, well, if I have a triangle wave that's being generated by something, how would I go about cleaning it up? Is it possible to use it for something? You know, for some functions, it might be absolutely fine. Certainly not for audio. It would sound terrible. And just to indicate that, you know, there really are waves. There really are, you know, waves that we're looking at that are not necessarily sine waves. We really do focus on sine waves because they're the most useful and interesting to us. But if you happen to do digital logic design, you know, let's say you're building computers, sine waves are bad. Sine waves are really bad. All right, any other questions? I think we're going to take a 5-minute break. Everybody get that coffee going.
Okay, thank you.
Yep. Mhm. 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 Everybody ready to go again?
Yep.
Okay, here we go. Okay, so one very important thing that I would like to point out is that there are these things called decades. A decade is a function of a factor of 10. We call out frequencies and wavelengths on the big chart by decade. And the reason that's important to note is that let's take a look at 3 megahertz. All right. So what frequency is to the left of 3 megahertz? It's 300 kilohertz. What frequency is to the right of 3 megahertz? That would be 30. What frequency is to the right of that? That would be 300. To the right of that would be 3 gigahertz, which is 3000. This is actually really important to note because each area that we have, each line is 10 times higher than the previous one as we move to the right. Notice that each wavelength is 10 times shorter, 100, 10, 1, 100 millimeters, and so on. So what's important to note here is that this area known as high frequency, or HF, this is where a lot of the fun is. This is a lot of the long distance stuff. But when we talk about frequencies and how we use them, as soon as we take a particular wave at a certain frequency and use it to convey information, it makes it take up space on the spectrum. The more information we transmit with it, the more space it takes. Well, this may not seem like a big deal, except that it really is. And the reason that it really is because let's take a look at this thing known as HF. You're going to have to actually remember these 3 things, HF, VHF, and UHF. You're going to have to remember that HF is from 3 to 30, VHF is 30 to 300, and UHF is 300 to 3000 or 3 gigahertz. You'll actually have to commit those to memory. They're going to serve you well anyway, so it's good to commit them to memory. But the thing that's most important about this is that HF is high frequency, VHF is very high frequency, and UHF is ultra high frequency. So that's why they get higher and higher. Now, in between 3 and 30 megahertz, how much space do we have? How many megahertz of space do we have?
27.
27. How about in VHF between 30 and 300?
It's 270, a lot more.
Yep. How about between 300 and 3000?
2070.
2,700, right? So each one is 10 times bigger than the previous one. There's that much more room. Okay, so now what we're going to do is take a look at something that we would call spectrum allocation. Okay, so we're going to take these 3 segments. And we're going to say that this is HF, and that goes from 30 or 3 to 30. That's HF. Then this one, which is VHF, that goes from 30 to 300. And then UHF, which goes from 300 to 3000. And now we're going to take a signal. We're going to give it a base frequency and say that it goes like this. Here's our center frequency, and we have a lower sideband and an upper sideband. This is like a frequency representation of a signal. Essentially, if we take a carrier frequency it has no bandwidth. As soon as we modulate it by putting information onto it and using it for our purposes, it takes up space. This is known as a bandwidth. So let us say that this random signal that I just created has a bandwidth of, let's say, 20 kilohertz or 20,000 hertz. So this is in megahertz. This is in megahertz. And this is where it's important to understand the difference between kilo and mega. What does kilo mean? 1,000. Mega means
Million.
a million. All right. A giga is a billion. So this is 20 kilohertz. So this is 20,000 hertz wide. Or if we were to make this in megahertz, it would be 0.02 megahertz. Okay. So if this right here, we have 27 megahertz of space. Could you put that signal fairly comfortably on that band? Yeah, I think you could. Right? It's a little bit wide, but you could certainly do it. And if you were to put that here on this frequency band, it would look something like that. It's a little wide, but it'd be fine. If you were to take that and put it up here, it'd be really minuscule, and take it up here and it would be really minuscule as well. But now we're going to take that signal and we're going to say that it's actually really high fidelity audio. And we're going to make this 200 kilohertz wide, is 0.2 megahertz. So that very same signal, right? That new signal, if we draw it on the bands over here, it might actually be like that. And it's still pretty small here and still pretty small over here. But now what do you notice is happening to that blue signal on that HF band? Starting to take up more space, isn't it? To the point where it's starting to become a bit of a burden. Okay, so now we're going to add a different one. We're going to make it the green signal. And we're going to say this is a television signal, a standard TV signal. This is 6 megahertz wide. That is an analog TV signal. 6 megahertz. It would go from here up to about here. What happens if we do that?
Kills your bandwidth.
Well, your bandwidth is your bandwidth. What it does is it kills anyone else's ability to use the band. I mean, you can only use it one time. Up here, maybe it's this wide. Up here, maybe it's like this wide. So if we were to take that signal, would we ever want to put it on the high frequency band? I don't think so. And that's why no television signals, no high-speed TV signals. This is known as NTSC, which is analog TV. That's why we never did television on the high-frequency bands. That's why it was always either VHF or UHF. And that's why when you go back to your old television, for those of you who are old enough to remember, why there was something called a VHF and a UHF, and VHF was channel 2 to 13 and UHF was channel 14 to 83. That's why they were split that way, because it was about ability to use the spectrum wisely. So as it turns out, about a third of the VHF spectrum was actually used for television, and almost half of the UHF, now about a third of the UHF spectrum was used for TV. So that actually has gotten considerably better through the use of cable and through the use of digital television. That's a lot more efficient way to transmit signals. But we still don't do television on HF. So this is it's basically about resource reuse and efficient use of the resource, which is our bandwidth, because you can only really use it one time. Okay, well, now that we've kind of covered that, so all right, we're going to take about 20 seconds. Everyone's going to you got to time yourself. everyone's going to have about 20 seconds to introduce themselves to your cohorts in the class. And as soon as you're done, you pick somebody else. So I will go first. And my name is Scott. My call sign is N7JI. This is, I think, the 28th or 29th class that I've taught. I very much enjoy teaching this stuff. I have a bachelor's and master's in electrical engineering from the University of Maryland, where I did it in communications and electrophysics. And I don't do anything at work with regard to communications or electrophysics. This is a hobby for me now. My degree is my hobby, and instead I build factory automation equipment. So I get into power design and robots and things that move around on a factory floor. So cool stuff. All right, Shannon. And everyone, don't forget to unmute yourself.
My name is Shannon Whitson. I am in Knoxville, Tennessee, and I'm a retired veterinarian. That's about it.
How did you end up interested in ham radio?
My husband has been a ham for 30 plus years, and I've just now had the time. He's been after me for years to do it, and just now getting
Cool.
around to it.
Right.
Mark.
Well, I am retired and decided to jump into ham. I got into a local, I guess you'd call them a militia group. And so I decided that I needed to know how to operate ham, and that's where I went. And Danny, I guess, would be next.
Do we have Danny? All right, let's go with Richard. You're muted, Richard. Everybody remember to unmute yourself.
Yeah, yep. Rick, I've worked for many, many years in computers and IT and software development and things like that. So that's primarily what I've done. But I've also worked a lot at hardware development environments, like Intel and things like that. So a lot of what you're covering makes sense and overlaps with a lot of my background. And I basically got pulled into this because my daughter, who is also on this course, she's learning it for her some of the work she's doing in college, and so I thought I would do with her. It's very interesting stuff. So I will actually pass it over to her, Anna.
Hello, my name's Anna. I first started getting interested into the radio licensing with my work with Portland State Aerospace Society. So I'm very interested to learn about all this.
So have you built satellites with them?
I've done some very small circuit design stuff and circuit assembly stuff.
And you're in electrical engineering?
Yeah, learning to do that.
What year?
I'm still in my beginning second year. I'm taking classes all out of sorts.
This will actually help a lot, I think.
Oh, I'm glad.
Yeah.
Awesome.
It actually drove me right through college. Ham radio was my lab when there wasn't a lab.
Let's see. Jacob?
I'm Jacob. I am a high school student. I live in Mississippi, and I got into ham radio because of my dad. He's been doing it for a while, and I want to get my license too. Calvin.
I'm Calvin. I'm just about 29. I wanted to get into ham just because I like messing around with different hobbies. I like music and riding motorcycles and stuff, but I'm always looking for something new.
Okay, who gets it next?
Let's go with Kathleen.
Hey, my name is Kathleen. I am also actually part of the Portland State Aerospace Society. I helped launch ORSAT 0. My name is on that satellite in space as we speak. It's awesome. I got my degree in math. I work in the aerospace industry. And I'm taking this course with my dad because my dad and I have both had massive interest in it. So I'm going to call on him next. My dad, Joe.
It says Bonnie, that's my wife's name, but my name is Joe. I am in from Great Falls, Montana. My daughter Kathleen that is also from. So I'm actually had an interest in ham radio for many years, and we finally decided, my daughter and I, to go ahead and do this. But medical background, I'm a primary care physician assistant here in Montana. So kind of excited to get into a hobby, not dealing with medicine. So very glad to be part of this class.
I edited your name there.
Oh, thank you. And let's see. How about Cynthia Andrews?
Okay. Well, my name is Cynthia Andrews. I live in Rochester Hills, Michigan. I'm a retired attorney. My boyfriend of about 10 years has been a ham since he was 10 years old. So that's like for 60 years. And I guess I have more of an interest because of him. And I just think it would be fun to be able to communicate with him through ham radio in case he's not available by cell phone, I guess. But so, and I thought it would be a cool thing to start doing and actually go beyond more than one level. So
It'd be quite addictive. Yeah.
Okay.
What's his, you know, his call sign?
It begins with a K. I know that because he got his license in Utah.
Okay. You know, what's his name?
Don Ledwith.
Ludwig?
Ledwith from Salt Lake City.
Okay. How do you spell his last name?
Ledwith.
Okay. All right. Go ahead and pick somebody there.
Yvette.
Hello, I'm from Colorado Springs, and I'm just a nurse. Taking this class because my big brother, Klaus, ACMG, let's see, I think I got this right, AC7MG, has been bugging me for many, many years, and finally sent us some radios and said that the first ones who got their license gets them. So yeah, that's that. My two daughters, Natalie and Victoria, are also in here. So I'm going to call on Victoria next.
Okay, so I'm Victoria. I'm also in Colorado Springs. And I'm taking this class because my uncle wanted me to. So yeah.
High,
go next.
high school junior?
High school senior.
Senior. Okay. Are you taking physics or have taken
This
physics?
next year I'm taking physics. I'm currently in calculus. So going over the unit circle and wave signs is fun.
Okay, sis.
Hi, my name is Natalie, and I'm also a high schooler. I'm from Colorado, and I took this course because my uncle, he sent us radios and he really wanted us to do it. And so I thought it would be neat and fun.
So I should point out that, go ahead and call the next person while I pull this up.
I guess we'll go with Buck.
I'm from West Virginia, retired attorney. I got my start in radio way back in the 90s when I was an RTO with Ranger Battalion, 3rd Ranger Battalion. And what was interesting back then is we created, or when I was in the field and specifically in Panama jungle warfare training, we created what was called a 292 field expedient antenna. And I didn't know anything about radio back then. And I was operating, and I thought 7 clicks, which was 7,000 meters, was a far distance because it was the record at the Jungle Warfare School. And it amazed me. Recently, I got into watching a lot of YouTube videos like ham radio crash course, and I followed Josh on there, and got interested in it, got a Baofeng in case of emergency, of course, and I can't push that little talk button because I don't have a license. So I'm trying to get my license so that I can push that talk button.
Okay, well, I would like to just take this keep an idea of who you want to call next, but this is for all the teenagers. Has anybody ever heard of this? Teenagers going to college?
Nope.
No? Okay, so the ARRL, I'm going to put in my plug for the ARRL. This is our National Organization for Amateur Radio. It's one of the it's the largest in the world of all the national organizations. Basically, every country's got an organization that represents its ham radio operators. You would think that the FCC represents us. The FCC does not. The FCC licenses us. Basically, when the government decides, remember that chart of all those frequencies that are available? When a commercial entity comes along and says, we'd like to pay $100 million to use a particular frequency, and amateur radio operators pay zero, basically somebody has to stand up for us in front of Congress and the FCC and say, hey, you know what? Just remember that, we don't pay anything, but we give back. We're the educational wing. We're the group that when there's an emergency, when FEMA can't even do it, they call on us. So just keep in mind that we're the ones who know how to get stuff done when it comes time to deciding whether or not you're going to take that $100 million check from the commercial company and kick the hams off of the frequency. So the ARRL is the organization that has a few lawyers who run around DC, in addition to doing education and things like that, who support us and make sure that we don't lose our frequency allocations. In addition to that, the ARRL also runs a scholarship program and distributes scholarships that range anywhere from about $500 a year up to $25,000 a year for college students for higher education. So they like to see activity. They like to see getting licensed. They like to see that you are, you're active in your local community. So what I would recommend is get your license and then do stuff. And then when it comes time to applying for scholarships, watch those dates and don't forget to apply. All right. Who gets picked next?
Joanne been called on?
No, I haven't. Can you hear me?
Yep.
Okay. My name's Joanne Yeager, and I'm in Pennsylvania, specifically Lancaster. I'm a retired teacher, 34 years in the school district of Lancaster. It's been a long time since I did this math, anything about wavelengths, but I've always been fascinated with ham radio. I didn't know much about it. And I'm at a point in life, I just feel like learning something new. So I don't know how far I'll go with this, but I'm going to give it a shot.
Well, you get involved with your local club and
Mm-hmm.
get some input. Now, I would also
Okay.
like to point out another thing that the ARRL does is this. Notice the Teachers Institute on Wireless Technology. If you teach STEM classes, for instance,
Mm-hmm.
they actually have all expenses paid week-long trips to go and become a student yourself and learn how to better teach radio as a STEM teaching tool.
That's great.
Yeah, it is. It's a
great.
good organization.
Yeah.
I know several teachers who have done that, and they
Mhm.
speak very highly of it. A lot of hands-on stuff. And for the students, this is your chance to be smarter than your teacher. Actually, it's funny. My daughter, who has actually last year she got a $25,000 scholarship, and this year she got a $10,000 scholarship.
Wow.
She has her extra class license. She's the president of the brand new University of Oregon Radio Club, reconstituted after 95 years of dormancy. And she actually gave the technician license exam, because she's also a volunteer examiner, to her high school physics teacher. She actually administered his exam, in addition to her vice principal.
Did they pass?
They did. She didn't. She didn't get to tell them that they failed. Oh, wah, wah. But she actually got to sign off on their. They actually got to sign off on their exams and sign off on their forms and everything. So that was kind of cool.
Great.
All right, who do you want to pick?
Jacob, did he go yet? He did. Okay. Joel.
Hi, I'm Joel Bryant from Jacksonville, Florida. I'm a wedding DJ, also a network administrator, and I did a little small stint on the FM radio part-time. Best $6.90 I ever made.
So which one pays better?
Oh, the network administrator. Well, actually, I lie. The wedding DJ pays the best, so that's what I do more of.
Okay.
I used to do more network administration. I still have a law firm that I help on the side and consult with, different people when people overthink things.
All right, who next?
Let's see. Has Amanda gone?
No, I haven't.
Okay.
You're up.
Hi, I'm Amanda. I'm from Tuscaloosa, Alabama. I'm in healthcare. The reason I want to get my ham radio license is because my whole family are ham radio operators. I grew up with my family being disaster relief, tornado spotters, helping a lot with the Red Cross when tornadoes hit. They've been doing it since the 80s. Me and my brother are the only ones who don't have our ham radio license, and I've always found it fascinating. So I'm trying to get it and surprise my dad, who used to teach classes, so I can't really go to him for advice because I'm trying to surprise him. So I'm just trying to get it. I find it very fascinating. And my mom knows about it, so she's very supportive. But other than that,
All right.
that's it.
All right, who's next? How about Scott Wilcox?
Okay, let's go with that.
No? Okay. How about Glenn? Oh, wait, there's Scott. Go ahead, Scott.
No, I'm just listening.
Okay. How about Glenn?
Sure. So I'm a mid-40s. My profession is a technical project manager, installing and upgrading predominantly hospital systems. But my interest starts way back in junior high school. I took an electronics class in junior high, loved it. In high school, I was always interested in math and physics. Well, physics and science probably be better to say. In college, I wanted to be an electrical engineer, and one of my little projects I did was just an experiment for fun, is I wanted to see which was more effective, transmitting a signal over the airwaves with a straight line antenna versus a coil. And at one point I had a line of wire going down the entire hall of the dorm room to see how well it picked up on my radio. I don't know if that was legal or not, but I did it. And then the guy next to me in the next room over, he had his license, and it was pretty cool. One time, I don't understand it or what he did, but we were in a car, in a group of guys, and we needed to call somebody about something. and he had his radio, and he did some fancy stuff, used the
Phone
word
patch.
auto patch.
Phone
Yeah,
patch.
auto
Yep.
patch, and made a phone call over the ham radio. It was really cool. But then, so I've always wanted to. I've always been curious about it. I wanted to know more about it. Wanted to get my license. But lately, with drones, commercial drones and whatnot, I'm not sure if this is true or not. But I read like some of the more advanced stuff like might require a ham radio license. I'm not sure about that, but that's my interest.
You have more frequency availability. A lot of drone pilots get their ham licenses for that reason. The frequencies aren't as crowded.
Cool. So that's me.
All right, who goes next?
Oh, how about Miro? Has Miro gone?
I don't think so.
Hello.
Walker.
Yes. I'm Walker. Yes, hello. I'm Walker. I'm a high school junior. I got my interest in ham and radio from a couple areas. I do have a lot of experience with search and rescue stuff. But I've also helped teach a radio merit badge, like Boy Scout merit badge class. So that was the main inspiration behind taking this class, because the instructor for that was just like, if you have like any interest in this, you should get your technician's license, because
it's at a minimum. Yeah.
It's just it's not too hard, and it really can just help you get into radio. And that was a long time ago, and I guess I remembered it. So taking this class.
Cool. And it gives you more cred when you teach when you teach the merit badge.
Yeah, definitely.
And then when you go to college, you can apply for all those scholarships. All right, who hasn't gone yet?
I can go, Jeff.
All right.
So Jeff Letcher out of Gresham, Oregon. I've been in public safety for about 30 years now. And this is just kind of the next step. I've always, grabbed radios and gone to work. And now I just want to understand them more. And I'm going to have some oversight in emergency management. So if I'm going to talk the talk, I want to walk the walk.
Cool. All right. Let's see. And who else? I saw a hand go up. Who else hadn't gone yet? Was that Peter?
That was me. Yeah, Peter. I am Peter. I'm out of Oregon, and I moved from California in 2014, and moved up here to Oregon just because the greenery and trying to go to a little bit more slow paced life, just to kind of relax and get some rest from the hustle and bustle. So I take care of farm animals, and just trying to find an additional hobby. I am a mechanical engineer by training, but most of my work right now is just management. So that's kind of what I do.
Okay, I see. Looks like Kara and Ben. How about Kara and Brock? I see a hand up. And okay.
Yes. So I'm in healthcare, and my brother has been in ham radio for an extended amount of time, and he has been on me incessantly about getting this taken care of. So
it's called nagging.
Yes. And my son Brock, who is not with me currently, he's in Boy Scouts, and he's actually volunteering today with the police. So he is doing it because he's got some interest in the search and rescue aspect, and also for merit badge opportunity as well.
Okay. All right. I see Ben next.
Hi, I'm Benjamin Guerrero, and I'm from South Texas. I was introduced here by my dad, and I'm in middle school. I went to 8th grade.
Very cool. All right. How about Vic?
Hi, my name is Vic Dietz. I live in Chicago, a retired attorney. Have been aware of ham all of my life, I remember hearing the stories about soldiers in Vietnam calling home to the United States by virtue of something about a ham radio patch.
Yep.
And I thought that was a wonderful idea. Thought that'd be fun to be part of. As I've been listening to stories this morning, I realized that I watched my dad flying an airplane as a child, and he was always talking on a radio. And so it was just a connection to the outside world. Maybe that's it. So I fantasized about being a ham all my life, not really knowing what it meant. Totally intimidated by the Morse code requirement. Tried to learn that as a Boy Scout. Didn't work. Mercifully, that has been lifted. And so a few years ago, I just decided that I need to do a few things before I get any older. So I, among other things, started a career. I'm a retired attorney, in case I didn't say that. I started a career as an over-the-road truck driver because that was something I always wanted to do. And I went and got a ham license because that was something I always wanted to do. So now it's time to get serious and take it to the next level. I don't even know how I learned about this course, but you encouraged me to take the course as a refresher, which I desperately need, and as a good prep for the general exam.
Yep.
And you've already blown me away this morning with all the math.
Okay.
And,
that's not a bad thing.
I don't understand it at all, but I'm enjoying learning something new. And I see you're recording this, so I'm guessing you'll spend several hours rewatching all that. So thank you very much for doing this. 7-3 K9 Delta Tango Zulu.
ETZ. Okay. If we missed anybody, Nathan.
I'm Nathan. And I live in California. And I'm in middle school and I'm a scout.
Okay, cool. All right. Well, I would like to just bring something up, and in case people think, okay, well, what can you really do with ham radio? All right. So can everybody see the picture on the screen? So, okay, so we actually just did with our local radio club. We did a special event for the World Athletics Championships. People might be aware that we just had the World Track and Field Championships here in Eugene. And so what we did is we basically had an Oregon-based party where anybody in Oregon, if they signed up for a particular time slot, could operate using a special call sign, which was the University of Oregon Club call, and make contacts and send them all to us. And we would basically offer to make commemorative cards available to people and send them out. We would also log all the contacts. And in a period of 10 days, this is most of the contacts that we made. So in case you think, okay, well, what can you really do with ham radio? Is anybody actually using the high frequency bands for making long distance contacts anymore? This is from the West Coast. Notice that big blob in Europe, lots of Japanese stations, South America. Here's all over the United States and the Caribbean, all over Europe, all over Asia. It was a lot of fun. So there's all kinds of things that you can do with radio. And, if you do it, somebody will show up to make a contact with you. So.
Observation?
Yes.
Looks like most of those dots were not red. Looks like digital's taken over the hobby here.
Well, okay, so here's one of those things. Digital is okay. So in particular, a lot of digital contacts are available to people because of improved signal to noise ratio that would not be able to make a contact otherwise. So if we were to look at, and this is something that we're going to get into. Okay, so let's say that you have a bucket. And so you have several buckets and you only have a certain amount of water. And here's a bucket. And here's another bucket. And here's another bucket. Right? They all can hold, that last one isn't very good. Let's do another one. They can all actually hold the same amount of water, right? Which one is going to give you the highest level? Let's say that you have this bucket too. Which one is going to give you the highest level compared to the ground when you fill up that
Tall,
bucket?
skinny one.
The tall, skinny one. Yeah. Okay. So what happens is that if you have a certain amount of water to fill that bucket, and now you say, okay, well, I am now going to say that here's a line which represents what I can see, right? Everything below the line you can't see. Which is the one that pops up above?
The one and only.
The one and only. Okay, so these are two different modes. These are CW, which is known as Morse code, and very narrow band digital. This big fat one is single sideband, which is voice. So the thing is, if you have a lot of power, you basically can take this bucket and make it a lot higher. But you need a lot more water, if it's water, you need a lot more power to fill that bucket. You can also get a really big antenna, which has the same exact function. But what ends up happening is that a lot of people don't have a lot of power. A lot of people don't have a really big antenna system. So if you lack those things, what you end up with is the modes that work really well for modest stations. And those are mostly right here. CW and digital contacts, because they are very narrow bandwidth signals. So they essentially give you a very high power spectral density, as it's called, which turns into, on the other end, signal to noise ratio. And signal to noise ratio is what allows something to be heard or not heard. So, I mean, I can transmit using single sideband, but it's below that red line. So unless conditions are really good, it doesn't work as well. So, or unless you have a monster station. And when I say a monster station, like I'm going to pull up a picture of my friend Frank's monster station. Okay. So this is my friend Frank's monster station in Maryland. He's W3LPL. And notice these small things up at the top of the picture. Those are his house and his neighbor's house. Those are like 5,000 square foot houses. Okay. So to give you an idea of those towers that are up there, those towers are each about 200 feet tall. Right. Here's a side view of that. Right. The house is really insignificant compared to the size of the towers. So that is known as, notice he calls it his antenna farm. And here's a view from the ground with the houses. So that is what we call a superstation. He has taken a lot of time and effort and built basically a monster superstation. Now, if we were to look at my house, for instance, I would consider myself a very modest station compared to that. I have my house that looks like this. And I have an antenna that goes from one tree to another tree like this, and another antenna that goes from one tree over here to another one over here. I just have two pieces of wire that are hanging in the trees. There is no way that this station will ever perform as well as that other station. However, if I were sitting at that other station back in Maryland, you know, Frank's superstation, I could basically contact anyone, anywhere, at any time on any band. Because, you know, I mean, he's got big amplifiers. He's got antennas that are 200 feet above the ground, and they have a lot of gain, which we'll get into. But I don't have the property for that. I don't have the money for that. So you do what you can. And what that turns into is you use the modes that give you the biggest bang for your buck, and the ones that make contacts. And the ones that make contacts when the conditions are not great or when you don't have a great station are the ones that are very efficient as far as bandwidth and power. And that's why so many people use Morse code and digital. Voice is actually very, very inefficient, but what you get is you get a lot of information. If it's good enough, I can talk a lot faster than I can send Morse code. I can talk a lot faster than I can send a digital signal like typing. Vic, does that answer the question?
Yes, it does. Thank you. I've got a bit of a dilemma here. One of my new friends has an antenna farm, not quite as dramatic as your friend, but still overwhelming for the suburbs. And he can't imagine being on the air for less than 500 watts because, quote, I want to be heard, close quote.
Yep.
On the other hand, the Elmer of our group is trying to help me understand that he can hit a repeater with 1.5 watts, and that's what he does.
Okay.
So the observation I'm making is that the folks that want to get out and cover the world need an antenna farm and 500 watts, and the people that want to chat with their neighbors can use a 1.5 watt unit, hit a local repeater, or even a simplex, and away we go. And one of these days, I'm going to know what all those words mean.
You want to hear what my opinion is on that?
Please, please.
Try everything. If you want to talk long, if you want to work long distance, okay. I mean, 2 meters is one thing. That's for talking to your local, local hams. I have this for talking to my local hams, right? We have lots of repeaters around here. We have a lot of mountains here, unlike Chicago. We have repeaters on mountaintops, which means that from anywhere on the ground, if you're a line of sight to something on a mountaintop, you can talk to anyone else who can see that mountaintop, which is great, right? But I'm not going to talk from here to Europe using that mountaintop. Now, I can, if the conditions are really good, late at night on the 20-meter band, I can make Morse code contacts into Europe at about 15 watts using a dipole. If I had a big beam on top of a tower, I could do it at 3 watts. I mean, I've made contacts into Europe on 3 watts and a dipole, just a wire antenna. So a lot of it is, okay, okay, this is actually going to come up. How much power are you supposed to run? Literally, how much power are you supposed to run when you're making a contact? This is actually in the rules. The minimum power needed to achieve the desired communications. Okay. That is how much power the FCC says you're supposed to run. The minimum power needed to achieve the desired communications. The question is, what is your desired communications? For some people, it is to be the strongest signal on the band. If you're calling CQ, and you want to be heard in Europe, then you're going to put up, a big tower, and you're going to run a kilowatt. I have never aspired to do that in my entire life, right? I've never wanted to have a big amplifier. I've never wanted to be the one who would have to put up and maintain a 75-foot tower. I don't want to be climbing that tower. I just don't. I don't want to be the one who has to go up there when the weather's bad and service or bring down that antenna and do work on it. I don't. I know people who do, but I'm not that person. So for me, what I'm happy with, I actually like the challenge of working minimal power and minimal antennas. I tend to be somewhat of a minimalist, right? So a dipole antenna fed with ladder line, and during contests, which are prescribed time periods and frequency bands that you operate on where there are a lot of people on, I will very frequently enter in the QRP, which is the 5-watt class, because to me, being able to do that, it brings in a little bit of frustration, but it also has its own separate, set of challenges and set of achievement. If I can work, I can go over to my friend's house who's got that big tower, and I can run 1,000 contacts in a period of 2 hours or 3 hours if I really want to. However, I can be out here in Oregon, which is kind of like a radio island, and operate at 5 watts and make contacts into Europe or into the East Coast, and if I do it 100 times in a period of 6 hours, I'm doing pretty well, right? I'm not going to win, but I'm pretty happy with it. And I can say, you know what? I actually managed to make 100 contacts at 5 watts and work 42 states in 6 hours. So it really comes down to both of your Elmers are right and both of your Elmers are wrong. It comes down to figuring out what you want to do, which is why this is such a cool hobby and service, because you can do exactly what you want. If you want to get into a certain, you know, if you want to run high power and, you know, you look at your frequency allocations, you can run 1500 watts. You can put up an antenna tower before you even have to tell the FAA that's 200 feet tall and put up as much gain as you want. Put up as big an antenna as you feel like, right? I choose to not do that. I know people who for them, there's nothing other than doing that, because why bother? So, Vic, does that make sense?
Yes, and that was a large issue as I was recently trying to buy a radio.
Yep.
And the question always is, what radio should I buy? And then the answer to the question is always a question.
That's
what
right.
do you want to do?
That's right.
And I don't know what I want to do. I'm just dabbling around. So I bought a small dual band at I hope a modest price. And now I'm learning how to play with that with 3 or 4 guys on a small repeater.
Mm-hmm.
And I still have fantasies of an ICOM 7300.
That's what I have. After 37 years, that's what I have.
I freely acknowledge I wouldn't know what to do with it if I had it. It'd be like giving a 16-year-old a Ferrari.
And you
Not
should.
a good choice.
Actually, that's a perfect choice.
So,
because you're not going to break it.
Okay.
Whereas you're going to wreck a Ferrari.
Okay.
You're not going to wreck a 7300.
So how much of an antenna do I need for that? Sounds
How much
like
room?
you're running it on a small dipole.
How much room do you have?
That's a great question.
Yeah, think about it. Think about that and come back with an answer.
All right. Thank you.
Okay. Okay, ready? We're going to get into propagation. And okay, propagation is, now that we've created radio waves and we all kind of know each other a little bit, which is great. Okay, this is a wave. Okay, we have that part and we have that part. And we have an electric part and we have a magnetic part. And the polarization of a wave is known as the direction of the electric field. So the electric field defines the polarization of a wave. So if we were to draw an electric field that was going up and down, that would be known as vertically polarized. If we had an electric field that was going horizontally like this, back and forth, that would be known as horizontal. If we had an electric field that was rotating in time, so it was sometimes going like this and sometimes going like this and rotating from one to the other, that would be called circular. So the electric field defines the direction of polarization. Okay, so why is this important? So what we're going to do is we're going to draw an antenna and we're going to make this antenna vertical. So the electric field that's generated by this antenna will be in the same direction as the wire. So this vertical antenna will have a vertical vertical polarization. Now we're going to draw another antenna, which is horizontal. That is going to have an electric field that is horizontal. Now, what's an important thing to remember is that every piece of wire that can make an electric field can also respond to an electric field. That's why antennas are great, because they can transmit as well as receive. So this vertical antenna, what type of energy, what type of polarization do you think a vertical antenna is going to respond to? Oh, somebody throw it out there.
Vertical.
Vertical. Yes, vertical. Okay,
Vertical.
so now what happens if this antenna, which is here, encounters a wave which is horizontally polarized? How will it react?
It's basically just noise on the wire.
Actually, it's nothing, because
it's a point that's crossing that wire. So
that's right. It will have essentially no impact. The same thing will happen if a vertically polarized wave crosses a horizontal wire. You will have essentially no effect, which basically means that the polarization of the antenna can be really important with regard to whether or not you hear anything or not. Because in addition to transmitting a signal with that polarization, it actually listens to it. This is exactly what happens when you have a pair of polarized sunglasses, because you have the hood of your car like this. Here's the hood of your car. The sunlight comes down off the hood of your car. And when it strikes the hood of the car, it's actually randomly polarized, but then you end up with horizontal polarization being reflected like this. If you have lenses that are then vertically polarized, guess how much of that horizontal polarization gets through?
None.
None. And you don't get the glare. That's why polarization is so useful. Because in this case, we use it to eliminate our ability to see something. Sometimes we use it for our ability to actually see something. Okay, so now let us get into radio waves and how they move. Okay, so what the two components of a radio waves are electromagnetic. So in case anyone's curious, we're on page 39 in the big PDF file. It says radio wave characteristics, and it looks just like this. It says radio wave characteristics. Two components of a radio wave are electric and magnetic fields. They are perpendicular to each other, so they're at right angles. Radio waves travel at the speed of light, which is about 300 million meters per second. The formula for converting radio waves: speed is equal to frequency times wavelength. You can change that around, but if you can write C is equal to F lambda, or if you can make this circle, and by the way, when you get to your exam, you will have the opportunity to have a piece of scratch paper, which you can then draw this on if you feel like it. You can draw that and use that to make sure that you remember which is which. So 300 is equal to this times that. And then if you don't know one, you cover it up, and then you have a division bar, and you can say that lambda is equal to 300 divided by F, for instance. So you can actually use that as a nice little tool. I like that little circular tool. Okay, let's see. High frequency. One of these is probably going to be on your test. High frequency is 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3000 megahertz. And RF is radio frequency. Okay, so now that we know that we have these different frequency ranges, we also have how these frequencies, once we generate them, interact with the world. Because just generating a signal that travels through space is kind of boring unless you're trying to talk to a satellite that's out there somewhere, like the Voyager, which is now still sending signals to us. It takes about 18 hours traveling at the speed of light for those signals to get to Earth. Hopefully they don't run into anything. But what we find more interesting is, because we're trying to deal with communicating with each other, we are actually trying to hit other things. We want to try to use these radio waves to our benefit. Okay, so radio waves, just like light, if you transmit something, will tend to hug the surface of the Earth a little bit, and this is known as ground wave. The lower the frequency, the longer the wavelength, the farther ground wave works. It tends to get curved a little bit. So if there's something that's known as a visual horizon, line of sight is called line of sight for a reason. It's how far you can see. So this is something called the visual horizon. There's also something called a radio horizon. So this would be the visual horizon out to here, and the radio horizon would be out to here. And that is largely because ground wave makes the Earth, because the wavelengths are longer, look a little less curved to radio waves as it hugs the surface of the Earth. Okay. And now if we were to look at that same, we'll call it VHF, UHF. And now we're going to take that same wave and we're going to aim it at the sky. Okay, so what would have to happen, not including satellites and things like that? What would have to happen up in the sky for that signal to come back down?
Have to reflect off of something.
It would have to bounce off of something, right? Well, there's not a lot up there that will bounce UHF and VHF waves back down. Once in a while, it does happen a little bit, but more than likely what ends up happening is it just shoots straight through the atmosphere and we never see it again. So basically VHF and UHF are typically line of sight for that reason. They're not propagated by the ionosphere. So now that brings up another question. Okay, so we have different layers in the atmosphere. We live in the troposphere, and then there's this thing called the stratosphere. And we have like something called like a mesosphere. And then up here we have the ionosphere. Okay, the ionosphere is broken into multiple regions. They're called D and E and F1 and F2. And they are specified by the height above the Earth's surface. The D layer starts at about 50 miles and ends at about 100 miles. Or maybe it's a, let's change that a little bit. Let's say it's nominally 30 to 50, and then this is 100, and this is like 250, and this is up to about 600 miles. This is not close in. Okay, so what ends up happening is that we have our layers of the atmosphere above us. Now, as you go higher and higher up, what happens to the atmosphere?
It gets thinner.
It gets thinner and thinner and thinner, right? So way down here in the troposphere, we have a lot of air to breathe, thankfully, right? As you go up into an airplane, into the stratosphere, if you lose pressurization and there's no oxygen available, everybody passes out because there's not enough oxygen to stay alive. Okay, so then you get up into the ionosphere and the atmosphere is really, really thin. Then the higher up you go, the thinner it is. You might get to the point where there are, like 100 atoms every cubic meter or something, but it's still the atmosphere. But what ends up happening is that we have this big yellowish orange thing in the sky. What do we call that? What's that big orangish yellow thing in the sky?
Sun.
That's the sun. Okay, and the sun, we think of it as yellow because that's the bulk of the light that comes out of it. But what are some other things that come out of the sun?
Solar flares.
Yep, solar flares. So we have particles.
Yeah, solar radiation.
Yeah, well, what's solar radiation? We have light. What else?
UV.
We have ultraviolet, sunburns. What else?
Charged particles.
Yep. Okay, well, we had particles already. So what else comes out of the sun? Infrared, that heats us. We have X-rays that come out of the sun. So if those ultraviolet rays and X-rays managed to make it all the way down to the surface, what would happen to our existence?
It would probably feel like Portland today.
Yeah. Well, except that it would end tomorrow.
Yep.
Right. We would basically be incinerated. And if we had any DNA, we'd be bombarded with X-rays and our DNA would be destroyed and we would basically be a completely lifeless planet. So fortunately, we have this thing called the atmosphere. And the atmosphere, which is largely nitrogen and oxygen, is really good at filtering out and absorbing a lot of the energy from the X-rays and the ultraviolet. Now, you can still get a sunburn, so clearly it's not all of it. But there's a lot of it that gets filtered out. So what happens to those X-rays and that ultraviolet energy when it hits the atmosphere? It occasionally you'll have a photon which comes down from the sun and strikes one of those things, either a nitrogen molecule or an oxygen molecule. And it has enough energy to take an electron, because if you think about what is inside an atom, you have your nucleus, which is your protons and your neutrons, and you have electrons flying around in different valence shells. And see, you didn't think we were going to get into chemistry today, did you? But basically, you have all these electrons that are flying around. Well, eventually, what will happen with one of these is that once in a while, you'll get a direct hit where one of those photons has enough energy and is in a direct hit to the point where it actually gets into one of those atoms and causes an electron to be ripped out. And the electron, because it's negatively charged, is now that, and you have a nitrogen molecule that is now positively charged. These are known as ions. You have a positively charged atom or molecule, which is an ion, and now you have free electrons floating around. Well, what do we know about electrons? And what do we know about ions? They have an electric charge. Well, if there's an electric field that goes up and flies through the air, what happens if it encounters a whole bunch of things that are electrically charged? What ends up happening is that depending on the number of electric charges up there, that actually impacts the waves that are striking that area and cause them to bend. The higher the number of electrons and ions that are floating around up there, the greater the chance that it's going to bend at higher frequencies. So the higher the density, the higher the frequency that can be bent. Well, okay, so now what happens if that energy gets bent? It gets refracted back to Earth. And we now are way over here. Where's it going to end up? Where's it going to end up?
It's going to end up a lot farther.
Yeah, it's going to end up a lot farther. And this is known as skip. And depending on the angle that it took off at, it may be possible or not possible for it to be bent. It could actually go off at a high enough angle that it'll still pass through. It could go off at a low enough angle that it'll be bent like that and it'll be absorbed. But basically what you'll end up with is this area, like in here, where you have successful bending. And this is basically known as ionospheric propagation, where you basically have signals that are going up into the sky and are being refracted back to Earth. They're being bent back to Earth. This area is known as the skip zone. And the reason that this is the skip zone is because it is the area in which the skip bounces right over. So if anyone has ever been on high frequency radio, such as with CB, and you'll notice that sometimes the skip is in, as they say. This is exactly what we experience. But you will also experience the fact that, let's say, from Oregon to Colorado is a good skip zone, and you don't hear any stations at all in between. So the question is, why don't you hear any stations in between? What do you think?
Because it's going right over the top of them.
You'd actually have to do the geometry, and the angle of takeoff would be such that the wave might get bent, but it doesn't get bent enough for a path to work. So the other thing that is interesting here is that we're going to erase this whole thing. I'm sorry. We now are going to draw the Earth again. We're going to have our D, E, and F1 and F2. Okay, down here in the troposphere, okay, this is where we live. We don't really get much in the way of X-rays and such. However, during the day, when the sun is overhead, we have a lot of direct radiation that's coming down into the atmosphere. What happens here is that because we're at lower levels, this whole D layer right here tends to absorb a lot of the energy that's coming in because it's got the highest density of all the layers. It's actually the lowest of all the layers of the ionosphere. And what happens is that, okay, well, we have an electron that gets made and a nitrogen molecule that gets made. But what happens is that then this goes flying off somewhere and encounters a plain old nitrogen molecule. And the same thing with the electrons. That will go off and that will encounter an oxygen molecule or an oxygen something. And basically the energy is such that it continues to get bounced back and forth. The degree of recombination of energy of electrons and ions is very, very rapid. Well, what ends up happening up there is, like, let's say you send a signal into that region, and that energy, it starts to get refracted back down. But really what happens is the energy is such that there's so much stuff here happening that there are so many electrons and so many nitrogen atoms or nitrogen molecules to absorb that energy and try to bounce it back, that this energy really ends up just causing movement of this stuff and causes things to bounce around. So the energy essentially gets absorbed, and this signal that you try to put up and bounce back down just sort of goes into that layer and gets disappeared. It gets absorbed. Certain frequencies, higher frequencies, have enough energy that they actually will get through this region into the higher layers. This is exactly why at night, AM radio can pass through, because the D layer disappears at night, but during the day, you don't hear any AM radio stations from greater than about 30 miles away. At night, that layer disappears and all those waves are now able to pass through it, because it's not there anymore, into these higher layers where they can bounce back down. So AM radio, if you look at your frequency dial, is about let's say 1,000 kilohertz, which is about 1 megahertz. But the AM numbers will say like 1,000 kilohertz. That is right in the band that it gets absorbed during the day, which is why, you can't hear AM radio stations for very long distances during the day. At night, again, because the D layer is directly generated by sunlight, and it's got a lot of electrons and a lot of oxygen molecules and nitrogen molecules. At night, when that energy goes away, that layer disappears very, very quickly. Everything recombines really fast because the density is actually pretty high. Well, now that absorbing layer is completely gone. And all of a sudden, you have this free path to get up into space. And that's why as soon as the sun goes down, you can hear AM radio stations over long distances. But now let's pick a different frequency. Let's go to, let's say 14 megahertz. That 14 megahertz signal, even with the D layer in existence. So let's put the D layer back. And we're going to make the D layer right here. So even with that layer, again, that frequency, which is about the 20 meter band, has enough energy to pass right through the D layer up into the upper reaches. So that's why you basically end up with frequencies that work during the day and other frequencies that don't work during the day. Whereas at night, other frequencies change, because at what time of day are you going to have your maximum levels of solar radiation up here in the sky? The daytime or nighttime?
Daytime.
Daytime. So now let's do this. We're going to have a very low density up here. We're going to have an electron here and an electron here, and an electron here, and an electron here. And now we're going to have our oxygens and our nitrogens. But now we're going to take all the solar radiation away. So we're not getting any new ions made. We're not getting any new electrons made. And every so often, even though they're really far apart at night, what we end up with is this. Oh, look, they found each other. Pop, they turn back into oxygen. Oh, look, these occasionally find each other. Pop, they turn back into a neutral nitrogen. So what happens is that during the nighttime, your density of electrons up here tends to go down. So the density of electrons that exists is proportional to the frequency that will work really well. So high density, that's density, is higher frequency. Low density is equal to low frequency. So at nighttime, which do you think will work better, high frequencies or low frequencies? When everything fades away.
High.
Well, again, high frequencies require high densities. So when do you have higher densities of electrons? When there's more sunlight coming down. And at night, that fades away. So that's during the day, you have high densities of electrons. And at night, you have low densities. And since high density translates to high frequencies and low density translates to low frequencies, during the day, you end up with high frequencies. And at night, you end up with low frequencies. Now, there's a really interesting way that I have to visualize this. One of the really great tools that we have available to us is this thing known as PSK Reporter, which is an automated system where people who are operating on digital modes have their computers tied to the internet. So let's take a look at an area where we're getting a lot of sun right now, which is, for instance, where we are in Oregon. So notice we have these markers, which are the 20-meter band, which is 14 megahertz, and 17-meter band, which is 18 megahertz. And we are getting really good propagation actually into Europe, into Asia, even though it's going through the dark a little bit. The sun is right over Florida right now. So we're getting irradiated with a lot of solar radiation. So you would expect that higher frequencies would work better. Now, what we're going to do is we're going to look at, for instance, I'm going to pick another grid square, which should be Sydney, Australia, I hope. Come on. So we've still got some of the orange lines, which are the 20-meter band, but notice we've also got the blue ones. And the blue ones are lower frequencies. The further you get into nighttime, the more pronounced that gets, to the point where you'll have only the low frequency signals working properly. So this pattern that you get is something that comes day and night, and continually changes. Now, so what you end up with is you get some really cool patterns which follow what's known as the day-night terminator. And the other thing is that you also have this line between light and dark, between black and white. And what do you think that would be called if it's between black and white? It's a line. It follows the curvature of the Earth and where the sun is shining. And what color would you say is between black and white?
Gray.
Gray. That is actually known as the gray line. And what you'll find is that a lot of really interesting propagation happens on the gray line because it has some properties of daytime and some properties of nighttime. So the middle of the day can actually be quite boring. The middle of the night can be quite boring, but wherever you are, when it changes from day to night or night to day, that's when you get some really, really interesting propagation happening. Okay, let's see. As far as propagation goes, why are UHF signals rarely heard beyond the radio horizon? Because UHF signals are usually not propagated by the atmosphere, by the ionosphere. So even though they can make it up there, that's why we use UHF. So who's with PSAS? Who's dealing with the satellite? Who's dealing with satellites?
I am a little bit.
Okay, what frequencies do you use to talk to the satellites?
I don't know about that.
Okay. Anyone? What frequencies do we use to talk to satellites?
Is it super duper high ones so that they can get all the way through all the way up the atmosphere and
They-
on into the satellites?
Yep. We basically use 144 megahertz and up for the most part. And the higher the frequency you go, the easier it is to get through the atmosphere. So we go with typically 70 centimeters. If we look at our frequencies chart, let's see, where did I put it? Here we go. This is another thing that you'll get used to seeing. This is our band plan. This is the commonly used frequency bands that we have access to. Notice this is VHF, UHF up here, 70 centimeter band. This is used for a lot of satellite uplinking and downlinking because it's 30 megahertz wide. There's a lot of space for very high modulation signals. And it passes right through the atmosphere like it's not even there. Once in a while, our very low altitude stuff, known as tropo, this is in our troposphere. Once in a while, if we were to expand this troposphere, so here's our troposphere, and we have a warm layer and a cool layer and a warm layer again, and maybe another cool layer up here of air. We get these different bands of air, which can be called temperature inversions. Has anyone ever driven down a highway? If you're over the age of 18, right? Have you ever looked out on a really hot day at the road and noticed that it looks like right on the surface of the road is a reflection of the sky? Anyone ever wonder why? Basically, what you're getting when you do that is you have an area of very hot air down on the road surface, and immediately above that, you have cooler air, but you might have a little more hot air above it. What you end up with is a temperature inversion. And what that forms is an actual guide for the sunlight that comes down that causes it to do this. And when you're looking at it, what you see is essentially the sunlight that's coming down that's then being channeled right over the highway in a little duct. And that's actually known as ducting. Well, if it exists for light, it probably works for radio too. And this is actually known as tropoducting. But because the wavelengths are so much bigger, whereas this might be, a half a mile, this could be 300 miles. This could actually be from California to Hawaii, or 2,500 miles. And people actually do that on purpose. When they get a temperature inversion over the Pacific Ocean, you'll have people who go up to a mountaintop in California and people who go up to a mountaintop in Hawaii, 2,500 miles apart, and they will talk over UHF, which is normally line of sight. But if they can get their signal up into a duct and it bounces around and they're sitting on mountaintops, they're basically in the duct. And you can actually, this is another form of experimentation. You can actually make UHF signals that are 2,500 miles apart talk to each other. Just another fun and cool thing that we can do and experiment with. Yes, I see a hand up. I can't hear you though. Scott, I see your mouth moving, but I can't hear you.
Can you hear me now?
Yes.
Okay, all right.
Good.
Okay, so you have to excuse me. I'm kind of a bonehead at this. Propagation, what you're saying is the heating of the sun or the heating of the atmosphere reduces the propagation. Is that what it is, or am I thinking of it a little higher?
Well, it's not heating. What we have to think of it as modification of the atmosphere. So let's draw the atmosphere, right? And you have to think down on a molecular level, the fact that you have nitrogen and oxygen floating around. And the sun basically bombards us with energy in the form of photons, which are basically packets of energy. And every once in a while, what you'll end up with is a photon that strikes a direct hit on a nitrogen atom, which causes an electron to go flying out of it. And then that nitrogen atom becomes a nitrogen ion, or the same thing with oxygen. So basically what ends up happening is literally you build this continual density, because every so often you'll also end up with a nitrogen molecule or nitrogen ion that finds an electron just randomly and says, oh, well, I'm positive and you're negative. We're going to attract and we're going to pop and disappear and turn back into nitrogen. So you have this continually occurring dance. It's like a balance between stable molecules and electrons and ions. The more energy that's coming down, at any given time, the more it gets tilted, the more the balance gets tilted toward the ionized portion of it. Well, you get more energy during the daytime when the sun is directly overhead. When that fades away and you get into nighttime, well, you don't have the energy coming down anymore and your balance gets shifted the other way. So your balance now heads over toward stability. Well, if your balance heads over towards stability and you need these free electrons floating around to do the work for you, at night you don't have them anymore. The density starts to go down. And the density of the electrons up there is directly proportional to the frequency that can be bounced. And that's why we have a day-night change. That's why certain frequencies, like if you look at this frequency chart, we're just going to look at the high frequencies, which is between 3 and 30 megahertz. If I were to draw up here between, let's say, the dividing line would be right around 20 meters. 20 meters can work in the day or the night. It's kind of the crossover point. Anything that's a lower frequency or a longer wavelength is basically a nighttime band. Anything that's above in frequency, shorter wavelength, is a daytime band. And when you get on the air, when you get on the high frequency bands, you will see that. You will see that 20 meters is basically always good somewhere. 80 meters is a dead of night band. I mean, 2 hours after sunset, it'll be hopping. But and right at sunset, it will basically just disappear. You will hear literally nothing.
So what you're saying is from 2 meters to 20 meters is more for the daytime?
Not 2 meters. I mean, 2 meters is a separate thing. 2 meters is VHF. It's typically line of sight. So the 6 meter band, 2 meter band, they don't even play. They don't even ever come into play when it comes to that ionospheric propagation. We're really just dealing with what they call MF, which is, way down here in 160 meters. That's like AM radio, and the high frequency band. And what you'll see is, well, I can bring up another really cool site that we use a lot. And this is known as VOACAP, which was created by the US government as a tool for predicting whether or not certain signals could be directed into certain parts of the world that we wanted to spread propaganda. We'll just call it news and information, right? But it's really propaganda. It's like, we want to tell the rest of the world our side of the story, right? So let's say that we want to send a signal into Eastern Europe. So we're going to pick Poland, for instance. This is, before the end of the Cold War. Okay. So now let's go with 100 watts, and we're going to send single sideband. Oh, we're going to send AM. Now we're going to look at our charts. Here we go. Now we're going to bump that up. Okay, so basically this says from the east coast to Poland, we have our ideal shot on the 20-meter band between, let's say, 21 and 2200 Zulu. This is universal time, which would be about, let's see, about 4 in the afternoon. And on at other times of day, notice other areas, it would work better. Now let's instead put a transmitter here in the UK. Okay. So this helps determine, let's say, okay, well, let's say we want to put a signal into Kazakhstan from Finland. This helps us predict where propagation is going to work best and when, and where to put a transmitter if you can do that. If you can't do that, and I say, okay, I want to make a contact with Kazakhstan, this basically tells me this is the best time of day, the hotter the color, to do it. And this is the frequency band to do. Let's look at South America, for instance. Right? So at night, these are nighttime down at the lower right. Notice that I'm down on the, let's say, the 30 and 40 meter band. Up here at the top, this is about 3 in the afternoon. All the higher bands work. So this is a really good representation of how it changes during the day. And this is all caused by changes between day and night with regard to the position of the sun overhead.
Okay.
Oh, somebody please answer that. It's only one more ring. Oh, no more rings. Okay. So now moving back to our book. Okay, we now also have something called multipath. So now we're going to think about a wave. I don't know why I drew that kidney bean. Okay, so now we're going to think about a wave, and when it goes from point A to point B, it's going to go up and down and up and down and up and down, and it has a wavelength, which we can measure from here to here. This is our lambda, which is short for wavelength. Now, if it goes from point A to point B, and there's nothing in the way, I would say that the signal will get there. That's just, there's no reason for it not to. Now, what we're going to say is by the time it gets to point B, here's what the signal looks like. All right, no problem at all. Now, what we're going to draw is a rock. It's going to be a rather big rock, like a hillside, such that there are, because you don't just send a signal one way, you send it this way, and you send it this way, and you send it this way, and you send it this way. Well, okay, some of the signal that goes this way will go like this, and some of it will end up at the same place. So now, if we were to do some geometry and take a look at this, we can say, okay, this is distance X. What is this distance? What is that distance? We think about triangles. Compared to X, is that total distance going to be longer?
No.
It has to be longer. Otherwise, it wouldn't be a triangle. So this is X plus something. Do we know how long that little something is? Not really.
Don't we up to a squared plus b squared
Well,
equals C
and that's
squared
only if it's a
function?
right triangle. So we really don't know. I mean, we know that this is an angle, but we don't really know what the angle is. So that doesn't really help us. What we know is that that signal had to travel a certain distance further, right? So by the time it made it distance X, maybe it was here. So we really have this area, this extra distance, which is known as question mark, beyond the distance X. If they got there at the exact same time, let's say that they were both the signal that went straight, they would add together. It's exactly what we'd expect because they're both following the same route, right? But now what we have is a signal that by the time it gets there is now delayed by a certain amount. It got there late. Do we know when it got there? I can't really predict it. Let's say that it got there this late. Okay, so now what we're going to do is we're going to add at any point, we're going to add the two together. Right there. What is the sum of a plus and a minus?
If they're of equal values, it'll be a 0.
That's right. And if that happens, what you end up with is that the signal completely goes away. That is known as negative or destructive interference, where you basically wipe out the signal completely. Now, if the signals, let's say you have the signal that gets there like this on time, and the other signal gets there this late, those would add together, wouldn't they? So you have two kinds of interference. You have constructive and destructive interference. If you have constructive interference, you get this. That is a good thing. If you have destructive interference, you end up with nothing. And that's typically a bad thing. So can you predict which one you're going to have if you don't really know how far this is from the mountaintop? And the answer is no. So what we do know, however, is let's say that we are on the 2-meter band. How long is this wavelength? I just gave you the answer.
2 meters.
2 meters. How far is 2 meters? Approximately. How long is 2 meters physically?
6 feet.
About 6.5
is
feet. About 6.5 feet. Okay, so if our signal instead is getting, if our second signal is getting here like this, how far shifted is that? It's about a half of a wavelength shifted. How many feet is that?
3 feet.
That's about 3 feet. So do you think if you take a handheld radio and you move around the room, you might be able to find a place where they are in phase instead of out of phase? And the answer is yes. And that is why it is often recommended if you're on a repeater or something and you're using a handheld, somebody will say, hey, you're in a bad spot. Can you move a little bit? Okay, don't move. Stay right where you are because you're in a good spot. This is exactly why. Because you go from an area of constructive interference to destructive interference. Okay, who's taking physics or has taken physics?
I have.
Okay. Do you remember doing like interference patterns with light?
Kind of.
Okay. This is basically the same thing on a macroscopic level. They're just electromagnetic waves. It's just that they're a lot bigger. So the spaces between constructive lines and destructive lines are a lot bigger. And they're big enough that you can actually move around and actually get in between them. Okay, let's see. Picket fencing. Let's say you're in a car and you're driving along and you go from areas of constructive, destructive, constructive, destructive. What's it going to sound like as you pass through them?
going to be choppy.
It's going to be all choppy. That's a good way to describe it. Kind of like when you're trying to talk to somebody and you're walking along a picket fence. Your signal gets through, and then all of a sudden it doesn't anymore. And that's actually known as picket fencing. Data transmissions, if you're using data and you have multipath, this is known as multipath. If you have negative, or if you have destructive interference, the same thing as you not being able to hear somebody will cause your data rates to fail. You basically won't be able to hear who you're talking to, and your data signals will have lots of errors. Let's say that you have a building nearby and you don't have a direct path to a repeater, but you have a building that's got like metallized windows all over it. That can actually function as a repeat, almost like a mirror. It works for light. It might just work for radio. So you might be able to find a path that bounces a signal directly to the repeater off of a building. Let's see, there's also something called knife edge diffraction. A knife edge is basically a sharp object. This goes back to physics again, where you basically have something called a single slit experiment. You transmit a signal through a space and it gets diffracted in lots of directions. Well, if this is a mountaintop right here, and you send a signal up over a mountaintop, some of the signal actually gets diffracted back down to the other side, which means that two people who can't see each other, using something called knife edge diffraction, because this has to be fairly sharp, might be able to hear each other. Let's see, on UHF signals, the effect of vegetation. Well, it turns out that UHF signals and microwave signals are getting close to the resonant frequency of water. And what is there in leaves? There's a lot of water. So when you transmit a signal at a leaf, some of your energy will go toward heating up that leaf. The same way that if you stick something in your microwave oven and you turn it on, a microwave oven operates at 2.4 gigahertz, 2400 megahertz. That's the resonant frequency of water. If you do that, basically what'll end up happening is you heat something up. If you take a transmitter on VHF and you point your antenna at a tree, you're essentially going to be heating up the leaves and your signal is going to be knocked down quite a bit. And that's known as attenuation. Okay, antenna polarization. So this is on page 45 of the book, 45 of the PDFs. The property of a radio wave that defines its polarization is called the electric field. When using different polarizations on opposite ends of a VHF or UHF radio communication link, your signal is attenuated. Your received strength is going to be reduced. Attenuation basically means to reduce. And what antenna polarization is normally used for long distance CW. CW is Morse code. SSB is single sideband. That's known as horizontal polarization. What ends up happening is that the same way that light can tend to skip off of things like the highway and get horizontally polarized light skipping longer, bouncing off of your hood. We use horizontal polarization because it does better when it's bouncing off of things like water. Let's see, other propagation phenomena. Sporadic E. Okay, so what are the layers of the ionosphere again? What are they called? Anyone remember what those letters are?
Was it D, E, F1?
F1, F2. Yep. Okay. The D layer is absorbing. That's really all it's good for. The E layer can actually be used good for refraction. And it's not great. It's fairly low altitude, but the E layer can actually form these clouds of electrons for some strange reason that's still not completely well understood. But what can end up happening is you can get so much in the way of electron clouds up here that VHF, like 6 meters and 2 meters, can actually get bounced back down. But because this altitude is only at about 100 miles compared to 500 miles, let's say, your range is typically less. So this can be up to about 1,000 miles. But it's on VHF, and that's known as sporadic E. Okay, so anytime that you can make an electron cloud, you can bounce radio waves off of it. So if we think about the Earth, and we draw the Earth, and we draw the magnetic field around the Earth, it kind of looks like this. What happens up here at the North and South poles sometimes? What do we get? We get a light show. What's that known as?
Aurora borealis.
Or Aurora australis for the South Pole. But yes, we get the auroras forming. Well, okay, auroras are essentially very energetic swarms of electrons and ions. Well, now that we know that radio waves, in particular UHF and VHF, or typically let's go with 6 meters. 6 meters, if you shoot it up into the aurora, it will typically get bounced back out, which means that this person over here could actually talk to another person over here if they can get a signal into the aurora. This is known as auroral scatter or auroral propagation. And it usually sounds very distorted. We usually use the 6 meter band for the aurora. And if you want to take an interesting listen, take a listen to somebody who's recorded a contact using auroral scatter on voice. And it's really trippy. It's very cool, but really, really trippy. Signal strength is all over the place and they sound really distorted. Meteor scatter. As a meteor streaks through the atmosphere, it leaves a hot trail. That energy creates an ionized trail in the air. Well, if it's an ionized trail, somebody can take a signal on the 6 meter band and bounce it up and it comes down somewhere else. And this is known as meteor scatter. Again, the 6 meter band is very, very good for things like that. Okay, tropospheric ducting. Again, that's through the troposphere on VHF and UHF for about 300 miles. My experience with that was when I was in college and I was watching on a humid Sunday morning, I was watching UHF TV and I saw a station come in from Connecticut from the University of Maryland. And I said, oh, I'm going to get on 2 meters. And I proceeded using a handheld radio like this. I talked to somebody through a repeater in Connecticut. So that's about 300 miles away. And that's known as tropoducting. What causes tropoducting? That's temperature inversions. So you get hot and cold. Humid Sunday mornings are really good for that. If you happen to live in the Southeast, you're going to get a lot more tropoducting and a lot more E-skip, sporadic E, than we do in Oregon. We have very rigidly hot and cold areas. In the Southeast, you get a lot of mixing over the Gulf of Mexico and you get some incredible propagation. What weather conditions might decrease range at microwave frequencies? You would know this if you have, let's say, the dish network. When it rains, sometimes your signal can go out. The reason that happens is because those operate at microwave frequencies and water absorbs microwave energy. So rain will kill your signal. On the 10 and 6 meter bands, high frequency bands, there's little effect from rain at all. Okay, the region of the atmosphere that can bend HF and VHF radio waves is known as the ionosphere. Okay, so we're on page 48, by the way. This is called HF propagation. A characteristic of HF communication compared with communications on VHF and UHF is that because the altitude of the layer that we're bouncing things off of is so much higher, we can get much longer skip. So long distance ionospheric propagation is much more common on HF. Which of the following bands can provide long distance communications from the F region during the peak of the sunspot cycle, which we haven't talked about? So the sunspot cycle, in addition to everything else, goes in 11-year cycles. And we are right now about here on the way up on cycle 25. So when there are more sunspots, typically there is more radiation. And what did we just say? What did we say about times that there are more radiation? What does that do to the atmosphere?
More ions.
More ions, that's right. So when we get to the peak of the sunspot cycle, we get more radiation, which translates to more ions. More ion density translates to higher frequencies that work properly. So when we start looking at that, we say, okay, what does our chart look like? Here's our band plan. Well, what that means is that at the peak of the sunspot cycle, the 10-meter band will typically come alive. You can go for 7 or 8 years where you never see a 10-meter opening, where you have propagation between 2 points on the planet. And then all of a sudden, when the sunspots are in, you get a lot of solar radiation coming in. 10 meters will open up to the entire world all at once for everyone. It's really wild. Okay.
How long will that usually last?
Who knows? The peak, the last sunspot cycle we got was kind of a bummer. I mean, there were a couple of days of good propagation. For those who were alive in 1958, 1959, and had their licenses, 10-meter band was open for years because it was a very big sunspot peak. I mean, literally years of big propagation to all over the world every day for years. I've never lived through that. I'm only 53. I wasn't born until 1969, and you know, the big peak had already passed by. But it doesn't mean we won't see another one. And if you're young, you stand a better chance. So okay, let's see. So 6 meters and 10 meters, even 6 meters. So if you talk to people who were alive in the late 50s, they could actually get F layer propagation on 6 meters. So like that's VHF from like the US to Japan, US to Europe for hours at a time, which I've never experienced in my entire life. Because of the way the ionosphere changes during the day, propagation is best on high frequencies during the day and low frequencies at night. So what is the best time for 10-meter band propagation? That would be basically daytime during periods of high activity of the sunspots. There's also something called fading. Okay, so now we looked at the fact that we could have 2 different signals coming in, bouncing off of different paths. This is known as multipath, right? Sometimes they can add together, sometimes they can subtract. So we're going to get rid of that one. Okay, so you've got 2 signals that are bouncing through the ionosphere. This one obviously bounced off of something different. Well, the ionosphere is not flat. Sometimes it's higher, sometimes it's lower. There are people who actually study the ionosphere for these kinds of things. They're known as they use ionosondes for doing this. They can actually take Doppler shift of how much the ionosphere goes up and down during the day and how much it changes from second to second. What happens is that you may suddenly go from this path to this path, in which case this was a good path and this was a bad path where they cancel. And what you'll end up hearing is like 15 seconds of fade between 2 stations where the signals completely disappear and then suddenly come back. You know, sometimes propagation works great and sometimes it hardly works at all. Sometimes it varies from second to second, and it's really wild, especially if you're, for instance, talking between the United States and Europe, and you hear stuff going through the aurora. It goes over the North Pole and it sounds all warbly, like continually warbly. Very weird sounding. Okay, let's see. A likely cause of irregular fading of signals, that's random combining of signals by different paths, which can change. And the fact that signals that bounce off the ionosphere, the energy gets absorbed and re-emitted. Typically, the polarization is random or elliptical by the time it comes out, which basically means there's part horizontal and part vertical. Independent of how you sent it up there, it's going to come down however it comes down, which basically means that for high frequency antennas, the polarization really isn't so important. Okay, how about another 5-minute break, everybody? When we get back, we're going to start talking about electrical principles. So we're kind of skipping around in the book a little bit, but electrical principles is movement of electrons. And since we pretty much know what an electron is, movement of electrons so that it does our bidding for us. Any other questions before we go? Take the break to think of some good questions.
Can I ask a quick question?
Yep.
When you're transmitting on the radio and you're saying that the signal is going in different directions.
Yep.
Why is the person on the other end not receiving an echo or delay?
Who's to say they're not?
Okay. Okay, thanks.
And that's the whole thing. Who's to say that they aren't? You know,
okay.
It might be that, you know, in fact, it's quite likely that they are, but typically they're going to be attenuated to the point where it doesn't make a difference, that the big signal is the one that they're going to get. But it's not, there's no guarantee of it. And if you listen to the high frequency bands, you will, you know, because all the signals are going up and bouncing around, there could be very easily 2, 3, 4 signals that are getting combined because they went through different paths, and the path lengths are different enough that by the time they get added together, you know, sometimes sounds like that and then comes back, then comes back again, and then it comes back again. And it's really fun trying to make a contact with somebody when they completely disappear for seconds at a time.
Okay. Thank you.
Part of the challenge. More coffee. All right. Anybody have any questions all lined up yet?
No questions, but it's just very interesting.
Good. Well, you know, it's really interesting because I find that there are like 3 groups of people who I get in classes. One is kids. 2 are adults who find that they have a new interest in this. And 3 is people who always wanted to get a ham license when they were kids and never did. And now they're at the retirement age and they really wanted to finally do something that they always wanted to do. I get a lot of those, actually. It's really cool. I have a lot of friends who are in that boat. Just locally, who I've taught locally. And it's really cool because, I mean, I got my dad introduced me to a ham friend when I was 14. And I got my license when I was 15. I probably someday would have found ham radio otherwise, but who knows when it would have been. And I mean, if it weren't for the fact that I got my license before I went to college and then upgraded right when I was a freshman, I don't know that I would have had time. And, I look at what I have gotten from this hobby in my life, and it's almost incalculable what I've actually gotten from it. I mean, I've gotten jobs. I've got friends all over the world. I've gotten all kinds of experiences. I just got invited to go to Vanuatu next year. Anybody want to know why I got invited to go to Vanuatu?
My first question is, what is it?
Okay, so we as hams, a lot of hams really, really enjoy doing something called DXing. And DXing is the act of making long distance contacts. Certain countries in the world. Now, when I say countries, there's a map of the world. Let's see. So here's a map of the world that I'm going to put up here. Let me see if I can get it up on the screen. Oh, shoot. Let me see images. Come on, why won't you get it bigger up there? Sorry, I'm trying to get a DXCC map. Okay, there we go. There's a DXCC map. Now let me put it up on the screen. So the world is a big place. There are 193 countries in the world, but a lot of countries have territories that are physically distant from the mother country. There are a lot of Caribbean islands that are owned by either France or the Netherlands or Great Britain or the United States. There are a lot of Pacific islands that are parts of other areas. The French have a lot of Antarctic areas, Antarctic islands, stuff in the Indian Ocean. A lot of them are either underinhabited or uninhabited, or there's only like a few people there working at a science station or a radar station or something like that in the middle of nowhere. Each of those has its own separate entry. And here is a list of all the different places in the world that there are to contact. So if you happen to like gaming, try working all of them sometime. I've been at this for 37 years, and I've confirmed 260 of the 339. And there's a very good chance I will never complete them all. I mean, I know people who have, but there's a good chance I will never get them all. And I've been at it for 37 years. So, talk about the long game. That's the long game. So Vanuatu is a fairly small country in the South Pacific. And so because Vanuatu is somewhat rare, on the air. There aren't a lot of hams there, and the ones that are not terribly active. But but a lot of these smaller governments are more than happy to have you come and get a temporary license and set up a station. And once people find out that you're there, you let them know. You'll basically, in a period of a week, be able to make contact with, oh, I don't know, 10, 20,000 stations and be able to get Vanuatu on the air for and confirmed for lots of people who are trying to work everything. So I just got asked to go to Vanuatu for that's the first time I've gotten asked to go to any one of these places, which is really cool because I've been a hunter for 35 years. I've never gotten the chance to go somewhere and be the hunted. All right. Any questions? Remember, there's no such thing as a dumb question. Just dumb answers.
I have a question.
Yes.
I didn't introduce myself earlier because I'm not a big talker, but
okay, go ahead.
So part of my question is I'm like a tech. I like to be behind the scenes. I like to be in the server room. I'm wondering if there is like much space for someone like me. Like I don't really want to talk to everyone all the time.
So let me just say that let's see. And Arduino. Okay, so notice this thing, a ham radio, an amateur radio guide to Arduino projects.
Yeah, actually, I'm an electrical engineer.
Okay.
And I just switched, careers from IT, server networking stuff to electrical.
Yep. Okay.
Yeah.
So let it suffice it to say that I'm a lot more talkative than a lot of people. And I know that a lot of people don't ever want to talk on the air. In fact, my I'm going to say colleague at the University of Oregon Club Station. Here's his, let's see. Here. So this is Dean. Notice he doesn't have anything up there for his bio or anything. He doesn't like talking on the air. He likes doing digital stuff. He likes doing like hidden transmitter hunts and things like that. Whereas on my side, like here's my bio, right? I'm on the air a lot. I talk a lot. And by the way, there's my daughter who's now 20. She's W7HER. But we're both active. He likes the teaching aspect of things. I like the teaching aspect of things, but he also likes the digital side of things. There's no reason why, especially now, there are a lot of people who never pick up a microphone. Their interest lies in designing equipment or coming up with new communications protocols or designing and building antennas and testing them. I mean, this hobby is big enough for, literally anything you want to try.
Great.
So
yeah, I've been listening on SDR for a long time. But I never really have the desire to press the talk button.
That's fine. Let me just bring this up. Let me go to Web SDR. I want to go to the one in the Netherlands. Here, I'm going to share this. Okay, so I'm going to turn the volume up if I can find it. Okay, so we're going to pick a frequency that's going to be busy, maybe. Okay. I personally much rather grab a Morse code paddle than talk. On the air, I'm not really much of a talker. I greatly prefer Morse code. Now you see all these signals over here? That's all digital. This is all digital. I don't see any teletype on today, but there's people doing that. There's, let's see. And if we go over here, we'll see a couple of voice signals.
Contest 5 Bravo 4 Whiskey November 5 Bravo 4 Whiskey November contest. Alpha Italy Fox contest.
So there's definitely enough room for everyone.
One further question that kind of relates to when you looked up on your profile.
Mm-hmm.
I see that there's a home address listed that's open for everyone to see.
Yep. You
Can
just need,
I
yes, you
have
can
a
just
PO
use a
box?
PO box. You just
Okay.
basically the only reason that it needs to be there is that the FCC needs to be able to get a hold of you. So you have to have an address.
Yeah, but they use email addresses now. And
No, they do. They use snail mail too.
okay.
It has to be, there has to be a street address.
Yeah. Well, that's why I was wondering.
But it
about the
could be a PO box.
Yeah.
Yeah, it
If
could
it's
be
a
a PO box.
I'd feel a lot more comfortable. I wouldn't want my address blasted.
Yep.
Thanks.
Okay. Everybody ready? Here we go. Electrical stuff. We're going to do electrical circuits. And the first thing we're going to do is Ohm's law. So we are on now page 7. Okay, so we're going to have to do what a couple of basic things are. So the first thing we're going to do is we're going to draw this. This is a resistor. This is a capacitor. And this is an inductor. Okay. So these are our 3 basic components. So the ability of something to resist a flow of electrons is a property known as resistance. And it is measured in ohms, named after Georg Simon Ohm. So that's our resistance, and we use the big letter R for resistance. All right, now we also have a battery, which has a big letter E and a positive and a negative. This is a battery. This is voltage measured in volts. Big letter V, named after Alessandro Volta. Now, we also have in a piece of wire or anywhere that we have electrons flowing through something, this is known as a current. And it's measured in amperes. And this is given the letter I for current. Don't ask, it's French. And that's named after Ampere, who was a French scientist. A capacitor has something called capacitance, which is from capacity. It's the ability of this thing to store energy between two metal plates. This is units of farads, named after Michael Faraday. It's given the big letter C for capacitance. And then we have an inductor, which has something called inductance. It has a letter L for inductance. Again, doesn't make sense, really. The units are henries, named after Henry. I believe it was Joseph Henry. And a capacitor has the ability to store energy in an electric field. If I put a plus here and a minus here and a plus here and a minus here, those charges want to get to each other, but I'm holding them physically apart. That stress, that strain, that force that I'm using to hold them apart is actually a storage of electrical energy. Now, what I'm going to do now is draw a piece of wire, look down at the bottom, that has a current flowing through it. A current is just a movement of electrons. As electrons move through a piece of wire, they generate a magnetic field. Right? Two electrons and opposite charges that are a distance apart, they generate an electric field. Electrons that are moving generate a magnetic field. And in fact, if everyone holds up their right hand and wiggles their thumb, the direction of movement of your thumb, the direction of your thumb is the direction of the current. And if you roll your hand forward and then around so that it wraps around, that is the direction of the magnetic field. It actually makes a loop around the wire. So if I have an inductor and I have a current flowing through it, that will actually generate a magnetic field around the coil. The amount of energy I can store in a magnetic field is basically the inductance of that device. A bigger inductor can store more energy in a magnetic field than a small one. Okay. So those are our basic components. Those are our basic things. So we have a resistor, capacitor, inductor, voltage, which is push, and current, which is flow. Voltage and current, if you think about it, voltage is, let's say you have a reservoir. How high above the other lake is that reservoir? The ability to push water out and down into the other area, if the dam were to break, that's your voltage. The amount of actual flow that happens is guided by how much resistance there is. If the dam is there, you don't get anything, right? If the dam breaks, you get a lot of flow because you have very little resistance. And it's important to note that just like water flowing, electrons follow the path of least resistance. That's generally, that general rule holds true. Okay, so now we're going to draw a very simple circuit. Okay, a circuit comes from the word circle. It basically means it's a closed loop. So here's our plus and our minus. Yes, I know. Electrons are what charge, everybody, plus or minus?
They're minus the
They're
protons.
minus, okay. Right, they're minus. Electrons are minus, which means that in a battery, the electrons really should come out of this side, out of the minus side. Well, an electron was not really known to exist when people started working on these things known as batteries. They didn't know that it really, well, let's just say they got it wrong. But the mistake has stayed that way for a long, long time, and we're not going to fix it now. So what we're going to do is say that the current comes out of the plus and goes around the circuit and back into the minus side. Okay, so that's our current. Here's our resistor. Okay, this very simple formula, E equals I times R. That is Ohm's law. Our voltage, or our electromotive force, is equal to our current times our resistance. I can draw it like this, E equals I times R, like that, so that whichever one I don't know, I just blank that out. So if I have, let's say, 1 amp of flow and 6 ohm resistor, I can say, if I were to measure the voltage, what would my voltage be, or my E? And I don't know the E, so it's I times R. So I can remember how to write it out. Is equal to 1 times 6 is 6 volts. So if I were to take a voltmeter right here and measure my voltage where I had that much current flowing through that resistor, I would get 6 volts. Okay, so Ohm's law, once again, very important. And you know what's really interesting about Ohm's law? So I've been working on machinery for the last 24, 25 years now. And 90% of things that go wrong are a direct result of E, or are exactly explained by E equals I times R. Isn't that funny? With all the complicated math out there and all the complicated circuitry, literally 90% of troubleshooting problems come down to E equals I times R. And that's going to be true just about anywhere. Okay, so what we're going to do is we're going to draw a little circuit. And once again, we're going to figure out how much current flows and stuff like that. So our first one is going to be a very simple Ohm's law application. All right, so I'd like everybody to tell me the answer as soon as you know it. So let's say that we have a 10-volt battery. You know what? Let's make it a car battery. This is actually really important. What's the voltage on a car battery? Nominal, please. Who
12.
knows? 12 volts. Actually, if you were to measure it, it'd be 13.8 if it's fully charged. But we're not going to do that now. It's a 12-volt battery. Okay. Now, does the voltage ever change? If we were to plot that voltage, ideally, that voltage is, if this is 0, we're going to be at 12 volts, and it's always going to be at 12 volts. This is actually known as DC, or direct current. DC does not change from positive to negative. It always ideally stays exactly the same. So this is a 12-volt DC battery. Okay. And let's say that this is a 1 ohm resistor. So what letter would I use for my battery? You guys can all unmute yourselves for this. You're gonna be able, that would be our E. What letter would be used for our resistor?
12. Or no, 1. Sorry.
1.
No, but what letter would we use for
R.
our resistance?
R.
We use R. And now we have our current. What do we use for current? What letter?
I.
I. Okay. Now we can do this. E equals I times R. Okay, what is our unknown in this case?
I.
We don't know our I. So we can take this and we can cross it out. And we're left with E divided by R. So I, for those of you who aren't good with algebra, this is a nice little thing, nice little trick. E divided by R. Okay, so what do we get?
12.
12
divided by
amps.
1.
12 divided by 1 is 12 amps. Okay, that's our current. Okay, so now that we know this, this applies to pretty much any circuit that you would ever want to do it on. I mean, Ohm's law is Ohm's law. It is a law. It's proven. Okay, so now what we're going to do is we're going to add a second part of Ohm's law, which is the power part. P is equal to I times E. Okay, so E is volts, I is amps, and how about power?
Watts.
Power is in watts. Okay, and a watt is actually a joule per second. A joule is a unit of energy. So that is a watt. But what's really cool about power is that a watt of power is a watt of power, because energy can neither be created nor destroyed. It just changes form. So if I have a watt of electrical power, I can convert that, assuming I don't lose anything to friction or inefficiency. I can convert that to chemical power. I can charge a battery. I can convert that to motion, right? I can convert it to mechanical power. I can turn a flywheel. I can run a motor. I can convert that to heat. I can actually directly run it through a resistor and use it as heat to heat something. Power is power. It can neither be created nor destroyed. It just changes form. And because it's that same three things, I can do PIE, draw the circle the same way, and X out the one that I don't know. So, well, now we're going to look at this circuit, and what do we know already? Do we know our I? Yep. Do we know our E? We do. So if we're looking at this P equals I times E, we don't know our power. So we can cross that out. And then we have P equals I times E is equal to 12 times 12 is
144.
144 watts. That's it. So now we know how much power our battery is required to spit out in order to run that circuit. Okay, so how much power is being dissipated in that resistor? Assuming our wire is perfect and our battery doesn't have any losses. I gave you a hint. Power and energy can neither be created nor destroyed. They just change form.
No, no,
So
no.
if the battery is making is supplying 144 watts, how much of that power has to be sent out as heat by the resistor?
144.
144 watts. Has to go somewhere, right? That's a fundamental thing that you'll get used to saying, that basically in a closed system, power in has to be equal to power out. It has to come out somewhere. So this is a closed system. If I put 144 watts in, it had better come out somewhere. And there it is. It comes out as heat from the resistor, and it's in the exact same amount. Okay, so now let me ask this next question. What if this resistor were rated for a continuous power dissipation of 100 watts? What would happen?
It'd catch fire or fry out as soon as the 100 watts is burned off.
That's right.
You got 44 more coming in.
Yep. Basically, what would happen is you'd end up with a resistor that started to get really warm and then maybe turned bright red if it was made of like ceramic. And then if there was anything around it, it would get really hot, and then it would start to smoke and turn black and let all the smoke out. And then it wouldn't work anymore.
That was my next question, is tell me about the smoke coming out.
Okay, the smoke coming out. Okay, smoke is a magical thing that is inside every electronic component. Okay, so this is a resistor, and one of the things that it's made from is known as smoke. All right. So what happens is when you let the smoke out, it doesn't work anymore because you've let the magic stuff out of it. Was that a good answer?
An acquaintance of mine owns an automobile repair shop, and this is some part of the lecture that he gives to everyone of the new guys.
Yep.
As long as you're putting wires together very carefully, the smoke won't get out.
That's right. Don't want the smoke to exit, because once the smoke leaves, the component, the magic is gone and it won't work anymore.
So the smoke is hiding in the wires and in the resistors and in all the pieces in the line.
Yep. It's the critical thing that allows the thing to work in the first place.
Okay.
And once you let the smoke out, it can't work anymore because the magic is gone.
Now we're getting down to my level of understanding.
Yeah, one of my friends here has a kilowatt antenna tuner, which is basically internally, we're going to get to this. It looks like this. So it's got an inductor and a capacitor and another inductor. And he fired it up once. And what happened was, so this was like a metal box that looked like this sitting on his desktop. Right? And it had a cable going in and another cable in the back going out to the antenna. and it was, you know, doing its magic. And he fired up his amplifier at 1,000 watts, which should be just fine. And as soon as he keyed it up, what happened was it had smoke and flames coming out of both sides. And it's like, oh, that, you know, that's not good. It's another reason I don't like high power. And what happened was that he had actually developed a short circuit in his coax. Something bad had happened up in the coax, and he was basically running 1,000 watts through the cable and into this short circuit. Well, 1,000 watts wasn't going to get dissipated here. It had to show up somewhere. So that 1,000 watts turned into large clouds of, you know, releasing smoke and flames out the sides of the box.
So it went up the wire from the box, ran into the
short circuit,
to the log jam, and the wire turned around and came back down the other side of the wire and fried the box.
Yep.
Okay, thanks.
Yep. Got to go somewhere. And it did. Okay. So now we're going to cover something called AC, right? Because we need to understand AC before we start talking about inductors and capacitors. Okay, AC. So this is AC. Huh, what does that look like?
Sine wave.
A sine wave, okay. That is, now we could also do AC. AC just basically means that it's alternating from positive to negative. That is also AC, but it's really ugly. This is also AC because it's alternating plus minus. Now, we don't typically use that. We don't typically make that. And the reason we don't typically make that is because if you look at the math behind it, really what a pure frequency looks like is a sine wave. So we typically try to use pure sine waves. Now, the other thing that's cool about this is that let's say that you have a water wheel. It's being run and spun around by water coming down. If that water wheel is connected to a generator, well, the generator is turning, and inside that generator is a bunch of coils and permanent magnets, and those are connected to wires. Things that are going around in circles usually make a pattern that looks like a sine wave. So coming out of the generating station, that's where we even start with our sine waves. If we have a classic generating station. Motors, they use sine waves as well. So we are typically dealing with sine waves when we're talking about AC. So our house current is 120 volts RMS at 60 hertz. Okay, so if it's at 60 hertz, how many times per second is it making this cycle?
I'll guess 60.
60 hertz. Yeah, 60 times per second. Now, the other tricky thing here is that 120 volts DC would actually be right about here. This is 120 volts DC. Well, what do you notice about the peaks on that AC circuit, on that AC?
They appear to be higher than what
They
the
are
DC.
higher, yeah. And in fact, this is about 170 volts, and this is about negative 170 volts. Well, the key to this lies in this
Wait a
thing
minute.
called, yeah.
What? This is 120 volts of AC is
Yep.
actually overachieving and becoming 170 volts on the top side.
Nope.
And overachieving to 170 negative.
Well, the key lies in this. See, this says 120 volts RMS.
What's an RMS?
RMS is root mean square. Okay, this is actually really important, although I don't know if you need it for this test. But RMS is root mean square, which basically means that you take what you're looking at is the ability of a signal to produce a certain amount of power. Now, if we were to look at Ohm's law and we look at the DC, we have two things. We have P is equal to I times E, and E is equal to I times R. Does everybody agree with that? We have two parts of Ohm's law, right? Okay, so what we can do is we can substitute, we can move this around and make this I is equal to E divided by R. And we can take the I and substitute it there, and we get P is equal to E squared divided by R. So what we get is that the power is proportional to the square of the voltage, right? Because we don't really know what the resistance is, but we do know that the power is proportional to the square of the voltage. How much power are we making when the voltage is 0?
I'll go out on a limb and say 0.
0. So if we peaked at 120 volts, we would have these areas where we're making no power that we wouldn't be able to compensate for. So what we're trying to do is create an AC signal that matches the power delivering capability of this 120 volts DC. In order to do that, we actually have to peak at 170 volts, because for that period of the time, we can actually make more than the 120 volts because we have a much higher voltage. And that's actually, it actually comes from doing the calculus. You do an integral over one full period of the square root of the square root of the integral of the thing squared. And what you end up with is that you have to peak at 170 volts or so, which is actually square root of 2 times 120, to get the same power. And that is why, if we look at the peak voltage of an AC 120 volt circuit, let's say that you had an oscilloscope and you plugged it into your wall and you looked at the power coming into your house, you would actually see it peaking at plus or minus 170 volts. So yeah, you really do have that. If you take a voltmeter, which a lot of us have done, and we plug it into the wall, what we'll do is we'll have an AC RMS voltmeter. We'll typically have this thing called an AC RMS voltmeter. And we plug it into the wall, and let's just pull up a very, very basic one. We'll go to Harbor Freight. And the reason we'll go there is because it's really cheap. Sometimes they'll even give them away for free. Okay, so here's your standard $7 Harbor Freight voltmeter. Ooh, don't miss the coupon. Okay, so on this it says, notice it says AC volts, right? And that is actually an RMS reading voltmeter. So there's some math being done on the inside, which says I'm going to measure the peak and the negative peak, and I'm going to take those two and see what they are, and I'm going to use those, and this is plus 170, and this is minus 170, and I'm going to say, okay, what's my actual peak? And I'm going to divide that by the square root of 2. And that's the number I'm going to put on the screen. It assumes that it's a sine wave coming in. And that's known as an RMS reading voltmeter. So that actually has some very profound results too. Let's say that you had this thing and you decided that you were getting noise on the signal coming in. And so here's your AC circuit. Man, look at that. You had this AC circuit, right? That's an AC power supply. And it's coming into your something or other. You say, you know what? I think I've got some noise on this. And what I want to do is I want to filter something. And I want to use a filter here to get rid of any DC components. And so I put an inductor here and a capacitor here. and here's my stereo. Right? So I built a line filter for it. And this is 120 volts AC. And my inductor is rated at 135 volts. What will happen to my inductor?
The inductor is bigger than the 120, so it should.
Yeah, no, it's not. Because what's the actual voltage in my AC power?
Oh, whoops, it's 170, so it's going to get fried by 35 volts.
Yep. That inductor will not survive. I can say the same thing about the capacitor. Like if this was a 150 volt capacitor, that's not going to survive either. Even though 120 is less than that, it's 120 volts AC, and you have to know what's actually making up your power.
So the theory in the diagram is that the electricity is coming out of the wall, and it's going over to the right, and some part of the electricity is going through the double lines on the top.
We're gonna get to those. We're gonna get to why you would do that. That's actually next.
Okay.
Okay, so let me trash this. Okay, so we've now done alternating current. Alternating current alternates between positive and negative directions, positive and negative sign. The number of times per second that AC makes a complete cycle is known as its frequency. For our standard power, that's 60 hertz, unless you're in Europe or Japan, in which case it's 50 hertz. Units of electrical resistance are ohms. Resistance blocks. Resistance is the ability to fight DC. Now, there's also something called impedance. Impedance is something's ability to fight back against AC current, and that's actually going to be really important in about 30 seconds. Okay, let's cover conductors and insulators. Everything that we know is made of a nucleus and electrons flying around in different orbits and different energy levels. As they're flying around, sometimes their electrons are very weakly held, sometimes their electrons are very tightly held. Something that's weakly held, if an electron drifts into the field, another one will very easily come drifting back out. If they can be moved very easily, this is known as a conductor. It conducts electricity. If you find something that when an electron comes nearby, it basically just gets turned around and pushed somewhere else, and nothing comes out the other side, that is an insulator. Okay, so what are some common conductors?
Metals.
What kind of metals in particular?
Copper.
Copper's great.
Water is a conductor.
Not water. Water itself is a terrible conductor.
Some of the stuff in water can increase conduction.
Salt water is a great conductor. If it has, because salt breaks up into sodium and chloride ions. Salt water is a great conductor. Deionized water is a terrible conductor.
Gold and silver.
Gold and silver are really good. Aluminum is a great conductor. So why don't we use aluminum? We use it for antennas because it's lightweight. Why don't we use aluminum for other things?
Won't handle the power.
Oh, yeah, it does.
Does it?
Yeah, aluminum's great, and it's lightweight. It handles a lot of power.
So work hardened?
Nope. You can make aluminum wire just fine. Why don't we use more of it? Anyone ever worked aluminum?
Yes.
What happens to aluminum?
It's very, very soft.
Well, it depends. Depends on the alloy. But what happens to aluminum when you leave it outside?
It decays. That's why we have to use special treatments on it.
Yep. What happens to it? It's very reactive. It oxidizes. And unlike a lot of other things, aluminum oxide is a very poor conductor. So what ends up happening is you end up with this blackish surface, blackish gray of a very poor conductor. And if you try to take two aluminum pieces together, you have to treat them very carefully to make sure that they don't oxidize. Otherwise, you'll set your house on fire. If you want to look it up, that happened a lot in central New Jersey. Whole bunch of houses burned down for that reason. They used aluminum wire, but they didn't really know how to properly treat it. So whenever they made a junction and they twisted it together and used a wire nut, it wasn't sealed in like oil or anything, and it oxidized, and then you ended up with a high temperature junction that burned the house down.
So once again, they let the smoke out.
They let the smoke out. Yep. Okay. A good electrical insulator. Name some good electrical insulators.
Glass.
Glass. Other ones?
Ceramic.
Plastic.
Ceramics, plastic,
Rubber.
Fiberglass.
fiberglass, air, paper. Paper's a really good insulator.
Huh.
Wood, if it's not too wet. Wood's a really good insulator. I actually made a wood insulator antenna once. Okay, Ohm's law, we've done that. E equals I times R.
So I have a quick question.
Yes.
Okay, so wet wood is a good conductor, but yet water is a bad.
Well, because it's not going to be, the water is going to have dissolved all kinds of things in it.
Okay.
If it's in the water.
Drop a toaster in a bathtub.
Yeah, you don't want to do that. I mean,
Thank you, Jeff.
You could if it was deionized water, but we don't typically have deionized water around the house.
Okay.
So
the James Bond movies are not accurate?
Yeah, I think it would still work. I think it would still happen. I wouldn't recommend it. But actually, therein brings an interesting point. If you're building something, and let's say that you have your plug and you have your plus, or we'll call it your line and your neutral, and then your ground. And that goes through, and you have your line and your neutral and your ground, and those come out to actually typically ungrounded. Let's connect that to here. And this is your hair dryer. All right. So this is a GFCI. Anyone ever had one of these trip annoyingly in their bathroom? I'm sure you have. It's a little thing that says test and reset on it.
Mhm.
Okay. So this is a ground fault circuit interrupter. Well, this is typically used for things that are, as they would say, ungrounded. All right. And so like a lot of hair dryers only have two plugs. So what this does is it measures the current going this way, and it measures the current going this way. Well, considering there are only two wires hooked up to it, they'd better be the same current, right? Because if it's not the same current, there's probably some leakage to ground, which is the earth or your hot water or your tub. So it measures the two different currents right here. And if they're not the same, it forces open the circuit right here. And that's a ground fault circuit interrupter. And they save lives. Okay. So we are almost at lunchtime. And so what we're going to do is now we're going to draw another circuit. And you can take a look at these resistors and notice these are parallel lines to each other. Call them R1 and R2. These lines are parallel. These resistors are known as being in parallel. Now, this is what's known as a node, that spot that I just drew, which is right at the intersection. If I have current here, I have I1 going through here and I2 going through here. The sum of all the currents going into a node has to be equal to the sum of all the currents going out of it, which basically means that the I total is equal to I1 plus I2. Now, interestingly, the great thing about this is that current follows the path of least resistance. So if I were to take this and make this an open circuit, what would happen to the current that's going through that first resistor? It would be unchanged, right? Both of the devices, both of the resistors experience the same voltage. And this is known as ground. That's our 0 volt reference. If I were to take this light bulb completely out of it, the rest of the lights still work, right? Okay, now if I were to draw this as a series circuit, that basically looks like this, where as you travel through here, you get to R1 and then you get to R2. So both of these have to experience the same current. That's known as a series circuit, kind of like watching a show. You watch them one after the other. That's known as a series circuit.
These are the lights on the Christmas tree where the
These are Christmas tree lights. This is why we don't wire our house that way. Because if we did, as soon as we had something open up here, we'd have a broken circuit and all of the lights in our house would go out. Now, the other thing about this is if we were to replace this with a short circuit, the current would be higher, and then this light would actually be brighter than you expected. And every light that you added would change the brightness of all the other lights. And nobody wants that. So these devices experience the same current, but their voltages will be different. If I were to draw a parallel circuit again, they experience the same voltage, but their currents would be different. Their currents would actually be defined by the size of their resistances. So one is known as a voltage divider and one is known as a current divider. This would be a current divider. Okay. Okay, so we're just going to quickly do math for electronics and conversion of units. And I think we'll do decibels and then we'll go get lunch. Okay, so here's the math. Okay, everybody, if you can, I'll show it also. We're going to pop this up on the screen. This is on the 18th page, I believe. So notice all these prefixes: giga, mega, kilo, and then units, milli, micro, nano, and pico. So is everybody comfortable with scientific notation? And it's okay to say, no, I'd like you to go over it. Does anyone want me to go over scientific notation?
Since I'm still worried about smoking the wire, I'll ask for all the help I can get.
Okay, here we go. All right, so scientific notation. So everything is based on the number 10. Number 10 is a great number, right? Because what is 10 times 10? It's 100, okay? How many 10s were there multiplied together? There were 2. How many zeros do we get over here?
2.
We get 2. Okay, so if we have 10 times 10 times 10, we get 1,000. We have 3 of them, and we get 3 zeros. Okay, now let's say that we had, I'm not going to draw it out, but let's say we had 10 times 10, and there were 6 of these. How many zeros would we expect to be on this side?
6.
6. Okay, now another way to do this notation, this is the scientific notation, we have 10 is 10 to the 6th power, which is the same as 10 times 10 times 10 times 10 times 10 times 10. Okay, so by convention also, what is, let me just clear this, 1/10 times 1/10?
100.
1/100th. How many zeros do you see in the denominator?
2.
2. We have 2 there, and we have 2 zeros in the denominator. If we made it 1/10 again, we now have 3, right? Okay, now we can also say that this is 0.001, which it is. So if we start at 1, 1, 2, 3. So we had to move the decimal point starting at 1, 3 places to the left. By convention, 1/10 is 10 to the minus 1 power. If we have 3 of them, we have 10 to the minus 3rd. This is also 10 to the minus 3rd, and we've also moved the decimal point 3 spaces to the left. So that's really how all of the scientific notation works. Everything's based on the number 10. And the real power of scientific notation is the ability to eliminate having to show all of these pesky zeros that don't really, that they're basically placeholders and don't give us any real information. This is particularly useful when we start dealing with something like 1.2 times 10 to the 16th power. Well, okay. So that would be 1.2 times 1,000,000,000,000,000,000,000,000,000,000. Okay. Is there really any benefit to having to write out all those O's? Or 1.20000 or 1,2000000. Is there really any benefit to that? I don't think so. The interesting part is the fact that it's 1.2, right? And so to basically to say we've now absorbed all those zeros. So the next part of this is that we can now say if we have, let's say, 1.5 amps, and we want to convert this to milliamps, the milli is 0.001. That's the definition of milli. So we want to know how many 0.001 amps are there in 1.5 amps. Well, okay. So this times 0.001 is equal to 1.5. Obviously, that's 1,500. So 1.5 amps is 1,500 milliamps. So what it allows us to do is take things that are not particularly helpful to us, like all those zeros, and make them disappear. So let's say that we have a frequency of 7248000 hertz. All right. Again, those zeros don't really mean anything to us, right? They're just placeholders. How many zeros are there that we could get rid of?
3.
3. What is 10 to the 3rd power, also known as?
Mega?
Nope.
Kilo.
Kilo. So we could now take that and say it's 7248 kilohertz. All right. Now, if we wanted to, we could also take that decimal point and slide it over 1, 2, 3 and put the new decimal point there. And when we did that, we'd have to take another factor of 1,000 out. And what does another 1,000 mean? We could write it as 7248 kilohertz. Right? Well, that doesn't really mean a whole lot to us. So what is 1,000 times 1,000?
It's a million.
A million. And what's
Megahertz.
another? That's a million. That's a megahertz. And that's 7.248 megahertz. So that's how we do conversions there. The other way we can do this is to go from to do very small things. So let's say that we have a capacitor that's 22 picofarads. Now, let's go with microfarads. I like microfarads. Okay, a farad is a huge capacitor. So micro means 10 to the minus 6th or 0.000001. That's the definition of micro. Okay, so we can write this out and say 22 times 0.000001 farads, or start with 22 and we go 1, 2, 3, 4, 5, 6, and just fill in zeros. So it's 0.000022 farads. Now, if we had something that was, let's say, 22 picofarads, okay, so that's 22 times pico is 10 to the minus 12th, so 0.0000000001 farads. So that would be 22 and slide it over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, you see why we don't bother to do that? That's why scientific notation and using all those zeros is very helpful. And so there are lots of practice questions with regard to that. Okay, so now what we're going to do is decibels. Okay. So now that we've sort of established the concept of powers, for instance, 10 to the 6th is equal to 10 times 10 times 10 times 10 times 10 times 10, which means we basically multiplied 10 by itself 6 times. A decibel is a way of expressing something using the exponent itself. Right? And in fact, this is known as a bell, not a decibel. What's in that place is known as a bell. So something that is 10 to the 6th could be known as, when being compared to 1, it has an increase of 6 bells. And the way that we write this is bell is equal to 2 log base 10 of something over something else. So let's say that we have a starting point of 1. That's our original signal. That's our reference signal. So P1 is equal to 1 thing. And P2 is equal to 1,000,000. Okay, so we're going to plug these in. We're basically looking to see how much bigger something is than something else. So log base 10 of 1,000,000 divided by 1 is log base 10 of 10 to the 6th power. So now log basically says, to what power would 10 have to be raised to get that thing? So see that number 6 right there? That would be 6 bells. So if, for instance, I change that to bells equals log base 10 of, let's say, 1,000, because we had P2 is equal to 1,000 and P1 is equal to 1. Okay, so 10 to the what power is 1,000? Third. So that would be, this is just 3. Okay, well, it turns out that Alexander Graham Bell was off by a factor of 10 in usefulness area. So really, what they figured out was, well, 3, we ended up with things like 3.6, and nobody wants a decimal point there. So let's make it something called a decibel, which is a tenth. How many tenths are there? So now what we ended up with is 10 log base 10. There's that factor of 10 out front to multiply it by 10 by that. So now it's 10 times that same 3 is 30 decibels. So basically what that means now is that an increase of 30 decibels is 1,000 times increase. An increase of 10 decibels is a 10 times increase. Another increase of 10 decibels is a 10 times increase. And another increase is a 10 times increase. 10 times 10 times 10 is 1,000. And these get added together, and that becomes 30 dB. So that's where decibels are very useful. Okay, now, practically speaking, there are only 2 things you really need to know with regard to decibels. 10 times is exactly equal to 10 decibels. And 1/10 is equal to negative 10 decibels, because by convention, this is 10 to the minus 1 power. And there's that minus 1, and then you multiply by 10. So, okay, so 10 times is 10 decibels. The other thing that's helpful is that the 2 times is equal to approximately 3 dB. And 1/2 is equal to, somebody give this to me. Because we're getting smaller. Those are the only things you need to know. Because you can approximate virtually everything by factors of 2 and factors of 10. The reason I say that is because let's say that somebody told us we had a gain of, let's say, 16 dB. Well, we can separate that out. That is 10 plus 3 plus 3. Okay? 10 decibels gives us how many times?
10.
10 times. 3 decibels gives us?
Double times 2.
Yep. And 3 decibels again? Another 2. So what's 10 times 2 times 2? That's 40 times. So what that means is if we have a 1 watt transmitter transmitting through an antenna with 16 dB, that is the equivalent of how much power?
Is that 40 watts coming out
40
the
watts.
end of the antenna?
40 watts. That's exactly right. That also
1
tells
watt
us
coming out of the radio.
Yep.
And
The
somehow
equivalent of 40 watts coming out in that direction. And what we've done in order to achieve that is instead of transmitting in all directions, we've taken all the stuff from these other directions that we don't care about and redirected them into this path. So basically what we've done is we've taken our antenna, and by building a better antenna, we've eliminated a lot of this unnecessary transmission of energy and taken it and pushed it all in this direction so that it has that new equivalent. This is why when you go and you see like a sending station, like air quality kind of station, it'll be like, here's your station, and up top, there'll be an antenna that looks like this along the side of the road. Has anyone ever seen that? And usually this is like a foot long. And that's because somewhere on the other end, there's a receiving antenna that is listening and only talking to that station, that is receiving telemetry information on air quality or number of cars or something like that. So this will be like a 1 watt transmitter with like 20 decibels of gain. And 20 decibels is 10 plus 10, and that's 10 times, and that's 10 times, is 100 times. So the effective radiated power in that direction is 100 watts. Which means that through that path, which might be a few miles long, there's enough signal, even with just a 1 watt transmitter, to actually get the signal through. Another one we do is, for instance, anyone ever heard of something called a ubiquity router?
Yes.
Okay, so here's our 400 milliwatt ubiquity router. Okay, and we take this and we convert this to be a ham radio, which we do. We take this router and we connect it to a dish antenna, which has a forward gain of 30 decibels. Okay, what is 30 decibels? Who's doing that math, Joanne? Oh, you're muted.
20?
Nope. What's the 30 decibels? 30 decibels is 10 plus 10 plus 10. Every time we go up by every time we have 10 decibels, we multiply by.
Oh,
So we're
1,000.
multiplying 400 times 30 to get 12,000.
No, not 30. This is decibels. We really want power multiplication. So we have to convert the decibels into power. So we have 1,000 times as much power in the forward direction. So what's 400 milliwatts times 1,000 watt times 1,000 times?
400 watts.
400 watts. Effectively, in the forward direction, we have the equivalent of 400 watts, a 400-watt transmitter. It's only 400 milliwatts still, but it's the same effective power as if we were transmitting with a 400-watt transmitter in all directions. So basically what that means is we really kind of want to avoid pointing it at people. Now, here's the next one. Let's say that instead of a ubiquity router, we have a transmitter that's 1,500 watts, which we are legally allowed to do. And we're going to aim this signal at the moon because we want to do moon bounce. And we still have a 30 dB antenna. So how much power are we equivalently sending out?
1,500 kilowatts.
Yeah. In other words, 1,500 kW, which is 1.5 megawatts ERP. So anybody have any question as to why you need to get a license? We are legally allowed to run that much power, and we can put it through any damn antenna we feel like. Which means that if we were to point this at somebody, what would happen?
I think you'd be frying them pretty fast.
Pretty fast, yeah. This is a higher power than a microwave oven. And if you point this directly at somebody, you can do some serious damage. So that is why we study for and get licenses, because we are licensed to use this much power with these kinds of antennas, and we have to understand the damage that it can cause.
I have a son who's in the Navy. He's a radar geek. And he wants me to understand that their radars are so powerful that they cannot fire them up close to land.
Oh,
They
yeah.
have to get out into the ocean before they can run them up to max power.
Absolutely.
They'll be melting cities on the shoreline.
And kill a bird flying right through the air. Yeah, you can do a lot of damage really fast. Okay, let's just take a look and see where we are. We're through decibels, and we are into capacitors and inductors. We'll do capacitors and inductors right after lunch, I think. Just out of curiosity, have people been taking practice exams and going through the question pool?
Yep.
Yes.
Okay, I think what in my experience, it really helps as far as your success. Okay, has everyone scheduled an exam?
Yes.
How many? Okay, so how many? I haven't looked to see how many people are on it. If you want to take a test, we're giving an exam tomorrow afternoon, right after the class, like 1 o'clock in the afternoon Pacific time. And it's done remotely. You basically need your computer and with a webcam, and a phone or an iPad with a second cam. So your main device is the computer that you take your exam on, and the second device is for kind of observing the room, because it takes 3 examiners to give an exam. And one of the caveats of doing it remotely is that since it's only you and 3 examiners, the examiners aren't physically there. We actually, believe it or not, have seen people try to cheat. So we have to do that to keep people from cheating. Okay. Any other questions before lunch?
How long is our lunch break?
Half hour. You
Would
guys,
you take the exam for me?
What?
Would you take the exam for me?
I have done that plenty of times. So tell me what you're worried about.
Oh, I'm just not ready. I've done practice, and now I'm taking this course, and then I'm gonna go back and study the book some more, and then I'll take my exam.
So I recommend doing the studying one section at a time.
Mm-hmm.
And because I know some people just try to jump into exams. And the thing is that you can take 100 exams and still not see some questions. If you do it one section at a time, you get to focus on one topic. So, and get used to it before you move on. That and the fact that don't worry too much. If you're taking practice exams, that if you're at the point where you're averaging about 85%, you're gonna pass. You only need a 74 to pass.
Mhm.
All right. Anything else before lunch? I don't hear anything. Lots of crickets. Okay. Think of more questions.
Okay.
All right.
I'll
Thank
see
you.
you guys in 30 minutes.
All right. Thank
All
you.
right. Yep.
Thank you.
All right. Bye.
All right. Well, I'm back a few minutes early to answer questions.
I have a question for you.
Okay.
Missed the first part of the series just because of some technical difficulties here. I know this is being recorded. Will we have access to that later?
That's the plan.
Thank you very much.
As soon as I close it, I should be able to convert it within an hour or two. So it's a big file, but yeah, it should work.
Perfect. I appreciate it.
Mm-hmm.
Are we gonna go over some of the like acronyms and stuff later, like the race, like RACES, and like there's a bunch of questions about those I guess like emergency service type clubs.
Mhm.
And I'm wondering if you're gonna go over most of that, or should we just do some research on our own?
If it's in the book, we're going to cover it.
Oh, okay,
We literally cover everything.
great, thank you.
Mhm.
Can I ask you about the Ohm's law?
Mm-hmm.
I've got a little bit of knowledge of this, but I don't understand what's the difference between, I understand what resistance is, but what's the difference between the voltage and the current?
Okay. What's another term for voltage?
Well, batteries are in volts, so electricity, energy.
EMF, electromotive force.
Okay.
Well, I mean, if you break that down, it's the electric ability to move things.
Okay.
And it's the force behind it. It's the push.
Okay, it's the push.
And current is the result.
Yeah, I always think about it, if you correlate it to plumbing, right? It's the pressure pushing the water through a pipe, and the pipe is the current, or the
Yeah. The water going through the pipe is the current. And if you
Yeah.
open the valve,
Yeah.
you reduce the resistance.
Okay, so the voltage is more like the generation of
That's
it.
exactly what it is. Voltage is voltage is basically how much push there is available.
Push, and then the current is kind of like a PSI pressure.
No.
No.
Current is the actual flow. Like if I were to draw, yeah, like I mean that's the definition. Actually, that's the definition of current. If I were to draw like a reservoir, right, and I've got a butterfly valve here.
Mm-hmm.
Well, I mean here's the reservoir. This is the voltage. And here's the butterfly valve. The butterfly valve is closed, so it's giving me a really high resistance, or infinite, really.
Okay.
Right. As soon as I open it, I get, a lot of flow. If I have a little bit of resistance, let's say I have a valve that's partially open,
Mm-hmm.
that's a little resistance. That's going to reduce the flow. If I take the reservoir and I raise it, put it on top of a mountain, I have more potential available.
Okay.
I have a higher voltage.
Hmm.
And I mean, current is literally a measure of the amount of stuff flowing through a point.
Okay.
I mean, that's what current is.
Which is why we use the multimeter to find out whether we've got a bad wire or bad battery.
Well, yeah. I mean,
when we measure at the battery, we've got voltage. And then if we measure the wire on the other end, if we've got a loss, we could tell maybe we've got a bad wire.
Mm-hmm.
Okay. What about the difference between the voltage and the watts?
They're totally different.
Okay.
What is voltage? One more time. What is voltage?
The push of the flow of energy or electrons.
It's the push available.
Push available. Okay.
And what is wattage? I mean, what is the definition of a watt? Is a joule per second, and a joule is a unit of energy. So a watt is a power flow in energy per second.
Okay.
And the relationship is that power in watts is equal to E times I, which is volts times amps, or it's I squared over R, or sorry, I squared R is equal to V squared over R. However you want to define it.
Okay.
So either one of those.
Okay.
Yeah, I mean, because a joule is a unit of energy.
Okay, and changing this around just a little bit. If I'm in Florida and I have a real humid conditions and there's a lot of humidity, there's a lot of water particles, do I have to transmit more power?
No.
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 Why?
Well, I mean,
it's making it through it.
It's going to be okay.
Okay.
I mean, on what? Well, the other question is on what frequency.
Well, my guess was that if I'm in Florida or if I'm in the desert, that you'd be transmitting maybe different power.
I wouldn't. I mean, it depends on the frequency. If you know, let's say you're on microwaves, sure.
Okay.
But you're not going to be on microwaves.
No, no.
So no, it makes no difference.
Okay.
Yeah, it really comes down to the absorption at a given frequency. And I mean, water is, you know, you look at water and you have an O and two hydrogens. Actually, they're about like there. So you have 109.5 degree angle. I mean, that's just the resonant frequency of a water molecule. That's about 2400 megahertz. And that's why we have microwave ovens that operate at 2400 megahertz.
Which makes me think, now I understand why the submarine has to surface to transmit and receive, because the water is like a resistor. It's blocking the.
I mean,
on some frequencies, maybe
on some frequencies.
Okay.
I mean, but actually, that's why a lot of submarines will transmit at VLF, very low frequencies, because they propagate through the earth and through the water better than the higher frequencies.
Ah, okay.
And, you know, there's no reason you can't trail along, you know, an antenna in the water. That works.
Right. Okay, thanks.
All right, everybody ready? Time to rock and roll. We are on to okay, electronic circuits and components. Okay, so this is on page 23 in the PDF. Okay, what electrical component opposes the flow of current in a DC circuit? That's known as a resistor. A special kind of resistor is called a potentiometer, and we will find these often in, let's say, a stereo system, where you want to take a resistor and vary the value. So this might be a 0 to 50K potentiometer. and you have a knob like on the front of it that goes all the way counterclockwise and all the way clockwise. And that allows you to change the value. The electrical parameter that's controlled by a potentiometer is known as resistance, which we just said. Okay, now we're into capacitors. Okay, a capacitor used to be known as a condenser. I don't know exactly why, but a capacitor is basically two metal plates separated by a gap. That's all a capacitor is. What it allows to happen is, if I hook this up to a battery, for instance, it allows the pluses to accumulate here and the negatives to accumulate here. And since they can't, unless the voltage is higher, they can't jump that gap, which basically means it's now storing energy in an electric field. Those charges are trying to pull each other closer, and the physical restraint in the capacitor is keeping them from doing so. So essentially what that is a storage of energy, energy in an electric field, because every pair of a plus and a minus, they have a pull toward each other. And if you keep them apart, that's known as the electric field. They try to pull each other toward themselves. Okay. The amount of ability to store an electric field is known as capacitance. The unit of capacitance is the farad. Okay, the next one is an inductor. Okay, so we're going to start with a coil of wire. We're really going to start with a bare wire. And again, we're going to have current flowing this way. And if we use our right-hand rule, our magnetic field goes like that. Whoop, yep, above, and it's kind of hard to explain. But basically, if you put your thumb up, that's the direction of current flow. Magnetic field wraps around. So basically, if we now look at this coil, and we have a current flowing through the coil, we have a magnetic field that would go this way, and the individual loops inside the coil would tend to cancel each other out, and we would get a magnetic field that kind of looks like this. This thing is actually known as a solenoid, and it's the basis for electromagnets. You may have built one at one point using a nail and a coil of wire around it, and use this to pick up paper clips if you hooked it up to a battery. Elementary school science project. The ability to store energy in a magnetic field is known as inductance. The unit of measure is the Henry. Okay, now a battery is a device that stores electrical energy in a chemical form. And so there are numerous different chemistries that allow us to do this. Some are permanently charged. In other words, it's a one-time thing. You can't go backwards. Those are known as primary batteries, such as your classic heavy-duty battery, the carbon zinc battery. Alkaline batteries are typically not rechargeable either, nor are lithium metal batteries, which are the little button cells that you find in watches and calculators and stuff. Some of the battery chemistries, like a lithium ion, lead acid, which is in your car, nickel metal hydride, NiCad, those are rechargeable, which means that it's a reversible chemistry internally. Okay, next. Diode. Well, we were talking about components that it didn't really matter before which direction you hook them up. A diode, it does matter. A diode is a special device, notice it has an arrow, that allows current only to flow in the direction of the arrow. So there are two poles. One is known as the anode and the cathode. This is the anode. This is the cathode. If you buy a diode, it will typically look like this, with a stripe on the cathode end, indicating that's the negative side. This is the plus, and that's the minus. And current only flows in one direction through a diode. What is true about forward drop in a diode? Some diodes have a lower forward drop than others. Okay, so a silicon diode is about 0.7 volts. So if I hook this up to a battery, I will see as it flows forward 0.7 of a volt disappears. Germanium diode is about 0.3 volts. So that doesn't necessarily mean that one is better than the other. Actually, silicon diodes are very often much more robust than germanium diodes. But forward drop varies by the diode type. A light emitting diode, we have them on our phones. They look like this. Instead of just allowing current to flow in one direction, a light emitting diode will look like this. The light that comes out of it is represented by those two arrows. So forward current causes an LED to turn on. An LED is very often used as an indicator. A very cheap red LED will last virtually forever and indicate that your power supply is turned on. Okay, so now what we're going to do, now that we mentioned diodes, we're going to actually talk about what's inside a diode. Okay, so diodes are made of something called silicon, which is element number 14. And if you look at the periodic table, you'll find that in the row that silicon is located, 11 to 18. Well, silicon falls right there, about in the middle. And the electron shell of silicon, the outer shell has 4 electrons. And it can be somewhere between 0 and 8. So it's half full. Depending on whether it's more full or less full, that makes it it gives it a higher or lower affinity to electrons. A metal will have 1 extra electron. A non-metal, such as chlorine, will have, it'll be missing an electron. Silicon is sort of in between. Silicon's not a metal or a non-metal. It's known as a semiconductor. And that's because it can sort of play both sides of the fence. So silicon by itself is not good at conducting things. However, if we take silicon and we dope the material with either boron or phosphorus, that can turn it from an intrinsic material, which is known as I, into a P or an N material. If it's N, it has slightly more in the way of negatives available. If it has a P, that means it has slightly more in the way of positives available. So depending on how we dope the silicon, that makes it a little better or a little worse at transferring electrons in one direction. So what that really does is we now have this thing called a p-n junction. This is actually drawn like that. So what that means is if we put a plus here and a minus here, it actually conducts in that direction. And we need a little bit of extra voltage to get the electrons moving over the junction. But once we're there, everything's fine. It works in the forward direction. Now, we could also make an NP diode, but there's really no point to that because an NP diode would just be reversed. We can do that. I mean, it looks like this. Right? But why would we want to do that? Because it's just another picture of the exact same thing, just turned backwards. So that's kind of dumb. We would never really do that. However, what we can do is we can take 2 diodes and put them back to back. We can make a P and an N and an N and a P. Or we could do an N and a P and a P and an N like that. Huh. Okay, well, these are really the same. So this is an NPN like that. And this is a PNP like that. And this actually has some very, very important uses. This is known as a bipolar junction transistor, or a BJT. It's a 3-terminal device. So it's not just 2 like a resistor or a capacitor. It has 3. And what makes it special is that if I, for instance, were to draw this the way a transistor is drawn, we're going to draw an NPN. Has 3 terminals. This is the base, this is the collector, this is the emitter. If this, because this is a PN junction, if I forward bias this and put a voltage on here that's 0.7 volts or higher, what will happen is that this channel, if you want to think of it, this back channel, which is isolated from the front channel in a way, becomes wide open. And whereas I can handle, I can put a very small voltage and current through here, in response, I get an immense amount of current available to pass through there. Well, if I, for instance, run this wide open, I run the backside wide open. If I run the front side a little bit open, the base, I get the backside a little bit open, but it's typically a lot bigger. So what this allows me to do is develop a larger copy of what's going in at the base. If, let's say, this is a low signal of somebody's voice, what I can get is a copy of that that's an exact or very close to exact copy. Why would I want to make a bigger copy of something small? Anyone?
Amplifier.
That would be known as an amplifier. That has a lot of uses, actually. So that is an amplifier. This is a very basic form of an amplifier. Now, in reality, you typically wouldn't run this full out. You would typically take part of this circuit and feed it back and do some negative, you would do some negative feedback on it so that it didn't go out of control, so that it was a little less prone to just the whims of the transistor, how each particular one is built. But what this allows you to do is make a big copy of something small. The other thing that a transistor does is the fact that it's not exactly linear. So if I have something that looks like the input over here and the output over here, as my input goes up, my output gets to a point where the transistor turns on. And then I get to a certain point where no matter how much more I put in, I can't get any more out of it. So basically this range right here, where it looks like there's a straight line or very close to a straight line, is known as the linear region of the transistor. This is where, if we want a nice clean amplifier, we actually run the thing. So we have our 0 point, and that translates to our 0 point over here, and we just move our signal back and forth over here, and it produces a bigger copy over in this range. So this is known as the saturation point, and this is known as the cutoff point, where it doesn't work anymore. If there are times when we don't care if a signal is dirty or not. If we're using something that's like a computer, we just want it to be on or off, right? We will typically run a computer that's using transistors in saturation. In other words, we just basically say, we don't care if it's linear or not. We actually just care about this point right here. We just want it on to be on. And down here, we'll use this point right here where off is off and forget all this other linear stuff. So transistors are they're good as switches for switching other loads, like being able to turn on a bank of really big lights using a small signal to turn it on. That way in your control panel, you don't have 600 volts in there. You can put it somewhere else. They can also be used for linear amplification, which is what you do in a guitar amplifier, or what you do in an amplifier for a microphone, or an amplifier inside a radio, where it really does matter that your signal comes out as close to the one that went in as possible. Okay, let's see. So in saturation and cutoff, a transistor is used as an electronic switch. And a device's ability to amplify a signal, that's known as gain. And what units do you think you'd measure that gain in? We talked about it just before lunch.
Decibels.
Decibels. So if you have an amplifier with a gain of, let's say, 13 dB, all right, remember how to break that up? 10 plus 3. And 10 decibels is how many times, everyone? And 3 decibels is? Oh, I feel like I'm losing you guys.
2.
2. And 10 times 2 is? 20 times. So basically, I have a 20 times amplifier. If I had an amplifier that had a gain of 23 dB, that would be 10 plus 10 plus 3 is 10 times 10 plus 10 times 10 times 2. That would actually be a 200 times amplifier. So I would have 200 times bigger signal coming out than going in. And that's why we use decibels. Decibels are a convenient way of keeping track of those numbers. Are there any questions there before I go on? It's a good time to ask.
Nope, I think you covered that one.
Okay. Okay, which of the following can provide power gain? That would be a transistor amplifier. Okay, a transistor consists of 3 regions of semiconductor material. They're called the emitter, base, and collector, again, in a bipolar junction transistor. Okay, now there is another kind of transistor, which is very, very important because bipolar junction transistors are actually not all that efficient. They're efficient, but they're not that efficient. Again, this is called a BJT. Oops. It has a base, collector, and emitter. And this specifically is an NPN because the arrow is not pointing in, NPN, not pointing in. If it was a PNP, it would actually be backwards. The arrow would be pointing the other way. There's also a device called a FET, which is a field effect transistor, which looks something like this. And what does that thing right there look like?
Capacitor.
That looks like a capacitor. And what did we say capacitors were really good at doing? Storing energy in electric fields, right? Okay, so now let's say that I put pluses over here. If I put pluses over here, what's going to be attracted to the other side? Remembering that opposites attract.
Electron.
Yep. How about if I switched it around and put negatives over here? What would I get on the other side? I'd get positives. Basically, the electrons would be driven away and I'd have a net positive. So the end result of this is that I'm able to affect what's happening on this side without actually putting any current in by just putting a voltage over here. So and that's known as a field effect transistor because we're dealing with electric fields. The field itself is making things happen on the other side without any actual physical connection. And because of that, it uses very, very, very low current. They're very efficient. There are 3 terminals. Instead of a base, collector, and emitter, they're called the gate, the drain, and the source. So I don't know how you want to remember those, but you can just say, okay, well, the bipolar junction, there's a letter B, there's a letter B.
I have a question.
Yes.
The diagrams don't make very much sense to me. Like, okay. I don't really understand. I don't know. It's kind of hard for me to understand like what it's supposed to be.
Okay. So we're going to draw the rest of the circuit now. Okay, so we're going to draw the rest of the circuit. Okay. Now we drew the rest of the circuit. Okay, so now what we have is a transistor that's now connected to a power supply that has a signal coming into it on the left-hand side, and it's a small signal. What happens is that this signal may look like this. Okay, now, if that signal existed, it would go plus and minus. And what did we say about when a transistor turns on? This has to be at least 0.7 volts. So what we can now do with this circuit, with this signal, is we can add this to a DC voltage. And we can go like this. So now we've boosted it by a DC voltage. And we can get rid of the capacitor there. Put the capacitor over here. No, I don't want to draw it like that. Okay, so now what we've done is we've taken a small signal and we've basically now raised it by that amount. So now instead of the signal being down around 0, our signal looks like this. And maybe this is 1 volt. Well, the lowest it gets now is 0.8 volts. The highest it gets is like 1.2. They're both above 0.7, so that's okay. So now what we end up with is this signal right here, which represents, let's say, somebody's voice, going through this transistor. And when it does that, it causes, as this current flows, a proportional current is allowed to flow. A proportional but much larger current is allowed to flow through here this way. And since we have essentially an almost unlimited supply of power and current right here, it can get really, really big. And as this gets down here slightly bigger and slightly smaller, this gets really big, but slightly bigger and slightly smaller proportionally. As this is drawn through a resistor, we can generate a voltage right here, and then we can use the voltage over here. So basically what we've done, or we could also use a current, depending on how we wire it. And what we've been able to do now is basically just make a big copy of something. If you want to think of it in another way, let's say that I have a spring-loaded, right? That's a spring in this case. Let's say I have a spring-loaded water valve. And I have this connected to a big tank. Okay. You with me so far? Okay.
Yeah.
Okay. So now if let's say I let this valve close, how much water am I going to get out through this valve, through this pipe?
If you close it down,
If I just if I do nothing and just let that valve close down, how much water am I going to get out?
None.
None. How about if I open this, let's say halfway?
You got half flow.
I'll get about half flow. How about if I open this a quarter? I'm going to get about a quarter flow, right? How about if I open this, let's say, all the way?
Full flows.
Okay, right. So what that basically means is now I'm applying, if you want to think of it, this is a signal. This is a modulated signal. If I have instead of just doing it like partway full, etc., if I go between 0 and full out, and my signal varies like this, as I do that and apply that to my valve, which is essentially right here, and it's spring loaded, so it's always going to be it's always going to move the exact amount that I want it to. The copy that comes out, the amount of water that comes out through here is going to be proportional to what I just did. Do you agree with that? All right, that's an amplifier. That's what an amplifier does. Essentially, I'm going to get an exact, hopefully an exact clean copy of what I put in over here, out here. I mean, the thing is that could be a small pipe. That could also be, that could also be a huge pipe. It could be that the water that's coming out through here, I'm allowing to move the plunger on this. What would that be? If I'm applying, if I'm moving my spring here and I get a bigger copy right here, and that is directly moving this much bigger one, what am I getting now?
That's still amplification.
It's still amplification. This is actually 2 stages, right? That's actually cascaded amplifiers. No reason people do that. This may be, this may give you 10 dB of gain, and this gives you another 15 dB. If you can't do it in a single stage, you might split it into 2. You just do it electrically instead of using fluid. Does that make sense?
Yeah, that helped me a lot. Thank you.
Okay, good. Okay, let's see. Here we go. We are on to schematics. A schematic is a pictorial representation of things that are connected in a circuit. So it's not actually like a chart of how it's built. It's a wire diagram. So for instance, let's look at this figure right here, T-1. Okay, we're going to go through just briefly. Number 1 is a resistor. Number 2, anyone?
Transistor.
What kind of transistor?
NPN.
It's an NPN. Is it a bipolar or a FET?
BJT.
BJT, because it doesn't have the capacitor, so it's not a field transistor. All right, and it's an NPN because it's not pointing in. Number 3, that's a light bulb. Number 4 is a battery. And number 5 is a ground. That's another way to draw a ground. There are many different ways to draw grounds. A ground is our 0 voltage reference. So if we now look at this, we see, okay, well, we've got, see if I can draw it. Nope, that's a signature.
Go on.
So basically, if we want to think about that transistor being split in half, essentially the transistor is split in half. Right there. And we have this first side and the second side. So whatever happens on the first side is now mimicked on the second side. So if this first side works, what's going to happen on the second side? When we turn the transistor on by putting a voltage on the left-hand side, this channel right here is going to open up. If the channel opens up, then this entire path, let's see if I can, oh, come on. It's not going to let me do it. Okay. Yeah. Okay. Basically, the backside of the transistor is going to open up and allow current to flow from the battery through the light and through the transistor to ground, which is basically just going to turn on the light bulb. essentially, this is a very simple electronic switch for a light. There we go. Okay.
Can you
Next
take me
one.
back to that diagram one more time?
Mm-hmm.
Show me where the flow goes.
See if I can get it to do it. There we go. So there's the flow on the outlet side. It goes from the battery through the light bulb, through the now open, through the now shorted out transistor down to the ground, thus turning on the light bulb. And that's
What does
caused.
the side one have to do with it?
What?
I don't quite understand the importance of the side one on that diagram.
The first side turns on the transistor. It allows the transistor to start functioning. So the split is right through here. If you think of a transistor as basically two separate things that are merged together, if it's turned on from the base, that essentially allows it to be turned on the other side. It's an electronic switch.
So what am I twisting or turning with my thumb to make that light bulb come on?
You're, ask the question again. What do you mean?
You got the power coming out of number 4 block there, going through light bulb number 3.
Yep.
Okay, where's my thumb? Where am I throwing the switch?
There is no switch. The left-hand side is the switch. The fact that you turn on like all the way over here, right here.
Yeah, that's the
if you put a voltage there, that will turn on the transistor. I mean, if we wanted to draw it, we could actually do this. Here, let me see if I can get it to do it. Here, there we go. So if I wanted to, I could draw it like that. Almost. Hold on. If I really wanted to do it right, I would draw it like this. Why is it not letting me do it again?
So where your cursor is where the switch on the wall or whatever it is.
Yeah, here we go. Basically right there. And this is connected to the wall socket or a battery, more likely, something very low voltage. So as soon as I close the switch, that switch, the transistor will turn on, which will turn on the light. I'm going to draw it over here. I'm getting tired of dealing with that. I hear a lot of crickets. That means you don't get it. Okay, so we have two different sides of this thing, essentially. Right here. All right, so we have our base, we have our emitter, and our collector. Okay, this is really two separate circuits in a way. We can draw it like this. And let me just erase the whole thing. What I'm going to do is draw it like this. There's a diode. And essentially, here's another thing. So my circuits are actually on the left and on the right. And if I put a voltage here, and this is at ground, so this is 0 volts, I will get current flowing right there. Everybody agree with that? All right, I see shaking heads. That's good. Okay. All right. So as I have current flowing there, the act of that device, these are actually now interlinked, where if this has current flowing through it right there, this channel right here opens up. It opens up proportionally to the amount of current that's flowing through the other side. Right? These, because it's actually one device. If you look at how it's actually built, that I basically have current flowing through here. When that happens, that makes this entire path available. So whatever I have available right here will flow. All right, I got to get verbal feedback, everybody.
So are you saying that the switch tells the P to open up so that the flow starts?
Yes.
Okay.
So if I were to draw it like this, here's my switch, right? Or I could have it be a switch that looked like this. Just be a push button, and I'd have a voltage over here. As soon as I hit that button, I'm going to have a voltage appear on this right here, which is going to cause it to flow forward. As soon as it starts to flow forward, this channel becomes available. So to whatever's hooked up here. This is usually labeled as like VCC. It's the collector voltage.
So you have two voltages at the same time going?
Yes, they are isolated from, they're essentially almost isolated from each other.
All right.
So the first one almost gives the second permission to go along for the ride.
Yes.
Okay.
Yeah, I was thinking it's basically a little switch that turns on a bigger switch.
Essentially, yeah. But now here's the other thing. If in fact this isn't either fully on or fully off, it's partway on or more on than that, then this is going to be more open or less open, depending on how you do it. Which basically means if I don't run it full out, what I end up with is an amplified version, a linearly amplified version. And that's basically the difference between running as a switch or running as an amplifier. Does that make sense? Okay.
Yep, we got it.
Okay, good. And
So,
it's actually, yeah, go ahead.
So for that one push button example, what if you put a potentiometer there?
Well, I mean, you could make it so that, in other words, you're changing the supply voltage essentially, right? If you were to put a potentiometer right instead of number one, you mean?
Yeah, because you said depending on how much you're pushing that push button, if you're giving it more voltage. So just make the resistor a potentiometer, turn it full on, and then you can just dial in your amplification.
Right. Essentially, yes, you do have, essentially what you then have is something operating as an amplifier, a linear amplifier, by adjusting it to that to that amount. If you operate it so that it's in the linear range, then it becomes a linear amplifier. And it comes back to the response curve of the transistor itself. And the response curve of the transistor again looks like this. So this would be, this would be saturation, or this is, if you want to think of it, flat topping. And this right here is cutoff. So if you can change that resistance so that it's either operating in here or in here and here, this would be using it for a switch, and this would be using it for an amplifier.
Gotcha. So we just talked about using it as an NPN. What about a PNP?
You'd have to, well, if you did a PNP, you would essentially have the voltages opposite, right? A PNP is actually drawn like this. So if it flows like that, essentially you would basically have a voltage here and grounded here so that you would have current flowing this way. And then you would have this being like a ground with some resistance or here or something like that. So basically it would look something like that, or you could flip the whole thing upside down. But basically, yeah, I mean, essentially because it's backwards, the polarities would be different. It basically does the same thing, but the polarities would be different.
Okay.
Yeah, because it still has to obey the laws, you know, Ohm's law. It's still only going to flow in the forward direction. And it's
Okay,
still
so-
a diode, so you can't do anything about it.
So the same thing, but in reverse.
Yep.
Okay.
Fundamentally, you don't get any real difference. It's just that you have to wire it differently. And that actually is really, really actually complicated in a way because and this actually is something that comes up in my work that makes PNP logic really kind of a pain in the neck, because you're not switching 24 volts or 12 volts. You're switching the common. You're switching 0 volts. So you'll see 24 volts somewhere when you don't expect to, because there's no place for it to go. Instead of there being 24 volts or nothing. It makes it very confusing sometimes. So NPN logic is a lot more common for that reason, I think. Okay, let's see. The next thing we're on to is this next diagram, which I'm just going to show you, and then I'm going to recreate because I don't like the way this thing does annotation. So can everybody see that diagram okay?
Yep.
Yes.
Okay, and I have this on page 32. So what we're going to do is recreate this diagram. Here's an AC power source. And here's a fuse. What's the purpose of a fuse?
Keep from overpowering and damaging other components.
To keep from an overcurrent. So you don't have too much current flow. To keep from smoking something. Yeah. All right, let's see. Now we have this. Yeah, a fuse is an overcurrent protective device. Okay, so there's a couple of interesting things here. And here we go. All right, I think I drew everything. All right. So this is actually a really important circuit. So we're going to spend a little bit of time on it. It has some very important things in it that are really important to learn, that aren't necessarily on this, but on the test, but are really important anyway and will help with your understanding of things. Okay, this right here, what is that right there? And please feel free to be really interactive on this one, because this is actually really
It's
important.
AC power. Basically.
That's AC power. So I'm going to draw an AC circuit, AC voltage that looks like that. Okay, now this thing that's a fuse, why do we put a fuse there again?
Keep the smoke in the wires.
That's right, to make sure we don't blow something up. Now, let's say that this transformer right here shorted out. And normally this was drawing, let's say, 2 amps, and we put a 4 amp fuse over here. That's not really all that uncommon. So when we close this, if this was shorted, then we would maybe draw 15 amps. Well, if we suddenly saw 15 amps there, we would blow that fuse and thus not melt any wires. So that's why we use a fuse. We try to keep from melting components. Okay, now, this right here, anyone know what that is?
Which one?
The one I put the red arrow on.
Switch.
That's on-off switch. Yes, on-off switch. Okay. And how about this guy right here?
Transformer.
A transformer. Okay. Now, this is something we haven't really covered, which I It's not covered in the text, but I'm going to cover it here because this is actually one of those things that's fundamentally important to understand. Okay, what is this right here? We just drew this a few minutes ago.
Inductor.
An inductor. Okay, what does an inductor do? It converts current into
Electromagnetic.
a magnetic field in particular. Okay, so if we have an AC circuit, an AC signal coming into this, what's going to happen to our magnetic field?
Switch directions back.
It's going to switch directions continuously. Exactly. Okay, now that's fine. The next thing we're going to do is actually put a core made of iron or some other ferromagnetic material in here. Ferromagnetic means that it responds very, very strongly. We are on page 32 of the PDF. So basically a ferromagnetic material means that it responds very strongly to a magnetic field. And it's typically iron or nickel, some combination thereof. So what this does by wrapping the coil around it is that it concentrates the magnetic field inside the core. Well, if we make the core into the shape of a loop, we can now concentrate a changing magnetic field into the loop so that it keeps going back and forth inside the loop. What we then do with it is we wrap another coil around the other side. And this is known as mutual inductance. That's a second coil. And we now have a varying magnetic field going through the second coil because it got passed through the core. So if a current makes a magnetic field, what does a magnetic field make?
Current.
It makes a current. That's right. So essentially what we've managed to do is we've managed to constrain our magnetic field inside the core and then use that magnetic field energy to generate a second current, which we can now use. Now, the cool thing about this is that in doing so, one thing that we've been able to do, because energy is neither created nor destroyed, it just changes form, right? We all agree with that? Okay, so let's say that this thing is 100% efficient. Well, it turns out that if I have N turns of wire in my solenoid on that side, and I have, let's say, T turns of wire on that side, I get a voltage ratio where I have, let's say, VT and VN. Vn over Vt is equal to is equal to N over T. So basically my voltage on my, and this only works with AC, my voltage on my primary, this is the primary, and this is my secondary, is proportional to the number of turns of wire that are looped around that core. So if I have a transformer where I have, let's say, 120 volts coming in, and this is AC only, I have, let's say, 100 turns of wire over here and 10 turns of wire over here. If I have 120 volts coming in, I will have 12 volts going out. Why is this so important?
Because you need direct current.
No, well, but we're not making direct current yet. Why is it so important to be able to change our AC voltage?
So that we can run different devices depending on what they can handle.
Exactly. So sometimes we don't need 120 volts. Sometimes if we're running a vacuum tube, we might need a plate voltage of 3000 volts AC. Could we make that with a different transformer?
I would think so.
Yeah. Instead of 10 turns over here, you'd put 2500 turns over here and you get a 25-to-1 ratio. And then on your output, you get 3000 volts. Where do we see something like this? Anyone look outside, look up on a power pole.
Of the transformers that blow.
Transformer on your power pole. That power line running up in the street is 12,000 kV. It's 12 kV. Your house, they're going to bring in 240 volts. How do they do that? Got a lot of turns on their side and just a couple turns on your side. They change the turns ratio. It changes the voltage that comes out. If you have a three-phase system, you'll see three transformers up on the pole potentially. Sometimes you'll see one with 4 wires going into it. That's also a three-phase transformer.
So just to be clear, our little diagram below with the blue and the green is superimposed on the red square box with the black squiggle lines in it, right? It's a blow up.
Yeah. Sorry,
Why
I had
do
to. Go ahead.
Why do they use DC on train wires, but they use AC everywhere else?
It's easier to make because they can run DC motors on trains. DC motors can be more efficient. And they only need, they only need a single hot rail. A three-phase motor, you'd need 3 hot rails.
Mm.
Okay, so now that we've developed a transformer, and we understand what a transformer does, we now have AC going in, and we have a different voltage of, a different voltage of AC coming out, but it's still AC, but I'm going to draw it in green. Different voltage. Okay, so now we have this voltage which goes plus minus plus minus. What happens to the diode when the voltage goes plus? If I have a plus over here and a minus over here, what happens to the diode?
It opens.
It opens up, it turns on. How about when the voltage goes negative? And now I flip. And this is minus and that's plus. The diode turns off. So if I were to draw my waveform right there, my waveform now looks like this. Where this is my 0 line. What is that? Everybody, what's that called? When the voltage is only ever on one side of 0.
Half wave rectified.
Yeah, but in particular, what is it? Is it AC or DC?
AC.
That is now DC. It's very ugly, but it's DC. Okay, so what now? This capacitor, when the capacitor, when the voltage goes high, the capacitor charges up. And then when the voltage goes low, the capacitor says, oh, well, we're not charged up anymore. Well, I'm going to use some of my charge to flatten it out. And now my wave looks like this. So now my wave is sort of ripply, but cleaner DC. If I use a bigger capacitor, I can smooth it out even more. And now, how about this right here, this little device?
Which one?
Right here. What is that?
LED.
That's an LED. Now, if I have voltage over here, what does the LED show me?
That it's on.
That it's on. This is
That
my
it's
volt.
on.
This is my power indicator saying, yep, it's working. Okay. Whoops. Let me undo that. Hold on. Is this thing complaining? Okay. There we go. Okay, so this is my LED now indicating with red light that it's turned on. Okay, I now have this right here, which is a current limiter. Basically, by adding a little bit of resistance, that allows me to change my current. Okay, and remember we said that every diode conducts in the forward direction, right? Not that one, right? Because for every rule, there's an exception. Okay, this is known as a Zener diode. Now, it will work in the forward direction, but notice it's kind of in there backwards. This basically is a voltage reference diode that is operating above a certain voltage. It says, okay, I'm going to allow you to go until you get to a certain point, and then I'm not going to allow the voltage to go any higher. So this might be, let's say, a 5-volt reference Zener diode. And anything above 5 volts, it's basically just going to take it and say, okay, all the current's going to go to ground. This is your reference voltage. So what that does is it takes any extra ripple above a certain point and just says, okay, the ripple's just going to go away. And now we have a clean DC power supply. And this is a half wave rectified DC power supply.
Now, I used to have an old guy that would put a capacitor between the battery and his radio in his car. And he said that would clean it up.
It's a filter. Yeah.
So he's just filtering it through the capacitor.
Yep. And now we're actually getting to why that works. Okay, you ready for why it works? That's actually the very next thing. So just to cover up a couple of things, or to cover a couple of things right here. Okay, so switch number 3, they're going to ask what kind of switch that is. That's a single pole, single throw. It's single pole because it's one wire, and it's single throw because it's either off or on. A double pole throw or double pole switch would be 2 separate things that are parallel together. If it were a double throw, that would mean it has 2 different on positions. Okay, so a rectifier creates DC out of AC, which we covered. And let's see, we did capacitors, LEDs. Okay, here we go. Now, we're going to have to get into something a little bit new here. I know everything's new, right? But something a little bit new. Okay. So what did we say about resistors? We said resistors resist. Does a resistor care if a voltage is DC or AC? Does a resistor care?
No.
No, it does not. Okay. So resistors don't care at all. Okay. Now, we're going to move on from resistors into a capacitor, okay, and an inductor. And in order to understand what these things are doing, what I'm going to do is hook up this capacitor to an AC power supply. At first, we're going to have a plus and a minus over there. The capacitor is going to charge up to plus, and the negative side goes to minus. What happens when it's fully charged? Does anything else flow?
No.
No, there's no more room. But what if before it got to the point of being fully charged, I managed to flip the voltage so that it was over here? What would happen to the minuses that are now over there? They would be called home. The pluses would be called home. Eventually, they'd be gone. And now I'd have a brand new starting condition where this would charge up to plus and this would charge up to minus. Okay, but let's say that just as that happened, I managed to do this and flip it back and forth again. All of these would go away. And all of these would then charge. Does everybody agree with that? Basically, the capacitor just goes back and forth. Okay, so now what I'm going to ask is a thought experiment for everybody. If I were connected to a mystery box behind a wall and I had no idea what it was, and I hooked up AC to it, and all I know is that whatever I'm hooked up to, whatever switch, whatever position this is, whether it's plus or minus, there seems to be current flowing into it. What would you guess that is? If it doesn't seem to matter whether I'm plus or minus, I switch back and forth and the current flows back and forth and back and forth. What does that look like?
I'll bite. It's a capacitor. It's by
No. You're not. You don't know that. if I just am, if there's a black box on the other side of the wall, if I just know that whatever's on the other side seems to just pass whatever current I put across it. What is a simple device, a simple thing that just passes current?
Resistor?
Nope.
A
Even
wire?
simpler, a piece of wire, also known as a
Conductor?
a short circuit.
Short circuit.
A short circuit. It's just a piece of wire. As far as I'm concerned, that must be a short circuit because it doesn't make any difference. Whatever, if I have plus here, my current flows in this direction. If it switches direction, what happens? If I had now suddenly have a plus over here, the current flows this way. Well, what's the simplest thing that it could be? That's a short circuit. So what that now means is that for AC, right, a capacitor is what?
A short?
A short circuit. Because it might as well be. You can't tell the difference. So now let's do this. Here's the next part of the thought experiment. Here we go. I'm going to put an inductor back here. Okay. And I'm going to put AC into it. And I put AC into it, and it goes back and forth and back and forth. And once the magnetic field forms, there's a magnetic field going this way. And it's going this way. Well, now I reverse it. And the plus sign is here and the minus sign is here. But there's already a magnetic field in there. Magnetic field energy doesn't like to do that. It doesn't like to switch back and forth. So it responds very badly to the fact that I'm trying to switch this. So it behaves in a way that basically says, no matter what my AC does, I can never push any current into it. What is something that no matter what you hook up, if it never has any current going through it, what's that known as?
Open.
An open circuit. So for an inductor is equal to an open circuit. Okay, now let's hook a DC power supply to it. And we're going to make this an inductor. Okay, now I try to push current through this thing. What does an inductor look like to just DC? It's a piece of wire, isn't it? What's a piece of wire known as?
Short circuit.
Short circuit. That's right. So here we go. I might as well just replace that for DC with a short circuit. So DC inductor is a short. And now I'm going to make it a capacitor instead. Okay. So here comes my capacitor. Okay. So I hook up my capacitor and it charges up and then it gets full. Well, once it's full, how much more current flows into it?
None, because it's
nothing.
full.
None.
So DC with a capacitor is an open circuit because nothing flows in. It might as well be this. So if you look at these, they behave very differently, right?
They appear to have opposing philosophies of life.
They do. And that's
Why is
actually
that?
really important because of how,
Just-
because of how they store energy and how they react to changes. Inductors don't like change. Capacitors like change a great deal. So what that really means is as you pick one or the other, they behave totally differently. And in fact, the formulas, there's something called impedance.
Mhm.
Impedance is the opposition of flow to AC current. Resistance is opposition of flow to DC current. For a resistor, resistors don't care, right? Resistor is just a thing. It just resists the flow of current. But for a capacitor and an inductor, there's a huge difference, right? If you try to push DC through here, you can't. It charges up and it won't go any further. Whereas with the inductor, it's just a piece of wire. If I try to push AC through it, capacitor is fine with it, and an inductor doesn't like it. So now, just like everything in the world, nothing is absolute. And in fact, resistance is a letter R, and impedance is a letter Z. And in fact, impedance actually relies on something called reactance, which is letter X, which you don't have to know, but it's important to know at some point, if you go further, that Z is equal to R plus JX. And in fact, this is your R axis and this is your X axis. So depending on which way it goes, either up or down, you can actually have negative or positive or negative reactance. That's when you start to get into capacitors and things like that. For those of you who are in engineering school, you're going to be doing that if you haven't already. It's called complex impedance. So what this really means, what? So what does this really mean for us? So what it really means for us is for an inductor, ZL is 2 pi FL. For a capacitor is equal to 1 over 2 pi FC. It just so happens that those are what they are. And in fact, a capacitor has a negative value on it. So here's where it gets really interesting. If we take the frequency, notice that the frequency appears in both of them. Everyone agree with that?
Mm-hmm.
But in one place, the frequency is in the numerator, and the other place, it's in the denominator. So if we take the frequency and set it equal to infinity, what happens to ZL? It goes to infinity. And what happens to ZC? It goes to 0. If something has 0 impedance, that means it's a short circuit, which is exactly what we just found. If something has an infinite impedance, that means it's an open circuit, which is what we just did. So let's switch it the other way around. If we made it 0, then this has 0 impedance, and this has the 0 in the bottom, so it becomes infinity, which is exactly what we just found. Now, in the real world, we're not typically going to have 0 frequency. We're going to have something in the middle. And so as the frequency goes up, this one will go up and this one will go down, and vice versa. So is there a point where they might actually cross? The answer is actually yes. So if I were to do this and draw this, and notice that ZL is positive and ZC is negative, could I make them so that they're equal and opposite and cancel each other out? What do you think?
Absolutely.
You can. And in fact, you can make them so they're equal and opposite, and you get 2 pi FL is equal to 1 over 2 pi FC. And you solve for that, and you get the frequency is 1 over 2 pi square root of LC. This is known as resonance. When you build a circuit that uses an inductor and a capacitor, and you pick your capacitor and inductor values, because you can choose your L and your C creatively. When you do that, you can find a frequency where If these are in series, they completely cancel out. If these are in parallel, they go to infinity. And what you end up with is the fact that you get a circuit that has zero resistance, zero impedance, but only at one particular frequency. And as you get away from it, it changes. So what you end up with is a circuit that's frequency response looks something like this. So you can do all kinds of creative stuff with that. And again, this is known as resonance. Resonance is really important because it allows us to selectively make frequencies like this. Now notice that has a certain tone to it. The question is, why, when I hit this, does it have a certain tone? It doesn't matter what I hit it with. It's always going to sound the same. Why is that going to happen? Why, when I hit a bell, does it always ring with the same pitch?
Because the pitch is coming out of the object being hit, not
That's
the
right.
object
It's
being
how it
hit.
was built. It's exactly how it was built. That's its resonant frequency. By changing the size or changing the shape, we can alter that. The same thing is true with electrical circuits. And that's why we do what we do here. Like, for instance, if I use these and use a transistor amplifier, I can actually use a transistor amplifier in oscillation where it's in positive feedback, and I take some of the output and stick it back into the input, and it will sound. Has anyone ever heard feedback on a microphone when it's too close to the speaker?
Mm-hmm.
An oscillator does that on purpose. And by picking the capacitor and the inductor sizes, you can choose the frequency it does it at. And that's known as an oscillator. And we build those on purpose to make a certain frequency. Okay, so that being said, what I'm going to show right now is a practical application of exactly what we just did. See this simple little device right here? Can everybody see this?
Yep.
Okay, so item number 2 is what?
And a variable capacitor?
That's a variable capacitor. That's a capacitor, and it's variable because of the arrow through it. And item number 3
is a variable inductor.
It's a variable inductor. And in particular, it's like a tapped inductor because it's actually hard to make a physical variable inductor, but they get very expensive. But yes, it's a variable inductor. Okay, so by using these things, and the one that doesn't have a number on it, that's another variable capacitor. Number 4 is an antenna. All right, and an antenna has an impedance. Everything has an impedance. Okay, so let's say that I have an antenna right here with a Z impedance. I then put that in series with a capacitor, which has ZC. This is Z antenna. They add together. So looking at from here out, I have Z of antenna plus ZC. Now, this feeds into this, which is an inductor. That has some value ZL. Well, if I think about it, this is now in parallel with that. They're actually in parallel with each other from a signal level. So they're actually in parallel. So I then have that in series with this capacitor. And we'll call this ZCA and ZCT. So basically I have this mess in series with this. And what that allows me to do is make this unknown impedance by changing this value and this value and this value to something that I want look like something that I recognize. These are actually all tunable items, and what it actually looks like is something like this. You'll see this all over the place. Whoops. Hold on, I meant to go somewhere else there. And then we're going to take a break. I know everybody probably needs it. Here, MFJ 949E tuner schematic. Okay, so this is an MFJ 949E. Can everyone see this picture?
Yep.
Okay, what does this have? It has right in the middle, it says,
Inductor.
yep, notice right in the middle, it has an inductor and a transmitter capacitor and an antenna capacitor. If you look at how this is built, you'll see that the schematic inside, let me find a picture of it. User manual. And that one's a little harder to see. There we go. I hope it lets me open it. Yeah. It's not going to let me. Okay. All right. Well, basically what we've got is, and a very simple version of it, without any electronics at all, looks just like that. Two capacitors and an inductor. And, oh, here we go, instructions. It's going to be there for sure. Look at that. Can everybody see that?
Mhm.
What do you see? A variable capacitor, a tapped inductor, which is a variable inductor, and another variable capacitor. This is an impedance matching network. This is also known as an antenna tuner. If you're going to be on the high frequency bands, you're almost guaranteed to have one of those so that you can match the impedance of your antenna system to the impedance of your radio and be able to transfer power into your antenna.
And so you need that to make sure your voice comes out sounding like your voice. Is that the reason?
No. Let's say that, okay, here's the easiest way to describe it. Let's say you take a jump rope. All right. Okay. And you take the jump rope and you tie it to a doorknob and you slam the door shut. And then you whip the jump rope. What are you going to see on the jump rope?
Like a wave.
You'll see a wave. Okay. What happens when it gets to the doorknob?
It comes back.
Yeah. Why does it come back? Conservation of?
Like no energy's lost?
Conservation of energy. Exactly. Now, let's say that instead the jump rope was infinitely long. Would you ever see it come back?
No.
Okay. If you're transmitting a signal out into space and you send it out through an antenna cable to an antenna, do you ever want to see it come back?
Oh.
No, you want your power to go out, not back. Essentially, what you end up with is when you tie your jump rope to a doorknob, that's an impedance mismatch. Essentially, what it means is that you don't have a good match between, ideally, your jump rope. Every section of jump rope wants to see another equal section of jump rope immediately following it. If it ever hits a point where there's a discontinuity, there's going to be something that happens. Either it's going to send some of the signal out and some of it back, or if it's a doorknob, it's going to send it all back. Well, if it sent it all back, how much went into the world?
Nothing.
Nothing, right? You don't want nothing. You want it all to go out, which basically means you don't want to see anything come back. That is the purpose of an antenna matching unit or an impedance matching device.
So is this something that has to be adjusted frequently, or you just set it and forget it on the day
If you change frequencies, you will adjust it. If it's automatic, it'll adjust it for you. But because antennas are frequency dependent, capacitors and inductors are frequency dependent. If you feed lines can be frequency dependent, their impedance can be frequency dependent. So if you change frequencies, you're going to see a different impedance.
I'm going to take electronics class.
So if you hit a doorknob, would you create smoke?
Yes. Well, actually, in most modern transceivers, that was the equivalent of what my friend did with his shorted out antenna cable. And it didn't blow up his radio. It didn't blow up his amplifier, but it did blow up his antenna tuner. Power had to go somewhere. That was just the unlucky device.
Do those tuners, do they have fuses in them?
Nope. Nope. Or else it would have blown a fuse instead of blowing up his thing.
Could they have fuses in them?
I suppose it's possible. Yeah. Typically, if you hear crackling from inside the device, it means your impedance, your mismatch is not good, or you're running too much power. I've actually generated enough heat in one of them that I got arcing, and I actually melted a plastic coil form once. The whole thing just sort of collapsed. Okay, which of the following is a resonant or tuned circuit, an inductor, and a capacitor in series or parallel, which we just did? What's combined with an inductor to make a resonant circuit? That would be a capacitor. The function of an SPDT switch, that's a single pole double throw. That means on, off, on. It means you can switch it between one of two other circuits, A or B. A relay is an electrically controlled switch. You basically have a coil, you turn it on, and it pulls a contact in and makes the contact. Which of the following devices displays an electrical quantity as a numeric value? That's known as a meter. A device that combines several semiconductors and other components into one package is called an integrated circuit, or an IC. Controlling the amount of voltage from a power supply, that's known as a voltage regulator. We did that Zener diode. Electrical component used to protect other circuit components from overloads. That would be a fuse. It's essentially the sacrificial device. And a reason to use shielded wire. Well, we said that any current generates a magnetic field. What if you have two wires that are right next to each other and they're not shielded from each other? What'll happen? Your first wire will generate a current, a magnetic field. And what happens to the second wire? It picks up the magnetic field and
you got a transformer.
You got a transformer. Yes, it's a very simple transformer, and it's also known as mutual inductance. It's also known as crosstalk. If you've ever heard of crosstalk on wires, that's why you shield wires, because you don't want crosstalk typically.
So at my work, we have a policy or not, but when you're running cabling through the system, you can't put like AC wire next to the signal.
What do you build?
Semiconductor capital equipment.
Okay. Is it semi-tool or something? Or something similar? Yeah. Okay. I used to work for Sony. We bought all kinds of stuff from semi-tool and a few others.
We sell to Sony and Intel.
Okay. Cool. Yeah, I build factory automation equipment, and my most fun experience with crosstalk was when I had it was a 20 amp motor on an analog servo drive, and there was also a force control unit that was a DC, and it was DC and RS 485, and the wires, they were both shielded. And what happened was when I ran the motor above a certain speed, the force control unit basically fell asleep and lost its signal. And it was holding a 200-pound weight, which then proceeded to just drop. And it basically, we're running a buffing wheel, and the buffing wheel just started rubbing against something, and we didn't notice it for a minute, and then the smoke starts coming up, and that was because the wires were run parallel to each other for too great of a distance, and the noise that was being generated in the or by the servo was so great that it basically blinded the communications cable. and it could no longer pick up the RS-485 signal. So we ran one cable this way and one cable this way. We ran, so they were going apart and then joined back up, and everything was fine. It goes up, it goes down as the square of the distance too. So if you can get them apart, sometimes a foot is 4 times better than 6 inches.
Yeah, we at our company we have cables that have to be the exact length. The RF cables, if they're the wrong length, they don't work.
And is that probably because of impedance matching as well?
Yeah, we're making plasma, and so the length of cables, it matters.
Yeah. Well, and part of it is that you're dealing at a certain frequency. So if you're trying to get energy into a device at a certain frequency, if you have a piece of cable, it can actually act as an impedance matching transformer. Sometimes you don't want it to. You just, it has to be a quarter wavelength long to be an impedance match, and it has to be a half wavelength long to do nothing. And if it's a little bit off, you're going to end up with power coming back. So it's probably something like that. Very cool. All right, you guys ready for a 5-minute break? I think I am.
Scott?
Yeah.
Cindy, I'm low on battery on this device, so I'll be signing back in on a new device.
Okay.
Okay.
All right. All right, is everybody ready again? You know, I was totally serious about asking lots of questions. I love questions. And, you know, because I love digressing. You may have noticed that. The hardest part for me is coming back to where we started. Hey, Jacob.
Yeah.
So, okay, so tell me, have you taken physics or going to be?
No. Neither.
Neither. Okay, well, maybe you will now.
Yeah, I'm like in the chemistry track, I guess.
Okay. Well, but
So,
you know, chemistry is just an application of physics.
yeah.
So, well, physics is the granddaddy of them all. So,
I wanted to, but I don't know. I kind of got roped into chemistry a little bit.
yeah. So which one are you in? Is it general chem or
AP chemistry?
have you done organic yet?
Yeah.
You did organic? Did you like it?
Yeah, I did.
So the whole thing about chirality and S versus R and so you're good with that? You're good with the you can't remember what it's called, but when you look at something from end on and try to rotate one across the other and all your S&P bonding and stuff.
I could do that. I think chemistry comes pretty easily to me.
So I guess my question is, did you actually enjoy that? See, I never learned that in high school or college. It was not until my daughter, who's in college, had to take organic chemistry that I said, you know, I'm going to go back and learn this stuff. And I actually thought it was really cool. She hated it.
Yeah, I don't know if I liked it, but I got it pretty easy. So,
well, because it's a spatial thing.
right.
It's like, you know, okay, so you look at an ethane molecule and you hold it up and you can see, okay, well, you can rotate the back one 60 degrees and then everything's at minimum energy. And I thought it was really cool myself. So, but see, that all goes back to physics, because then you start dealing with electric fields and things like that. So there's a lot of tie-in between between physics and chemistry. You can't have chemistry without physics.
Right, and the other way around too. I think.
Yeah, you can have physics without chemistry, but you can't have chemistry without physics, because you know the whole thing about how a nucleus is built, and you know how you have, like, you know, specific orbitals and suborbitals. They can't, you know, their quantum levels are defined by physics. So anyway, that's when you get to physics, let me know. So what do you plan on studying?
Yeah, I have no idea.
I mean, is there any one area that you say, you know, I would really like to do this?
I kind of want to be a geologist, but
well, chemistry fits in well for that.
Yeah. I'm not sure yet, though.
And you know, actually, when you go out and do field studies and you don't have any cell service, you bring a radio with you. Actually, that was actually one of the reasons why our the head of the club at the University of Oregon, the faculty advisor, that's one of the reasons he got into radio in the first place, was because he's a field biologist and he goes all these places where there's no coverage of any kind. I mean, way out in the middle of nowhere.
My parents actually, they used like 10 years ago or whatever, they used ham radios to communicate before they had phones. So
yeah, so did I. Well, I was in college.
In the middle of nowhere too.
Yeah. All right. Any other questions before we move on? Okay, we're on page number 50. Okay, so we're jumping around a little bit, but now that we've touched on what waves are and how to make them, now we're going to talk about how to move them from place to place, how to actually launch them and move them around. Okay, so we're on to antennas and feed lines. Okay, a simple antenna, The most fundamental antenna is known as a dipole. A simple dipole is a horizontally polarized antenna. Here's the surface of the Earth. It has a total length. Yes, it is split into two halves of 1/2 wavelength, which is why it's called a half-wave dipole. Right? That's a simple dipole, horizontally polarized. Okay, so a half-wave dipole radiates its strongest signal broadside to the antenna. So that would be, if we're looking at the dipole edge on, it would be right toward us and immediately away from us, and also up and also down. There is essentially no radiation from the direction of the wire. So in the direction of the wire, there's virtually nothing coming off of it. The simplest pattern you can draw around it is if you think about, let's say you take a piece of wire and you can either use a bagel or a donut, depending on which one you feel like. You string the bagel or the donut onto the wire in the center, and that's what the radiation pattern looks like. Okay, so now we're going to start making antennas. So the question is now, how do you make an antenna? Well, we're going to start by saying this, we're going to use this wavelength. Or sorry, we're going to use this formula for frequency and wavelength. And we're going to say that we're going to make an antenna for, let's say, 6 meters. Okay, so what we need to know for that is our 6-meter band is, the wavelength is 6 meters. We really need to know by looking at our frequency chart where in the band that is. And we can see that on the 6-meter band, it goes from 50 to 54 megahertz. So we're just going to go right for the middle of the band. That's a safe bet. So we're going to pick 52. So 300 F lambda. Okay. We know our frequency is 52 megahertz. So we need to know our wavelength. So by this, wavelength is equal to 300 divided by 52. Anyone with a calculator handy?
What was it called? So you got 5.76.
Okay, keep that calculator open. 5.76 meters. Okay.
The ballpark of 6 close enough?
Yeah, no, we're gonna carry a couple of extra digits. 5.76 meters. All right. So now that was for a full wave. So we're going to do a half wave. So somebody divide that in half. What do we get? 2.88?
Yep, that's what I got.
Okay, 2.88 meters. Okay. So now what we're going to do is we're going to take 95% of this. The reason we're going to shorten it by 5% is because of the real world effects of wire. No wire is infinitely perfect. So it turns out that the real world effects, coupling to itself, coupling to the things around it, 5% shortening. So we're going to take 95% of 2.88. And what do we get? All right, who was doing my calculator?
2.74.
2.74. Okay, in meters. Now we're going to multiply that by 39.36 inches per meter. What do we get?
One 107.68.
Okay, we're going to go with 107.7 inches. All right, so for 52 megahertz, we've got 107.7 inches. If we went with 50 megahertz, it would be a little bit longer or shorter. If we went with a lower frequency, would it be longer or shorter?
Lower the frequency, the longer the wave, isn't it?
Yep. So if we lowered the frequency to, let's say, 50 megahertz, our antenna would have to be slightly longer. If we went to 54 megahertz, our antenna would end up being a little bit shorter. So let's say that we made this antenna and it's 108 inches long. So if we did that, it would be cut for 52 megahertz. So that would be a 52 megahertz antenna. It would be 108 inches long. So when we actually build the thing, how long should we make it?
It's easier to cut off than it is to add to, so.
Exactly.
112.
Exactly. So maybe you go a couple inches too long. You know, maybe you go 112, 114, something like that, and then you trim it to length. And you continually, basically, you hook it up to something called an antenna analyzer, and you see what the SWR or standing wave ratio is on a particular frequency, and you keep trimming it until you like it. All right, so guess what? We just built an antenna. So it's 100, let's say it's 112 inches. We're going to go 112. If it's 112 inches total length, how long is each of the two legs? 56 inches. We would typically feed that with coaxial cable. One side goes to the shield, one side goes to the center. We run that back down to our station. That's a fully functional, very, very useful 6-meter antenna. Now, we can also make a 2-meter antenna. So next, we're going to do the same math, but a little bit different. So we're going to pick 146 megahertz, which is right smack in the middle of the 2-meter band. These are things that it's good to remember. Okay, so we're going to do the same thing, 300 F and lambda. Somebody do the math for me. 300 divided by 146. Don't be shy.
2.0547.
2.05. Okay. All right. So that's one wave. Okay. So now we're going to say, do we want to make a half wave or a quarter wave? Let's do a quarter wave. Okay, quarter wave. So what's a quarter of that?
0.51.
Okay, 0.51 meters. Okay, and we're going to take 95% of it. Zero point what?
4.48.
Okay, and now we're going to multiply that 39.36 inches per meter.
$19.2.
Perfect. That's what I have on the roof of my house. Okay, so what I have up there is a vertical quarter wave. And at the base, I have 1, 2, 3, 4 ground radials that are a quarter wave long, tipped down at about a 30-degree angle. And that's it. I have a $5 antenna on the roof of my house. It works great. And that's the nice thing about this, that you don't have to spend a lot of money on an antenna. You're rewarded for creativity if you come up with something that works well. Okay, let's see. How to
bare wire, or do you have coated wire?
Up there I have number 12 THHN. And yes, a coating on the wire actually changes the length that you need. Believe it or not. Coated wire versus bare wire actually changes it slightly.
What is the there's 468 and 234 numbers that people use?
You can use those. I choose not to, but basically the length of a wave in free space instead of 300 is 984 feet instead of 300 meters. So it's just basically that 984. Then they reduce that to 492, which then goes down to 468 and 234 for a quarter wave. So I choose to not do that because it's just more stuff to memorize.
Right, but it's the same ultimate.
It's the same thing.
Okay.
Yeah. Okay. So let's say that I find that on my antenna analyzer, when I built this antenna, my target frequency was 146 And I found that here's my SWR. And it's at about 147. Is my antenna too long or too short?
Too long.
Nope. Think about it.
Yeah.
It's too short. Yeah, I kind of screwed myself. I have to start all over. Or I have to solder something to the end of it. If I instead found that my antenna looked like this, oh, come on, let me erase it. If I found that it looked like this, and it was at 145, is my antenna too long or too short?
Too
Yeah.
long.
It's too long. Okay. At that point, I go up here and I go snip, 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 like 1/8 of an inch at a time, and I watch the frequency come up. Always better to make an antenna a little too long than too short.
Is now a good time to ask about the difference between center feed and end feed?
Sure. Okay. Really, here's the, okay. Ignore the feed completely. What we're going to look at is an antenna element. All right. So we're going to start with a trick question. What is the current at the end of a piece of wire? Can only be one thing.
Zero.
Zero. Has to be zero. It has to be zero at both ends. And if we're doing something that has a wavelength, basically what we start doing at that point is drawing waves on our antenna. If it's a half wave long, it must be in this format. Right? Our current distribution has to be that. Well, by looking at that, it's obviously it's highest in the center. Now, its voltage is going to be peak at the ends and lowest in the center, so it's going to look something like this. So this is our zero. It's not really going to be zero. It's going to be, but it's going to be as low as it's going to get. So now here's my question. If this is my I and this is my E, oops, and this is my E, what is my resistance? What's the formula? What's Ohm's law, everybody?
E equals IR.
E equals I times R. But in fact, we don't really have R in this case. What we have is impedance, which is actually the letter Z. Because it's actually complex. It has resistance and it has reactance. So we actually have to take that into account. But what this really means is we can rearrange it and say that Z is equal to E divided by I. Okay, so let us analyze at the center. We're going to look at this empirically. So is our current at its minimum or its maximum in the center?
Maximum.
Max. Okay. And what, how about our voltage? It's going to be minimum. So what's something big divided by something small?
Big.
Oh, wait, hold on. I did that upside down. Ah, crap. So it's going to be min because it's our voltage divided by our current. Min divided by max. So if something is minimum divided by maximum, what does that mean it's going to be?
Small
Minimum.
fraction.
Minimum. Okay, so now we're going to take it at the end of the antenna. Z is equal to, is our voltage going to be minimum or maximum? Maximum. And our current is going to be minimum. And maximum divided by minimum is big.
Yep.
So basically, these antennas, what it really means is if you look at where you want to feed it, that will determine how hard it is to get power into it. Once the power is on it, will they behave exactly the same? What do you think? The laws of physics say,
based on our 3 hours of training, I'm gonna hypothesize that it's all the same once you get
it's
into
all
the
the same.
circuit.
Once you get the power onto it, it's just a piece of wire. It's going to be the same. It's always going to be the same because the laws of physics say that the current has to be zero at the ends. I mean, that's the laws of physics say that that has to be the case.
Okay,
Right?
but
So
somebody makes two different kinds of center feed and end feed. There's got to be a reason that they make them.
there is. There
Do
is
tell.
definitely a reason. Okay. The reason that I would do a center feed is because I'm feeding it at an impedance minimum, right? That makes a lot of sense because let's say that this has an impedance of 70 ohms. I have cable that's 50 ohm cable. That's actually not that bad of a match. So let us take it instead and feed it at the end. My feed point impedance at that point is 2000 ohms. What would happen if I hooked up a 50 ohm cable to it? This is 50, 50, 50, 50, and all of a sudden it sees a doorknob. What happens to the power?
It goes backwards in the wire or turns
Yep.
to smoke.
Right. Well, more than likely, it's not going to be burned up, but it's going to end up going back down into your transmitter. Well, that's not particularly useful, right? So a very popular antenna now is something called an end-fed half wave. And what you do with an end-fed half wave is if you feed it here, you do this with it. What are we doing there? What does that look like?
It's a transformer.
That looks like a transformer, doesn't it? Well, it turns out that you have a Z2 over Z1 because a transformer changes your voltage and your current is proportional to the square of the turns ratio. So if you have an impedance match of, let's say, 2000 divided by 50, which is about 40, is equal to n squared, then your n is about 6.5. That's your turns ratio. So what you'll find in an end-fed half-wave antenna is a transformer with about a 6.5 turns ratio to get your proper impedance for your coax cable. Pretty cool, right? Now, why would you want to make an end-fed antenna versus a center-fed antenna? It's all about mounting. It's all about, when you actually go to put the thing up in the air. What if you've only got one tree? What if you've got two trees? What if you've got a tree and a house? This antenna, if it's for the 80 meter band, okay, so we're going to say 80 meters. How long is this antenna? 300 divided by 80. So that actually, we don't even need to do that. Let's just say this is like 3.6 megahertz. It's about 80 meters long for a full wave. Half wave is about 40 meters. And 95% is 38 meters, which is about equal to about 130 feet long. Okay, if that's 130 feet of wire, you have two ways to do it. You can do two 65-foot segments and feed it in the middle, or you can use a 130-foot piece, feed it here, and use really light gauge wire and pull it up into a tree. So at that point, it comes down to how you feel like putting it up. Vic, does that make sense?
Yeah, so it's not just straight science. There's some
Nope.
real practicality, like how much real estate, how many trees do you have to play with?
Yep. That's
Okay.
why antennas are what we call a black art, because you start with theory and then you really deal with practice. You can build something as theory says you should, and then you actually build it and it doesn't work worth a crap. Because
There's a group
theory,
on Facebook that claims you can use the gutters on your house. as
yeah,
an
you can. I mean, you can use anything, right? I mean, you can literally use anything if that's a piece of metal. But the question is, I mean, and you can load up the gutters on your house and have them radiate signals. I mean, a lot of the power is going to get lost, but some antenna is better than nothing. That's really what it comes down to.
So when you put the 130-foot antenna in the tree,
Uh-huh.
do you need like the whole thing in the tree? Because you said it has to be a very specific length. So if it's not that, like, what if it's not, what if it's underneath the tree or something like that?
Well, how
Part of
high?
it. I don't know.
Okay, so here's what the antenna in my parents' attic looked like. Okay, so this is a top view of the attic. Here's the center point. So it actually went like this, right? The peak was in the center. My antenna looked like this, center fed. It went like this, and this, and then this, and then that. And then this one went like that and like that. This is not a perfect antenna, right? Ideally, you want the whole thing to be stretched out. Clearly, that is not a perfect antenna. I even tried it like this. I tried a shorter one that looked like this. And for this one, I went like that. Right? That didn't work so great, but it's certainly better than nothing. I mean, I tried antennas that went like this, where I fed it off of one side. I went like this with one. And the other side, it went like this. And, you basically have to go, and it's drooping down at the same time. So really what it comes down to is you try to put up whatever you have space for. And you do the best you can. And, if you have room for a tower, more power to you. And if you don't, then you put up what you can. And learn to be creative. I have an antenna up in my tree right now. So let's look at this, 160-meter band, right? 160 meters times 3.3 is about 525 feet, right? A half wave would be about 262 feet long. A quarter wave is still 131 feet long. I do not have a 131-foot tall tree, right? But I do have a 95-foot tall tree. So what I did is I took an antenna. I had somebody put a pulley up there the last time they came out to trim the tree. And I pulled a wire up to here, which at the top, so this is about 75 feet. Well, it's still obviously not long enough. So what I did was then I ran a wire here and a wire here, and through some computer modeling, I found that if I made those about 60 feet long and I fed it all the way down here, and I had 60-foot long pieces down here, that actually was a functioning antenna. It doesn't look like it should be, but it actually is. And I could get power into it. And I've on 160 meters, which is basically your AM radio frequencies from Oregon, which is all the way on the West Coast. I've confirmed 41 states so far. And most of them that I'm missing are in the Northeast. So I got to wait till winter again. But, this antenna, it shouldn't work, but it does. And that's when, you start looking at, okay, well, what is the function of this section up top? And what is the function of the section at the bottom? And how do they interplay with each other? And really what it comes down to is you put up what you have room for. And if something, goes through a tree, so be it. You know, if something is fed out of the center of the top of the tree, that's great. If you don't have room for that, and you have a tennis ball launcher, or you have a slingshot with a weight on it with fishing line to get it up over a tree, then you do that. Antennas are still the most do-it-yourself thing that there is in ham radio, and that's what makes that a lot of fun. Okay, electrical loading. That's electrically lengthening an antenna by inserting inductors and radiating elements. Okay, we have one of these, and it looks like this. This is a 2-meter antenna. Does everyone agree with that? This is a 2-meter radio. This antenna, as we said, should be 19 inches long. We all agree that this antenna is only about 7 inches long. The reason being that this antenna looks like this internally. What they've done is taken 19 inches of wire, and they've taken about 16 inches of it and coiled it up. And there's 3 inches at the end that's exposed. So the question then is, how well does that part radiate? What do you think, everybody?
Pretty well.
Since most use it, I'm guessing it works pretty good.
No, it's pretty shitty. It's pretty
I'm
awful.
thinking the coils will cancel, like,
yeah,
one coil will cancel the next coil
exactly.
above.
You get all
cancel
kinds of
each other out.
cancellation. It's pretty horrible. Pardon my language, by the way. It's pretty awful. But here's the question. Now you start looking at this. Now you start to have to go through. Here we go. Let's say that we have this antenna with this radio, right? Okay, and up here at this repeater, on top of this tower, on top of a hilltop, we have another antenna. And we're operating with 1 watt of transmitter power, and we'll call that 0 decibels. And we have, between here and there, minus 120 dB of loss. Yeah, let's call it minus 100. Okay. So we lost 100 decibels of signal. Well, okay. So let's say that anything greater than minus 110 dB will still be good. Well, minus 100, we started at 0. 0 minus 100 is minus 100, which is still better than the minus 110. So does that work? Yes, it does. We can still be heard. All right, now let's instead take this antenna, and we're going to use this dummy load antenna, or the rubber duck as it's called, and that has a gain of minus 4 dB. Okay, well, let's do the math again. So now we have 0 minus 4 minus 100 is minus 104 dB. Okay, well, we still have anything greater than minus 110 is okay. So are we still good? Even with the lousy antenna, we're still fine. So what it means is, if we're on the fringe of being able to work or not, that means that we're closer to the fringe, but we're still fine. It might mean that if we went 20 miles further that way, that might be the difference between getting heard and not getting heard. But for what we're doing, it's fine. And the fact that I can put this on my belt and not jab myself in the armpit all the time is a definite benefit. You know, and it's kind of a pain to have a 19-inch antenna laying around and, you know, sticking up all the way to here when it's on your belt. Kind of gets in the way. Okay.
I use the Bree, they're 42-inch
Yep.
antennas, but you know, yeah, it does stick up, but I get a much better signal than I ever got with the
That's
others.
right. That's right. The question is, do you need it? Where are you? And whether or not it's going to make a difference.
So what
Well,
about the
West
ground?
Coast Seattle area.
What?
What about the ground plane and all that?
Ah, yes. Okay. Well, here's that. Therein lies the next question. Okay. A quarter wave antenna is kind of a misnomer. All right. So the reason I'm going to say that is because what we're going to do is take this light. Notice everybody sees the light. Okay. I'm going to find a nice reflective surface. like this can. Okay. Do you see a reflection coming off the can as well?
Yes.
Okay. Now, if I didn't tell you that was a can, how many lights would you see?
2.
There would be 2. But in reality, there's only 1. So to the rest of the world, let me hit the lights again. This is one of those things where antennas are, again, kind of a black art. Okay, so let's say that I have this signal, this person looking at an antenna, right? This person basically gets this antenna image right here, right? Okay, now this antenna, we're just looking at that one dot up top. There's 2 paths of light that make it to the person's eye. One of them goes that way, and one of them goes this way. It bounces off the reflective surface. If I were to continue this ray and find that it intersects somewhere, it actually intersects right there. How many lights would the person then see if they didn't know there was a reflective surface? They would see 2, the top part and the bottom part. Essentially, the observer doesn't know that the other antenna isn't there. It might as well be there. And in fact, in order to do that, this current goes up this way, and this imaginary current flows downward into this ground plane. So this is a quarter wave, and this is a quarter wave which doesn't really exist. Essentially, it's mirrored in the ground plane. It's like a reflective surface. And current flows down into here and back out of here to create that image. So now let's ask this question. Let's say that I have this handheld radio in my hand, and this is a quarter wave antenna. What do you see that's missing?
I don't see any ground to help you.
That's right. Okay. Let me ask this question. What is this back of the radio made out of typically? This is metal. And what is this that's holding it?
Your hand. So you are the ground.
But notice I'm not directly coupled to it. If you were to look at the metal case and my hand, what is there between the metal case and my hand?
Plastic wrapper?
No. There's your skin and some moisture. But what is that? What are you largely made out of?
Water.
Water. But in particular, what kind of water?
Salt.
Salt water. Yeah, you're a pretty good conductor. So essentially what you have is metal, and then skin, and then you. What does that look like to everybody? That has a name. That is a capacitor. So what happens? You become capacitively coupled to the case of the radio.
So you're storing the energy?
Essentially, yeah. The current is flowing from the shell of the radio and using you as the ground plane. And it's flowing back and forth in time. The same thing is true if I do a quarter wave mag mount on the roof of my car. So this is a quarter wave antenna. And here's the metal roof, right? It's just a magnet. Well, in the base of the magnet, we have our cable coming in, the center conductor goes there, and the outer and the shell goes there, and there's a shell there's basically a like a plate. Well, what do you call a metal plate and a metal plate with a gap in between? What's that called?
Capacitor.
That's a capacitor. So essentially what you have is you have capacitive coupling of your quarter wave antenna to the roof of your car. So you're basically still using a well-functioning antenna. You don't actually have to drill into the roof of your car to get it to work. Now, I have been unlucky enough to actually get an RF burn on my hand from my handheld radio. I was transmitting at high power, and one of the mounting screws, which I didn't have the clip on it, one of the mounting screws was right next to my hand. As you can see, there's the mounting screws right there. It was right next to my hand. And it was a really humid day, and my hand would like move away and get closer and move away and get closer. And every time it got close, it would make contact and give me a little RF burn into my hand, which actually surprised me quite a bit. It's a little painful. Okay. Shall we move on? Okay, so that's loading. What is a beam antenna? A beam antenna is something that looks like this. It's an antenna that concentrates signals in one direction. That's a beam. Antenna gain is the increase in signal strength when compared to a reference antenna. A reference antenna that's usually used is usually a dipole antenna. So when we measure our gain, what units do you think we would use for measuring gain?
Decibels.
Decibels. So this antenna might have a gain of 9 dB compared to the dipole. So it's actually 9 dBd. That's how you'd call it. If I had a smaller antenna, for instance, I got rid of some of these elements. This antenna might have a gain of 7 dBd. So in other words, 7 decibels better than a dipole. All right, this antenna, the typical design of beam is known as a Yagi, named after one of the inventors of, actually he was the professor who had the student who actually came up with it. So he got the name. It's known as a Yagi beam antenna. What is the disadvantage of a short, flexible antenna provided with most radios? We just covered this. It has reduced efficiency because it's electrically short. We're on.
So on
yes.
Question on that coil with a straight line at the end. So it suffers in that it doesn't have as much decibel output, but it still is capable of transmitting on whatever wavelengths is the length of the antenna.
It's definitely right, because electrically it's the right length. I remember an antenna once that somebody came up with, and I don't remember what the exact name was, but it looked like this. And it was 2 inches long. that was a 2-meter antenna. It was 2 inches long. So, I mean, its gain was probably negative 10 dB. But if you were working right under the repeater site or a mile from the repeater, it'd be fine. So it really all comes down to the right antenna for the job. That's all antennas come down to the right antenna for the job. Okay, let's see. Disadvantage of using a handheld radio inside a car. Everyone?
It's a Faraday cage?
Faraday cage. You have an incredible amount of shielding from the car. That is why most people take, if they're going to be in a car, they take an antenna, they slam the cable in the door and use a mag mount antenna and stick it to the roof.
Does that break the cable to slam it in the door?
No, usually there's enough weather stripping that it just crushes the weather stripping. I've never guillotined a cable that way.
Mine's got crush marks on the side, cable that is.
Well, yeah, I mean, you
Looks
can,
like it's broke, but I worry.
yeah, it's probably fine. I mean, I wouldn't use anything bigger than RG58 for that, just for that reason. Most of them use RG58. Some people use through the glass antennas, which is essentially capacitively coupled. I'm not a huge fan, but they do work. Unless you've got metallized windows, in which case they don't work. A 5/8 wave antenna typically has a lot more gain than a quarter wave antenna. What's the disadvantage of using a 5/8 wave antenna?
Well, it's gonna be quite a bit longer. Go
It's
back to the-
46 inches long. So if you have that on the roof of your car, you smack a lot of trees, you hit garages, garage doors, you pull into a gas station, you hit stuff hanging down. So for me, a quarter wave is just fine. All right, we're on to feed lines and connectors. We are on page 54. Okay, why is coaxial cable so commonly used? The reason being that it's really easy to use and you can do cool things like bury it without worrying about damaging it. What is impedance? Impedance is the opposition to AC current flow. Unit of impedance is also the ohm. Most common impedance of coaxial cable used in radio is 50 ohms. And that is true because it turns out that most radios have an impedance on their output of 50 ohms as well. 50 ohms represents actually a good match between cable size and power handling and ability to transfer power. So there's no reason that a feed line can't be something other than 50 ohms. But it was standardized, I don't know, probably 70, 80 years ago at 50 ohms. What happens as the frequency of a signal in coaxial cable goes up? Coaxial cable, as the frequency goes up, gets worse. You get a lot more and more loss. So you have different cables that can have the exact same impedances. All right, so the way that cable works is that since we have two parallel lines, or you can have a cylindrical symmetry like this, where you have a center conductor and then an outer conductor or outer shield. You basically have a cylindrical symmetry between the center and the outside. If you were to draw it like that, you have this, you have self-inductance. You also have in between, you have two wires and a space in between. What is that known as?
Capacitance.
Capacitor, right. So you can model a coaxial cable like this. And that goes on and on forever. It's a repeating thing. You could actually split this up into other ones as well, like that. And then you can break it up into individual sections. And from that, you get characteristic impedances. So it basically has a characteristic impedance, not because there's a lot of loss or anything like that, but because that's physically how it's built. The capacitor is defined by how far things are apart, and how thick the center conductor is helps to determine what the impedance is of the inductance. So essentially what you've got is the way that it's built, the geometry. I could do the same cable with the same parameters in a size like this. This would be 50 ohms, and this would also be 50 ohms. I could also do a cable that was this big. That was also 50 ohms. What would the advantages or disadvantages of each of those be?
Flexibility in the wire. I don't know.
Yeah, that's a big one. Like this could be hard line. This is 1 5/8 inches and it weighs a ton. How about other ones?
The length of the cable?
No, the length doesn't matter.
How much power it can carry?
Yep, because you have different size conductors. So there's power handling. How about other ones?
Is heat dissipation an issue?
Yep, well, that comes into power. But yes, heat dissipation because you have more surface area. Other ones? It sort of feeds from the other ones. It'd be loss. Just generally loss. The smaller the cable is, the higher the loss. And what we can do is pop this up. Where did I put it? Right. And coaxial loss calculator chart. And there are many of these out there. And notice attenuation in dB per 100 feet. Here we go. I hope this works. Here we go. So dB per 100 feet at different frequencies. So you basically will look at this and say, okay, well, as clearly as our frequency increases, our loss goes up. And as we go to bigger and bigger cable, like LMR 600 is pretty big, we get better and better performance. So let's say we're using one gigahertz right here at the very bottom. If we were doing that, well, for 100 feet, if we were using LMR 400, which is pretty good cable, we're only going to have 4 dB of loss. If we went to RG58, we'd have 21 decibels of loss. That's a difference of 17 dB, or 10 and 3 and 3. So that's 40 times. We'd lose 40 times more power. It makes a big difference. So that's why it's important to understand this when you're picking a cable. Somebody asked once, we run a TechNet here, and they said, well, I've got a 100-foot piece of cable and I'm using it on 70 centimeters. And I'd like to know if I should use only 40 feet, which I need to get to the antenna, or I should just coil up the other 60 feet. What do you think, everybody? If we look back at that chart.
So the minute you hear coil, don't you get the crosstalk you were talking about before?
No, because it's all one coil. It's all the same signal. But it's at 400 megahertz, and it was RG58. So what's the loss per 100 feet at 400 megahertz? 11.2 dB. So in other words, by reducing that to 40 feet, it's down to about 5 dB, 4 to 5 dB. By going back to up to 100 feet, they get an additional 6 dB of loss. What's 6 dB? Let's do the math. 6 dB is equal to 3 plus 3. Every time you get a factor of 3, that's 2 times. Yep, 2 times 2. So in other words, their loss went up by a factor of 4 just by leaving that extra 60 feet of cable in. So what do we tell them to do?
Cut it off.
Cut it off. Get some extra, end up with 60 extra feet of cable somewhere else. Don't put it there, because it will have a huge impact on your system.
What about the ladder cable that old timers used to use?
I use it. That's actually what I have up in the up in my trees. Okay, so ladder line looks like this, also known as window line, and it's got 2 parallel conductors, and it's 450 ohms impedance. Now, how does 450 ohms work with an antenna that has a 50 ohm impedance? That doesn't match, does it? Well, I could, if I really wanted to, I could use a transformer. I could do that. I could use a 450 ohm to 50 ohm impedance matching transformer, but I did not do that. What I did instead was I just connected it directly and accepted the fact that I have an impedance mismatch between my antenna and my cable. And so what that does is I intentionally have an impedance mismatch, which I then tune out of it. And because this particular ladder line, this particular feed line, has a loss of something like 0.2 dB per 100 feet, what happens is my signal basically will bounce up and down and up and down and up and down, back to the antenna, back and forth. But because the loss is so low, most of the signal eventually goes out. So that's why people still use it. the conductors are far enough apart that the losses are very, very, very low. Okay, let's see, where were we? Okay, bigger cable has less loss. So RG213 is about the size of my thumb. It's about the thickness of my thumb. RG58 is about the thickness of this pencil. So the bigger cable typically has less loss. If you're using VHF and UHF and you're putting up, let's say, a repeater station, you might want to use air insulated hardline. Like my friend Brad, who put up an antenna tower and used 1 5/8 inch hardline. It weighs about 20 pounds per foot, but he got it for free and he got the connectors for it, and it works really, really well. Source of loss in coaxial feed line. Water intrusion. Water intrusion is bad because it causes things to corrode. Corrosion makes for bad connections. High SWR and multiple connectors in the line. Every time you add a connector, you add loss. So that makes things worse. High SWR because you have signals bouncing up and down. SWR is standing wave ratio that we're going to get to. What's the main cause of failure in cable? Moisture contamination will kill cables. That means if you're going to do something outside, anytime you have a connector, tape, 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 tape. Lots and lots and lots of tape and waterproofing. The outer jacket of a coaxial cable should be resistant to ultraviolet because it's going to be outside. If it's in the sun, it's going to crack if it's not. And if it cracks, what's going to get in through the cracks?
Water.
Water, and water destroys cable. So there you go. Air core coaxial cable compared to foam or solid dielectrics. You typically have to pressurize it with nitrogen and make sure that it doesn't get any moisture in it, which means you need all kinds of special techniques to use it. But if you go to a television station or a radio station, something that uses a high power transmitter, they all use air-filled cable. A PL259 connector. Okay, so a PL259 connector is also known as a UHF connector. Isn't that weird? So a PL259, this is what a PL259 looks like. And here we go. You may recognize these as your very, very basic connectors if you've done radio before. Okay, notice this says UHF male crimp. Well, that's a misnomer. UHF was coined a long time ago, and it stands for Universal High Frequency, which basically means this is a good connector for HF and kind of VHF as well, but it's actually terrible for UHF. It's really bad for UHF. What you want to use for UHF is something called an N connector, which looks like this. And this is actually a waterproof double shielded connector that's good up to about good beyond a gigahertz. And in fact, they say up to 18 gigahertz. So I don't typically go that high, but okay. So up to VHF, a PL259, also known as a UHF connector, is fine. Above that, you'd use an N connector. Okay, so standing wave ratio. Now is a good time to talk about standing wave ratio. So a feed line, we're going to talk about feed lines and antennas. A feed line is something that's used to transfer power up to an antenna from a transmitter. All right, so a feed line is essentially your conduit through which your transmitter sends power to the antenna. So an antenna is going to have an impedance. A feed line is going to have an impedance, which is a characteristic impedance, and your transmitter is going to have an impedance. Ideally, all of these have the exact same impedance. If they all have the same impedance, they are matched, and you have a good impedance match. A signal that goes out into the cable will go through the cable and get to the antenna and be radiated into the world and never come back. If you have something called a mismatch, you basically have the equivalent of having the jump rope tied to the doorknob, or at least partially tied to the doorknob, in which case you have this right here, and some of your signal goes out into the world and some of it bounces back. And then when it gets back down to here, it's either dissipated as heat or it goes back up here, at least part of it, and some of it goes out and some of it comes back, and then some of it gets dissipated as heat and some of it goes back out. And notice that it's echoing up and down the cable multiple times. That's typically not a good thing. For us, it doesn't matter so much. If you're running a TV station, you get echoing and ghosting on your picture. And then somebody calls you and tells you that we can't watch your TV channel because your signal is dirty. So having a good impedance match is really, really important for certain applications. Now, in the case of us, what ends up happening is that as every time the signal comes back down, it transfers energy to the transmitter. And energy that is not used for anything else comes out as what?
Smoke.
Heat. It generates heating. All right. And what kills transistors more than anything? Heat and overvoltage. But they're really one and the same. So overvoltage and heating. So you can generate overvoltages in your transmitter because of the signal coming back. You can also generate lots and lots of heat. Now you're already generating some heat because nothing's perfectly efficient. So which means now you have all this extra heat to get rid of. And if you're not careful, you can destroy your transmitter, and nobody wants to do that. So what we do is we add a device right here. So here's our transmitter. And here's our matching network. And here's our feed line. And here's our cable. Or here's our antenna. Okay, so when we see this, this is going to be 50 ohms. This is going to be something, Z. This is going to be something, Z. And we have this matching network. What the matching network does is allow us to use, again, capacitors and an inductor, all being variable, to take what the impedance is over here and match it to what the impedance is on the other side. That way, when the signal goes up and out, if some of it bounces back, it gets caught and turned around and sent back up. And then some of it comes back, and then it goes up again and bounces around a few times. But notice where it never makes it back to. Where does it never get back to?
The transmitter.
The transmitter. Because we have tuned it so that the transmitter sees the world as a 50 ohm impedance, which is exactly a perfect match for what the transmitter is expecting. And as far as the transmitter is concerned, even though the world is not so good out here, the transmitter doesn't know that. As far as the transmitter is concerned, the world looks fine. So this is a way, by using a matching network, of protecting your transmitter from being damaged and also protecting things from overheating.
So your friend could have used a match.
Yeah. Well, which friend?
The one that made smoke in his transmitter.
Oh no, he just should have started at lower power. I think he just should have started lower power. But here, what can cause erratic changes in SWR? A loose connection in the antenna or feed line. The other thing that can do it is a short circuit right there. That can cause all kinds of problems. Standing wave ratio is a measure of how well a load is matched to a transmission line. A perfect match is known as a 1-to-1 impedance match. So that's your SWR of 1-to-1. 1-to-1 is a perfect match. An SWR of 4-to-1, if you ever see that, is an impedance mismatch, and a pretty serious one for that matter. A benefit of a low SWR is that you have reduced signal loss, because even if you have a matching network, if you have a mismatch, like up here at the antenna, you're still bouncing signals around up and down the cable every time. So let's say that your cable run has a loss for the entire cable run of 3 dB. And your signal has to go up and down and up and down and up and down 6 times. How many decibels is that? Every time it passes through, it loses 3 dB.
9. Negative
Well,
9.
it's actually 18 because it's 3, 3, 3, 3, 3, 3. It's up and back. So that last time through, it's 18 decibels of the original of the signal that's, going through. So, I mean, it's, it's pretty serious. That's why it's important to have cable that's, if you're going to be dealing with high SWRs, some of your signal went out in the first place. So it's really not as bad, but if you make multiple passes through the cable, every time it goes through, you're burning up some of your energy. And energy that gets burned up, where does it go?
Heat.
It keeps your cable from freezing up in the wintertime. It doesn't transmit any kind of signal, does it? So now it might not be bad to have a cable that doesn't freeze in the wintertime, but that's not the ultimate goal. What happens to power loss in a feed line? It turns into heat.
Heat.
Yep. Why do most solid state transmitters reduce power output as SWR increases beyond a certain level? And I can show you this. We already kind of covered it. So here's our transmitter. And let's just say we're going to have a mismatch. And let's say our transmitter is operating at 30 volts. And it sends out a signal. And of that, part of the signal comes back at 18 volts. Coming back down. If they happen to be in phase, how much voltage do you get? You get 48 volts. What if your transistors can handle a maximum voltage of 33 volts? What happens to your transistors?
Smoke.
You smoke them. That's right. So, so this is a pretty severe SWR. And what happens is most modern transceivers, when you transmit, will sense how bad of a match it is and how much voltage is coming back. And it will say, okay, well, clearly I have a maximum of 33 volts. I can't go higher than that. The only way I can achieve that is by reducing our output voltage to 15 volts. And that way, when it all comes back, I'm only going to see, let's say 12 volts, and then that'll be 27, and that'll protect my amplifier. Keep it from getting fried. That's known as fold back. And it's designed to protect the transistors. What should be considered when selecting an SWR meter? I could build, for instance, something called a tiny tuner, which looks like this. Does that look familiar to everyone?
Mm-hmm.
Okay. That has it's designed for low power levels and has a maximum power capability of 5 watts. There's another one I can buy, which is like a Dentron something or other that looks like this. Wow, it looks exactly the same, which has a power handling capability of 5 kW. Essentially, they're the same system, except that this one with the 5,000 watt power handling capability is probably 24 inches wide, 24 inches deep, and 12 inches high. Whereas this one right here fits in my pocket. But they do the same job, except they don't do the same job on the same amount of power. So it's also entirely possible that because there's metering, because you need to know how to make your tuning, some tuners will work at frequencies that other tuners will not. So for instance, I have a 2-meter antenna tuner, which won't work at HF, and I have HF antenna tuners that won't work on 2 meters. What instrument can be used to calculate SWR or determine SWR? That's a directional watt meter. Basically, a directional watt meter measures the power going up and the power going back. And with those two numbers, you can actually calculate the standing wave ratio. It's a mathematical calculation. an RF power meter should be installed between the transmitter and the antenna, because if it's not installed, actually, it should really be installed as close to the antenna as possible, but between the transmitter and the antenna. How do you determine if an antenna is resonant at a given frequency? All right, so I'm going to draw a little bit of a scenario here. And let's say that I have an antenna that has an impedance or an SWR that looks like that. And this is at 12.4 megahertz. Okay. Now, if we look at our frequency charts, you will see that 12.4 megahertz is not a ham band. It does not fall in a ham band. But it might turn out that you're coming up with a brand new antenna and you said, oh, well, it's 12.4 megahertz. Huh. But that's not a ham band. Well, how do you know that it's 12.4 megahertz if you're not legally allowed to put out a signal there? And the answer is you don't. So what you would use in that case is something called an antenna analyzer. Okay, here's an antenna analyzer. Okay, so here's a very simple antenna analyzer, which is actually not simple at all. It's actually very complicated. Anyone ever seen one of these? It's called a nano VNA. Notice that's measuring in decibels. This is basically giving you a standing wave ratio on given frequencies. We can also do something like this. And let me share that. Can everybody see that? That's a little more expensive. It's a vector impedance antenna analyzer that works from, here we go. It gives you a nice little graph. Well, the way that it gets away with it is that it is a 1 milliwatt transmitter, which is not a ham radio transmitter. It's just a generic transmitter. And it's allowed to sweep from 0 up to 60 megahertz and give you a test of its standing wave ratio at all those frequencies that you're not legally allowed to transmit on as with using a transmitter, a ham transmitter. So that's known as an antenna analyzer. Okay, let's see. What's the major function of an antenna tuner? Matches the antenna system impedance to the transceiver's output impedance. And how many ohms is a typical transmitter? See if people remember
50.
that number. 50 ohms. Yep. It's pretty much an industry standard. Okay, the primary purpose of a dummy load. So I'm going to draw a dummy load. This is a dummy load. That's a dummy load. What does that look like?
Resistor?
A resistor. That is a 50 ohm non-inductive wire wound resistor. Okay. Now, why would it want to be non-inductive? What do we know about inductors? Remember, they are frequency dependent devices. Their impedance changes with frequency. Well, if we want a 50 ohm resistive load so we can dump 1,000 watts into it, we really don't want it to be an inductor also. It wouldn't work very well. It wouldn't be 50 ohms anymore, and it would change at every frequency. So essentially, it's a big resistor with a heat sink on it. And this could be, when I say big, it could be 10 watts. I've seen them as big as 2,500 watts. Essentially, you fire up your transmitter at 1,500 watts, fire up your amplifier, and use it to heat the room in the wintertime. Okay, the main purpose of having a dummy load is to transmit signals without transmitting them over the airwaves. You want to see how much power your system puts out, you transmit it into a dummy load. So, and a dummy load is a non-inductive resistor mounted on a heat sink. Okay. Well, let's see. How's everybody doing?
Good.
Good.
It's a lot.
A lot.
I'd like to apologize again for throwing out an S bomb there. I feel kind of badly about it. We have some kids here, and I feel badly.
Oh.
Not that they probably haven't heard it before, but you know. So my apologies to everybody. I'll try to not do it again. All right, we're into amateur radio signals. We're on page 61. Okay, so what we're going to get into right now is modulation techniques. So in order to understand what modulation is, we have two things. There's something called a carrier and something called modulation of the carrier. So a carrier frequency is just a sine wave at a given frequency, just some sine wave that is just a sine wave. There's nothing that's happened to it yet. All right. In order to send information, has anyone ever heard of a modem?
Mm-hmm.
Do you remember what modems are? Wait, I see Jacob saying no.
Oh.
I guess you missed that entire era. Good for you. Okay, a modem is a modulator demodulator. That's what MODEM stands for. And it allows you to take information and encode it onto a carrier signal and then pull it off at the other end. So that is a modem. Now, it is also true that a modem in the classic sense operated at something like 300 baud, which is very, very slow, right? And then we went to 1200 baud and then 2400 and 9600. And then we went all the way to 19,200 and then 57,600. This is bits per second. This is bits per second. Still pretty slow compared to what we have with Bluetooth and what we have with all those other modes. But to be totally honest, these are the kind of bandwidths that we get when we're talking about ham radio, unless we're going into the gigahertz range. And that's because of bandwidth considerations. Remember, when we're transmitting something over the air, it takes up space. So let's now look at the frequency spectrum, and we're going to draw our FC, which is our carrier frequency right here. That's our center frequency. That's just going to be a sine wave at a single frequency. Now, that's very boring. It has no information on it, and it also takes up no space, believe it or not. It takes up no bandwidth. But now we can do something with this. What can we do with it? Let's hear some things we can do with that to make it interesting.
You could amplify it.
You could make it bigger. You could make it bigger and smaller. You wouldn't change the frequency, but you could make the amplitude bigger and smaller. Okay, that has a name. That's called AM. What else could we do with it?
You could change the frequency slightly, or you
yep.
could shift it.
You could change the frequency slightly and make it a higher and lower frequency over time, and higher and lower. We're changing the frequency. That's known as FM. You could also change the phase of the signal. So instead of having just this, you can also do this and suddenly shift it from there, have a discontinuity where it jumps down to there and keeps going, and then it changes. That's known as phase modulation, where you basically shift it. Let's see, other things. We can do, how about turning it on and off? How about just simply turning it on and off? What's that called?
Is that PWM?
Nope.
CW?
CW. That's Morse code. We just turn we just turn a signal on and off. We turn a carrier on and off, and it gets decoded at the other end as ons and offs. So we can also do something that looks like this. We can have a signal that goes like this, and then suddenly we change to a lower frequency for a certain amount of time. And then we switch back to a high one, and then switch back to a low one. That's actually known as frequency shift keying. This is how teletype works. This is how FT8 works and lots of other digital modes. So there's a lot of things we can do to make a radio wave more interesting. But every time we do something like that, what happens is that now it takes up space. Information requires bandwidth to transmit. Certain things take up more space than others. For instance, I can do, for instance, CW. CW takes up, CW takes about 150 hertz of space. AM, which was red, takes about 6,000 hertz of space. FM takes up about 15,000 hertz of space. Pulse or FSK, depending on how it's set up, that can actually have a spike here and a spike here. So that can be one channel. Pulse width phase shift keying, which was the blue, that can be something really narrow like this. So as you can see, all of these different things take up a lot of different spaces on the band, right? Depending on the mode of modulation that you're using. One of the ways that we can simplify this is we can actually take this AM signal and we can only transmit half of it. And that's known as single sideband, because it turns out that the upper and the lower are actually mirror images of each other and contain exactly the same information. So they're completely redundant. So if we only transmit one, we've saved half our power. And actually, we've suppressed the carrier as well, and that saves more power even than that. Okay, so the most commonly used modulation technique for voice repeaters, that would be PM or FM, both. One is phase modulation, one is frequency modulation. Most of these little radios that you get, most handheld radios, are going to be FM radios. For VHF packet radio transmissions, I'll turn this on, and usually I'll hear something on packet very, very quickly. 14439. We'll see if we hear anything. Okay, so I'm going to keep this here. When you guys hear a squawk, you'll know it. Now I'm getting impatient. Can everybody hear the noise? No? Okay. It's not going to work then. I guess Zoom is really good at canceling noise. I know Zoom is really good at canceling Morse code. I teach Morse code classes over Zoom, and I actually have to turn off a lot of the noise canceling, or else it considers Morse code noise. So VHF packet radio. Packet radio is essentially digital information sent over FM radio. So packet uses FM or FM or phase modulation as well. Amplitude modulation, a type of amplitude modulation, as we discussed, is single sideband, where you basically only transmit one sideband. For weak signal work or long distance work on VHF and UHF, we often use single sideband. A lot of people also use digital and Morse code because those are very narrow bandwidth modes. But if we're talking about voice on VHF and UHF, we're using single sideband. You can use either an upper or a lower sideband. Okay, so now one thing that's interesting here, and we're getting to the end of today. Everybody can take a nice deep breath. Okay, so we're looking at the split point between upper and lower sideband. Well, you see this band that says 30 meters, that says CW and data only? There's no voice allowed on that band, but that's at 10 megahertz, and 10 megahertz is the break point for whether you use upper or lower sideband. The easy way to remember, if it's above the frequency, you use upper. If it's below that frequency, you use lower. So on the 10 meter band, for instance, that's 28 megahertz, which is above 10. So we would use upper sideband. Okay, let's see. And let's see, what's a characteristic of single sideband compared to FM? A lot narrower bandwidth, also typically a lot lower fidelity. Single sideband signal is about half of the 6 kilohertz for AM, which makes it 3. A VHF repeater signal is going to be between 10 and 15 kilohertz. Again, that's why it's nice and clear and clean, because it uses a lot of bandwidth, much higher fidelity. A disadvantage of FM compared with single sideband is that FM has something called a capture effect. Only one signal, the strongest one, can be received at a time. And this is actually why aircraft radio still uses AM, because if there are 2 airplanes on the same frequency, you want to actually be able to hear both of them. Because if you were using FM, you'd either hear one and thus not the other one, or you'd hear neither. And again, that's something called the capture effect. The approximate bandwidth of AM fast scan TV is about 6 megahertz. AM fast scan, analog fast scan, also uses something called the NTSC. NTSC is television. CW is another name for Morse code. CW also has the narrowest bandwidth, which is about 150 hertz. Finally, what's an electronic keyer? An electronic keyer is a device that assists in the manual sending of Morse code. The nice thing about an electronic keyer is that it sends dits and das for you instead of you having to do it, and it will send a long string of them. If you're sending faster, it's a lot less tiring than doing it with your wrist. So anyway, I think that's a good stopping point for today. And does anyone have any questions? I'm sure there are questions.
What was that website you were at first thing this morning where you could look at the different radio bands and see what was on them?
Well, okay, so what? Okay. Okay, so let's go to WebSDR. Let me share this. Okay, so I think we're talking about WebSDR. These are all WebSDRs around the world. As you can see, there are many, many, many of them. This is where they're all located. The one that I actually like the most because it has a continual coverage of the entire HF band is the one that's all the way on the top. And that covers all the way from 0 to 30 kilohertz continuously, or 30 megahertz. Can everybody see that okay? Can everybody hear it?
Yeah.
Okay, good. And once you're there, let's just type something in. Let's go to 10. Not going to hear anything there. Let's try, ooh, there we go. Okay, so this is what happens if you have the wrong mode selected. So this is more listening to Morse code using AM. Because AM expects there to be a carrier frequency there, and CW doesn't have one. However, sideband modes and CW will actually re-inject a carrier into it. You can also do stuff like increasing the filter widths. You can also zoom in. It's so cool. You can change your filter bandwidths. Slide it. There we go.
You could easily get lost playing with that.
Oh yeah. And what's cool is that it covers the entire high frequency band. Does everyone remember the limits of the HF band? 3 to 30 megahertz.
3
right?
to 30.
And this
Yeah.
covers the entire HF band in one continuous image. The other cool thing about this is that this is actually called a waterfall display. And it gives you a pictorial view of what it is that you're able to hear. Let's go to upper sideband. Zoom up to here. Okay, so this is actually a guy who's is on Prince Edward Island, I think, and he's being heard on this SDR in Europe. Okay, so is that what you were asking about?
Yes, sir. Thank you.
Oh, good. Okay.
That's pretty cool.
It's pretty cool, yeah. And there's a whole bunch of them all over the world. So if you want to hear what, like one thing that's actually kind of cool is transmitting somewhere and like from here and listening to the system in Utah and being able to hear yourself and being able to listen what it sounds like when it gets to the other end. It's actually kind of cool. There's another one in Northern California that I did that on, where I was just listening and I could actually, you know, like, well, I kind of know what my signal sounds like, but like what I thought it was really cool to actually be able to listen to a delayed received version of myself and see what it sounded like. All right, other questions? I know there's got to be a few. Any questions about the exam?
Hey, Scott, I had a question.
Yeah.
Back to I don't know if you still have your whiteboard up.
Yep.
Where you had all that stuff drawn on there. Difference between AM and FM. So AM is amplitude modulation, and FM is frequency modulation. Yeah, you drew that line down there at the bottom, and that represents the frequency spectrum.
Right.
Like what I don't understand, if AM is amplitude modulation, that to me that means, you know, the peaks and the valleys go up higher, but the frequency stays the same. So if I'm changing the height and depth of the wave, but I'm not changing the frequency, why do I take up, I think you said it was like 6,000. Why do I take up bandwidth? Why isn't it just the sliver?
See, that's something it's kind of messed up, isn't it? So, all right, here's another one that will sort of blow your mind a little bit. Okay. So let's say that I have a wave that looks like this. What's this known as?
That's CW.
That's Morse code.
Morse code, right?
Okay. How many different frequencies are in there? I mean, what frequency? If this is all at the carrier frequency, what frequency do you see?
I think there's just one.
There's only one, right? Okay. What if I were to tell you if I took a visual representation of this on the frequency spectrum, it would look like this? Does that make any sense?
No.
No, it doesn't. And this is actually something that comes from the fact that the signal is being turned on and off. The fact that anything is happening to it, if I were to not turn it on and off, those sidebands would go away. The fact that I turn them on and off generates sidebands. It generates other frequency components. And it's really hard to explain without Fourier analysis and a lot of calculus.
That's where my mind was going when you drew that spectrum down there. I was reminded of your earlier today, the Fourier, where we can't do, what was it? We can't do square wave.
Yeah.
Because of that.
Right.
And I was wondering if it's a similar, I mean, that's on and off and on and off. It's almost like a block square wave.
Okay, now here, look at this. Okay, do you see that?
No, I just see you.
Oh, I'm not, I gotta share it. Hold on. I thought I had it shared. Okay. Can you see that picture?
Yes.
Okay. I want you to look at here. I'm going to zoom in a little bit. Okay. It's only a single tone switching on and off, right?
Yep.
Agreed?
Yeah.
What do you notice is happening when we're looking at the spectrum of it, right? When it's transmitting, when the guy's transmitting, look what happens to his signal. Now he's going to make a liar out of me again. Come on. What do you see? Is it a perfectly straight vertical line?
No, it's fuzzy.
It's
Is
fuzzy.
that an artifact to the fact that the antenna is not a digital device?
Those are actually sidebands. Those are sidebands that are generated by Morse code. And the thing is, if you go slower, the sidebands won't be spread as far because you're not sending as much information. Doesn't that mess with your head? I know it does mine. And I went through lots of engineering school for that. And it still messes with my head. Like if we go to a slower one, let's see if I can find a slower one. And notice that a weaker signal, you won't see them as easily. The reason you won't see them as easily is because they are weaker. But if you can actually see it, they are actually there. And the first time I saw it, I was like, no, that can't be. Let me try. The slower you go, the narrower the signal gets. Like this guy's going fairly slow. Right? This guy's going, he's going faster. His sideband spread out further. Same with this one. And when it gets stronger, you can see that it's fuzzy wider. Yeah, isn't that a trip?
Yeah.
Yeah, I thought so too. And the fact that if you're dealing with phase modulation versus FM, phase modulation doesn't change the frequency either, but it takes up bandwidth. It just changes the phase of what's happening. You know, it changes the phase of the signal. And, you know, frequency shift keying just basically like, you know, phase shift keying just does that. It moves it around. And if you look at, there's a mode called PSK31. There's a whole bunch of PSK modes, which are phase shift keying. They only use a single frequency, and whenever there's data that comes across, it changes the phase. When it changes the phase, it causes there to be bandwidth. And this is honestly a direct result of Fourier analysis and Shannon's information theory, which basically says sending information requires bandwidth. The first time I saw it, I couldn't believe it.
Oh, okay. I accept there's a ton of math and explanation behind it, but I don't understand it. But thank you.
Well, you know, before you go, let me just see. Fourier analysis of CW. Okay, let's see. Let me see if I can find it. Morse code decoding from its spectrum. Yeah, essentially, if you think about it, it's basically a square wave, and square waves generate sidebands independent of the carrier frequency. So, yeah. Yeah, it's hard to explain without some pretty heavy calculus.
Basically, the more changes there are in the signal,
yep,
it starts looking blocky, which then starts obeying the math of that Fourier with all those echoes that go on down in multiples of whatever wavelength.
Yeah. Well, it's harmonics of the modulating frequencies at that point. Not harmonics of the carrier frequency, but harmonics of the modulating frequency. So you get a combination of the two.
I didn't expect that.
Yeah.
The harmonics of how fast you're changing the frequency.
Yeah.
Not
that's what
of the carrier frequency. Okay.
Correct.
Wow. That's really even more complicated. Okay. Thank you.
It's like essentially it's a multiplication of a carrier with, like, it's amplitude modulation is like a of t cosine omega t in time. Essentially, it's a multiplication of a modulating signal with a carrier, and one is changing much faster than the other one. Here, let me see if I can find that. AM formula modulation formula. Okay, amplitude modulated wave. Okay, here we go. It's been a long time since I did this. But basically, here's it's misspelled, of course, but so modulating signal is V sub M sine omega MT, carrier signal is V sub C sine omega CT, and then you end up with a combination of the two. Oh, there we go. Okay.
Oh my God.
Yep. And look, and the end result is a carrier plus upper sideband plus lower sideband, which is true. It's both sidebands, which is why it turns out they have equal information. So it's really amazing. The mathematics that's involved in this stuff working at all is really quite amazing.
Mm-hmm.
The fact that I actually went through this in school is even more amazing. And the fact that I forgot a lot of it or forgot most of it is the most amazing thing of all. So.
I got a question. You mentioned before that you taught Morse code. Do you still do classes for that?
Yep.
Okay.
That's still my favorite mode of operation. All right. Any other questions before we come back at about the exam or anything like that? Go try some practicing. Go try some practice tests. And maybe hopefully you'll know more than you did before this morning started. I hope everybody's brains aren't completely fried.
Yeah.
I know it's a lot.
It's a great class. It really is. Thank you.
I appreciate it.
Yeah, thank you.
And did we did we lose Victoria and or are they still here?
I'm still here.
Victoria, and your sister's name is?
Yeah, I'm still here.
You're still here, Natalie. That's right. All right. So you haven't totally glazed over yet?
Kinda.
Okay.
Like
close.
I think around an hour or half an hour ago, things just started like going over my head, and I was like, okay, I guess I'll just review it later.
Okay.
I'm in the same boat.
Okay. Well, at least you can bounce it off each other. And what I tell people is that I teach a lot more than you need to know for this test. But what that also does, I think, is it gives you a basic understanding of the stuff behind it. So if you can't remember something, you look at, okay, I remember that we did mention that, and with a little bit of extra practice, the general exam's like that far away. Because most of the material that I teach is very, very similar to what you do for the general exam.
So do you recommend taking both tests on the first day?
Well, okay, so what you won't know is you won't know the band limits and things like that. And, like your maximum baud rates and stuff like that. It really adds about HF operation. But I know people who have gone through and looked at the practice exams for the general exam. It's about 60% the same stuff. So, I mean, if you crush the technician exam, I would definitely take the general. What? Yeah. So, all right, I'm going to have to run. My daughter's giving me the, come on, Dad.
Okay.
So,
okay, Scott,
yep.
are we going to be able to get a copy of the recording?
Yes, it'll probably be up by, I'd say 6 o'clock or so our time.
And then how do we access it?
I'll send everybody a link.
Oh, okay. Thank you so much.
Yeah.
Okay.
All right. Good
All
work,
right.
everyone.
Thank you.
Thank you.
Thank you.
Thanks so
See you
much.
in the morning.
Thank you.
Yep. See you in the morning.
Thank you.